Test, test. Okay. Good morning, everyone. Welcome to Purdue and to our third edition of the Quantum Science Center's Summer School. We are so excited to have you here at Purdue University. I'm David Stewart. I'm the Managing Director of the Purdue Quantum Science and Engineering Institute. If you guys have any questions throughout the week or concerns or issues, please find me or our team out at the registration desk to help you out. Before we start, I just want to do some thank yous up front. First, I want to thank all of our corporate sponsors, which are Inflection and JP Morgan Chase. So thank you, Dana. I don't think Marco is here yet, but round of applause for them. And then I also want to thank our internal sponsors, both the College of Engineering and College of Science, the Quantum Science and Engineering Institute, and the departments of Chemistry and Physics and Astronomy, and the Elmore Family School of Electrical and Computer Engineering, and also the Emerging Frontiers Research Center. So we couldn't do it without their internal support. Also want to thank Oak Ridge and QSC, of course, and Department of Energy for their support. Next, I want to thank all of our speakers who have traveled great distances or short to be here and help make this a very exciting event and super beneficial for our students and postdocs in attendance. And lastly, I want to thank all of our team that helped put this together. Sandy Araji, Tracy Hudson, Thomas Roth, Blake Wilson, Morris Yang. Did I forget anyone? Sasha? So this couldn't have happened without them. So if you see them out there in the hall, please say thank you for their efforts. So yeah, round of applause for them. So with that, I will hand it over to our fearless leader, Professor Sasha Baltaseva.
Thank you. Well, I'm so happy to welcome this crowd, and especially after COVID, and even last year for our second summer school, we didn't see the crowd which is as big, and we can compete, I think, with the most attended conferences right now to welcome you all here. I wanted to start with a short story. So recently, my sixth grader asked me, she's like, "Mom, why no one ever visits Indiana? Like, we go to California, Florida, Italy." And I'm like, yeah, well, I don't know. And then yesterday, I'm like, we are hosting a big 120 people summer school here on campus. And she got so excited and so proud. Yeah, makes sense. Purdue is such a great place. And I totally agree, because Purdue is in bloom, both literally and in terms of what's going on here. We are very, very proud of the program that we put together. For this Quantum Science Center Summer School, we are going to highlight not only our research, but also research and developments that are coming out of other DOE-funded quantum centers. So we will feature talks, presentation, posters from Quantum Science Center and Purdue and all over PIs, researchers, postdoc students from academia, national labs, and industry. And we're also happy to announce that we are collocating this with some presentations from the Emerging Frontiers Center of Crossroads of Quantum and AI at Elmore Family School of Electrical and Computer Engineering, so that you will get exposed not only to the latest development in quantum science and engineering, but also to machine learning advances as well. And as you know, these are two ongoing revolutions that are shaping the future society. Without further ado, I guess we should move on. And it's my pleasure to introduce the next welcoming speaker from College of Science, Associate Dean for Research and Partnership, Gar Simpson. Thank you.
Thank you, Sasha.
Welcome. It's so great to have you guys here. I'm really honored to be up here and representing Purdue in our enthusiasm in having such a great cohort here. Oh, sorry, I need to bring this closer to my mouth. Thank you for that little peek. Let's see, I'm a chemist, which means quantum mechanics is really at the core of what I would know and love. It's the wave nature of the electron that defines chemical bonding, and that is really central to everything in chemistry. So I've always, even from my early days as an undergraduate when I took PChem for the first time, it opened my eyes to the world of quantum. Now, obviously, quantum's been around a long time, but in the past few years, it's been really exciting to see the revolution of it, in computing, the new platforms, the new quantum mechanical aspects that are being constantly discovered at the edge of physics. And it's great that we're able to harness that, pass that information and knowledge on to the next generation of investigators. So I'm really excited to be up here representing Purdue and welcoming you here. Purdue sees this as an area where we are excited to grow. And there's been a lot of investments and a lot of opportunities at Purdue it overlaps with initiatives in quantum mechanics and quantum science. We just announced pillars in Purdue Computes with 3 arms, one in expanding the ties between computer science and electrical and computer engineering, essentially breaking down those barriers between the 2 different colleges. And that's really critical for establishing interactions that harness the complete capacity of the university. There'll be a bunch of 50 new hires in that area over the next few years, and some pretty substantial investments in semiconductor manufacturing that you'll have later on in your day. You'll have a visit to Berk, and that's our sort of centerpiece for driving that initiative. And of course, the quantum mechanics and quantum computing is going to lay the foundation for the next generation of innovative computational architectures. So we're very excited about the future that this area holds. So I'll just say again, welcome, and I hope you have a great 4 days here at Purdue, and go team. So I'll go ahead and hand the mic back to Sasha. Let's see, here you are. Or who should it go to? All right.
Thank you so much.
Absolutely.
And thank you again for your support. So we are starting with our first welcome. And now I'm turning it over to our director of the Quantum Science Center. And thank you, Travis, for driving us forward. We are very excited about everything that's going on, and I hope that everyone in this audience will learn about the excitement stuff we are doing at the Quantum Science Center. Our director, Travis Humble.
Great. Thanks, Sasha. Great. So good morning, everyone. It is an absolute pleasure to be here. As Sasha said, I'm director of the Quantum Science Center, and I'll tell you a little bit more about what Quantum Science Center is, but what I want to explain first is why you are so important to me. This school is part of what we do within the center to address our country's strategy for building out quantum information science as a technology, not just for discovery and innovation, but to set a new technology base for the 21st century. And so what you are today are that workforce. Those people who are going to assimilate this understanding, this information, and make a step forward on that progress. So that's really important to me. It's really important to me that this is the 3rd annual summer school that we've held here at Purdue University, and I want to extend my thanks to Sasha and David and the entire Purdue team for making this a really successful event. It's actually the first time I've been able to attend. You all may not remember this, but there was a pandemic that happened over the course of the last 3 years, and that's impacted everyone's life around the world. It also prevented me from being able to travel, and it prevented many people from being able to get together and to share ideas. But what is surprising is that it did not prevent Purdue and the QSC from putting together these summer schools so that we can put forth the best ideas that we have around quantum science and technology. The reason that I think workforce is so important isn't because I'm concerned about filling out job applications with our industry partners, with our national lab partners, or even with our universities that are looking for faculty in these areas. Those are immediate near-term needs. Yes, we have to address those. What I am more concerned about is that 10 and 20 years from now, if we continue on the trajectory that we are going, quantum technology will be pervasive through our society. Whether you're talking about communication systems, computing systems, sensor systems, new types of materials, new types of devices, where is that expertise going to come from? Who's going to understand how that technology works? When you think about how other technologies have been disruptive, the internet or mobile phones, how quickly were we able to adapt to those? Pretty dang fast. Compare this to the development of electricity over 100 years ago. When that suddenly became a commodity, our society changed. The types of things that we could do, the way that we did them, huge revolutions in human behavior, all because the technology itself made a fundamental difference. We're seeing that happening now. We're seeing our ability to harness quantum mechanics making an enormous difference on what we can actually do in these information technologies and potentially beyond. So for that reason, you all are really important to me, because what you're going to learn over the next several days is the ability to take these ideas, to discover what they're capable of doing, and hopefully to innovate on what we as a world can do going forward. Okay, that's my pep talk. Hope that's okay. It's really impressive, the amount of people that have taken time out of their lives to come to the school, both to learn, but then also to teach. And so I would like to extend my thanks to all of our visitors who are lecturing today, because I know that this is an enormous commitment on their part, both in terms of making the presentations, 6:30 in the morning, trying to get them together on time, as well as the travel and the coordination of logistics. But I also know that they share my opinion that this is really important. And so thank you. What I hope you get out of this is, one, a better, deeper understanding of what quantum science and technology is. But then two, maybe you have some questions. Maybe you piques your curiosity as to what we should be looking at going further. So I would encourage you to also use this event as a way to talk with each other, to talk with our teachers, our lecturers that we have. Please come up, introduce yourself to me. I'm really interested in understanding how you view this type of new technology, this type of new field of discovery, and where you think it should be headed going forward. Okay, so I think I've said my thank yous. Tried to get you all a little focused about what to be thinking about for the next couple days. I've got good news and I've got bad news. The good news is I'm done. The bad news is I'm also your next speaker. So let me turn it over to David, though. I think he's going to get us set up, and then we will get going on the first presentation. Any questions so far, though? Does that work? Okay, so let me talk about discovery and innovation with quantum science and technology. And I'll give you a little bit of background on myself. Like Garth, I'm a chemist. I was actually a theoretical chemist, did my PhD at the University of Oregon. I was looking at the control of chemical reactions using optical pulses. Pretty exciting field of study. And then when I graduated, I wanted to make a change, try a new topic, and I was fortunate enough to get a postdoc position at Oak Ridge National Laboratory. This is one of the Department of Energy's federally funded research and development centers. It has a broad scientific mission. And one of the things that they were looking at the time was something called quantum teleportation. And quantum teleportation is this idea that I can transfer information between two locations without that information traveling in the space in between. It's really kind of remarkable. And that got me hooked. right? So I became invested in the idea that we could start to think of quantum mechanics not just a theory of physics and chemistry, but also as a framework in which to reason about nature. So if you think about the types of nature that's around us, especially within the Department of Energy and their priorities for scientific discovery, things like the high-energy physics experiments that are going on at Fermilab and CERN, the Large Hadron Collider, and other locations are giving us insights into how the fundamental particles interact with each other. And that's a great, let's call it scientific problem. It's interesting. There's a quantum mechanical model there, the standard model that you can start to probe. But what's remarkable is that those interactions are at the core of how things like the sun behave. So now when we say that we want to understand nature around us, we're not just talking about understanding thermodynamics and classical mechanics. We're talking about understanding quantum mechanical phenomena as detailed as how individual subatomic particles behave in relationship to each other. Well, a little closer to home, you can look at materials like superconductors, where we know that when we cool down that material to a certain critical temperature, that it actually loses its ability to resist the flow of electrical current. And that's a remarkable feature because now you can think about creating transmission systems for energy that actually have low loss. Department of Energy, of course, cares about this as well because that plays an enormous role in our ability to be energy efficient. Can we create energy distribution systems taking advantage of superconducting transmission lines that have much better energy efficiency? Well, it turns out one of the critical concerns there is that critical temperature. How do I prevent that temperature from being so low that I need a bulky infrastructure that's very costly and expensive to maintain and operate and offset the distribution costs for those energies? Well, maybe even a little more focused is the understanding of how we use catalyst. That's a picture of aluminum. It's incredibly popular as a way of trying to mediate chemical reactions. It can actually help with the transfer of electrons. Catalysts in particular are important for things such as creating ammonia. Ammonia, you may know, is one of the key ingredients in fertilizer. So if we're going to try to understand how to make these types of catalytic reactions more efficient, we're going to have to get a better understanding of those electron transfer reactions, which again are examples of subatomic particles interacting with their surroundings. Now, this is a picture of Knoxville. We have a big gold ball, and that's literally what we call it. It's a leftover from the World's Fair back in 1982, I think. But I like this picture because it emphasizes what it means to have a sustainable city. And if we can create more energy efficient chemical reactions, we can support this vision of having a more sustainable society. But all of this goes back to that idea that I have to understand nature from the perspective of quantum mechanics. Well, that's not an original idea. In fact, it's just over 42 years old now that Richard Feynman, a well-known Nobel laureate in physics, made this point that if you want to make a simulation of nature, and we do, we use simulation as a tool for understanding, we'd better make it quantum mechanical. And of course what Feynman meant here isn't that the model of the simulation has to be inherently quantum mechanical, but the method of simulation should be quantum mechanical. That I should use quantum mechanics to simulate quantum mechanics. Of course, there's more to this quote. He says, and by golly, it's a wonderful problem because it doesn't look so easy. And my opinion is he was right about both halves of this statement. It's a great idea, but gosh, it's been 42 years and we're working on that still. It's good for making a career. It's got potential to make an enormous technological impact on the world. But we need really smart people to come in, have insights like Feynman did about what's going to be the best way to get there. Hence my comment about why you're so important. But it's not just me that thinks this is important. In fact, many countries around the world have initiated global efforts focused on the development of this idea, both for computing and simulation, but also communications, for sensors, for materials, for many different topics. In the United States, we actually have a National Strategic Overview for Quantum Information Science. And you can see here what are the 6 pillars of that strategy. The first one is to choose a science-first approach. So as opposed to going out and saying, well, let's all make QKD systems, or let's all make a computer that can crack encryption, the US has said, we're going to step back, start with the fundamentals, and work our way forward. And that's part of what the QSC is doing. That's part of what our research program is focused on. The second bullet here, you'll note, is to create a quantum smart workforce. And this is essentially what I was trying to say earlier. How do we enable an entire community of scientists to embrace the concept that quantum mechanics is fundamental to how technology should evolve in the future? And more importantly, even if you accept that, what do you do next? How does it change the way you think? How does it change the opportunities that we have? It goes on, it talks about other strategies, deepening engagement with industry. I was actually just in Boston yesterday at an event called Quantum Tech. Quantum Tech is really more of an industrial, commercial event, brings out a lot of the different companies working in this area. And one of the key things that they were concerned about is how are we going to staff our efforts? Where are we going to find the talent that we need in order to do fundamental research and do translational research, to do the engineering research, to work with people on how to turn these products into useful technologies? Critical infrastructure, well, of course, a lot of the things that we're doing right now depend on specific ways of doing them. I was talking earlier about the superconducting materials. You need typically some sort of refrigeration system to bring down those temperatures. Thermodynamic controls that can isolate the system from its environment. Shielding for electromagnetism and other stray fields. And then, of course, things like vibration control and interfaces to make these programmable. All of that type of infrastructure has to be built up from scratch. Maintain national security and economic growth. So why are we investing in quantum information science? There is a really strong national security argument here, and people may have heard this already. But in addition to Feynman's quote about simulating nature, there's a well-known algorithm out there that says that we would be able to decrypt information much more efficiently if we had a quantum computer available. Now, this is Shor's algorithm. We're not able to perform that algorithm yet on any meaningful size of encrypted message, but the potential for that to occur catches a lot of attention in the national security community. The same is true on the economic innovation side. Just like we were talking about energy distribution and catalytic reactions, the better we understand nature, the more that we can take advantage of it. We can control it and harness it for the purposes of our own good. That has huge implications for the types of economies that we have, as well as the types of products that we can create. And of course, we're not doing this alone. It is an international situation. There, of course, are geopolitical tensions going on all the time, but the advancement of science moves most quickly when we all work together. And so the 6th bullet point here is to advance cooperation around this topic with our partners. Now, I just realized that I'm looking at the pictures in the back and not pointing to them behind me. Sorry about that. Now, the Quantum Science Center was established as part of this national strategy in QIS. The QSC is one of the Department of Energy's National Quantum Information Science Research Centers. It was a competitive process. There's 5 of these. QSC is one of them. It's hosted by Oak Ridge National Laboratory, but it's a partnership of 16 different institutions, and Purdue University is our anchor partner in the academic space. We have 3 scientific goals that we're focused on: scientific quantum computing, topological quantum information and scientific instrumentation for QIS. And if you look at your agenda for the next couple days, you'll notice that these talks that you're going to hear will align with these scientific goals. And that's what makes this summer school unique, is that it's been tailored to the QSC in order to promote our scientific agenda and to align the material that you'll learn with the types of research goals that we're pursuing. Now, those 16 institutions include 4 national laboratories: Oak Ridge, Los Alamos, Fermilab, which is not too far from here, and then Pacific Northwest National Laboratory up in Washington. There's 9 universities. I won't read through all of them, but I'm sure you noticed Purdue up there. But there's 8 others, also essential to how we're performing our research. And then there are 3 industries. Cold Quanta, which is a branch of Inflection, and also a sponsor of our summer school. We're extremely grateful to them. IBM, which I think many of you will know for their Qiskit tools and their IBM quantum services. They play a key role here. And then Microsoft. And Microsoft is one of our major partners on multiple topics, including the development of topological quantum information. So we'll tell you more about this as the day goes on, but it is this network of 16 different institutions that make up the QSC. So within the center, we're actually thinking about many different technologies. We're not invested in just a single approach to how you can realize quantum technologies. You can see 4 examples up here. Ions, which is the idea that I can actually store information within an individual atom, typically within the individual electrons. Those atoms can then be trapped in different configurations. You can see an example of the traps on here. Oh, my laser pointer's out. You can see an example of the traps here that you would find at places like Quantinuum or IonQ. These are commercial vendors for these systems. The second is the superconducting technologies. Here, again, what you're doing is you're taking circuits made out of superconducting material, actually designing them in order to capture pairs of electrons that can be used to encode that information, and supercooling that system down in order to isolate it from its environment. And so places like Rigetti and IBM are working on this technology. Neutral atoms, which actually use electromagnetic fields in order to capture these individual atoms. Now, not like ions, they're not necessarily charged, but instead you can actually address the individual atoms and by varying the electric field, cause them to interact with each other. So companies like Cold Quanta and QEra are working on those technologies. And then finally, photons, which is maybe a stretch to call it a material, but the truth is the photons themselves are generated by sources which consist of materials, including semiconductors, that are then focused into channels like the waveguides that you see in the picture in order to interact and eventually lead up to scalable photonic quantum systems. Xanadu and Orca are 2 examples of companies working in this area. So there's many different materials out there that are the focus of quantum technologies, and you'll hear about many of those today. Well, the reason we want to build these technologies, the reason we want to harness those materials is so that we can start to test out some of these ideas. And with the QSC, our focus on scientific quantum computing actually draws from Feynman's original vision. We have a very strong focus on quantum simulation. This is basically solving Schrödinger's equation, but now using a quantum computer as the solver of that system. There are many different ways to try to tailor that algorithm in order to get it at specific applications. Maybe you're solving a chemistry problem. There's actually a little bit of the irony in my life at the moment. I spent all that time working on chemistry, then I left the field, and 20 years later, I'm having to remember a lot of that chemical jargon again. Because it turns out that these types of problems are very well suited for solving on quantum computers using quantum simulation algorithms. But the same is true for material science, high energy physics. You can even start to make these mappings over into more abstract spaces like machine learning, data analytics, and optimization. So there's a lot to explore in this space, but you need a good platform in order to do it. So one of the things that we're doing within QSC is actually taking advantage of all the different commercial platforms we have access to, as well as our in-house development of quantum computing systems, and pairing that up with computing systems that we have already developed. And this includes our high-performance computers, and what you see here on the slide is an example of Frontier. This is the world's fastest supercomputer located at Oak Ridge National Laboratory, and it's exceptionally good at simulating noiseless quantum computing systems. Our partners at PNNL have actually put out an open source code called SVSIM that can be used to program different quantum computing circuits and test their effectiveness and verify their correctness. But the SVSIM code quickly reaches the limit in the number of qubits that it can simulate even on the Frontier system, the fastest supercomputer in the world. And it's because fundamentally quantum mechanical systems will not scale well in classical models. It's the technology mismatch. And it's the reason that we're pursuing quantum computers in the first place. Now, we're pairing up our supercomputers with these quantum computers partly to do a verify and validation. We want to confirm that the materials that we've created, the devices that we've designed, are actually meeting the expectations that we have from our quantum circuit simulations. So that's part of the research that we do in-house with QSC. Some of this is giving feedback so that we can tailor these technologies. If you're thinking about the photonic system here, for example, the particular arrangement that we're using is based on continuous variable quantum optics. It turns out that there's a representation of that model that will map over into things like machine learning more efficiently, but that requires you to have direct access and control of those systems. So this is one of the advantages of doing this in-house. By comparison, we can also work with our partners in industry who are creating these devices independent of our own algorithms research. And we get access to that through something we call the Quantum Computing User Program. Here, the Department of Energy has actually bought access to many different types of commercial quantum computing systems. We then provide access to users like yourselves and other researchers who come in and test out their ideas on those devices. By publishing their results, they actually provide feedback to the vendors so that they can improve, and you get into this virtuous cycle of iteration. Now, the other thing that this does is it starts to form a community around the idea of what is scientific quantum computing. Well, it's the development of quantum computational methods applied to scientific problems and run on quantum computing devices. But that's not something that existed prior to now. But even those systems are going to have noise. And in fact, that's the biggest challenge at the moment today, is that our control over these materials is actually limited by our ability to reduce the amount of noise in their operation. Even by using these thermodynamic controls, even by using sophisticated techniques for mitigating against errors, we still encounter noise. You can see the progress on this slide in terms of superconducting coherence times, and this is taken from many different technologies over about the course of 20 years. And Aaron Cho from Fermilab is going to talk in more detail about this particular trend later. But what I wanted to emphasize is that one of the leading concerns at the moment, specifically for superconducting, but possibly for other materials as well, is that these coherence times may ultimately reach a limit due to their environment. And it's not necessarily something I would have thought of at first glance. It turns out that cosmic radiation from outside of the Earth's atmosphere, many light years, emitted from many light years away, is actually flooding this room at the moment. These cosmic rays, these particles are coming through and they're hitting these materials and they're being absorbed. And for quantum computing materials, the absorption of a cosmic ray actually leads to a significant amount of energy that disrupts the coherence within that system. This is what is expected to occur in the presence of these cosmic rays. Now, as the quantum computers themselves get bigger, they actually grow in size. So now I'm making an antenna for cosmic rays that's getting bigger and bigger with each generation of quantum device. Well, how much of a problem is that really? And is there a way to engineer a material that could actually mitigate against those types of cosmic ray energy concerns? Well, this is what we're working on within QSC. This is actually a new facility that we're creating at Fermilab called the Quiet Laboratory. It's located 100 meters underground. It's a clean room. They're actually in the process of installing it right now. This particular clean room will house a dilution refrigerator, and inside of that dilution refrigerator, we'll be able to put in some superconducting transmon chips that are actually being created here at Purdue University. Those chips will then become the sensors for cosmic radiation from which we can baseline whether or not the radiation is in fact making a difference on their coherence times. And the reason for this is that there's 100 meters of rock that is going to serve as shielding from those cosmic rays. Well, we can compare that particular experiment with an identical experiment, this one called the LOUD measurement. And this is located on the surface at Fermilab. Equal dilution refrigerators, we can actually either put the same chip in or different chips in, but we can do this comparative test between them to understand what are the effects of this. And this is research that's going on right now within the QSC. Another remarkable part of what we're doing is focusing on the scientific instrumentation that's needed for QIS. And in that experiment I was talking about, getting down into the experimental hall that's located 100 meters underground can take quite a bit of time. And it'd be much better if we could somehow automate the instrumentation that was needed to collect those measurements. So this is what our folks at Fermilab are working on, are these electronic control systems. You can see here an FPGA board that is actually an open source hardware. That means you can download the firmware online, upload it onto your own copy of that board, and use that for your quantum computing experiments. It's been interfaced with many different technologies, including superconductors, ion traps, and photons, but there's no reason it probably couldn't be extended to others as well. What's remarkable is that that has created a new community around the idea of instrumentation for quantum technologies. And by pooling together our resources, we're actually able to discover new ways of controlling these systems, and ultimately leading, hopefully, to more cost-efficient methods of creating those technologies. Similarly, we're working on another issue, which is how do I move my control systems closer to my qubits? These materials that we've been talking about, many times they are in these dilution refrigerators and they're being cooled down to low temperatures where conventional silicon electronics simply doesn't behave as expected. So again, at Fermilab, they're looking at the development of cryoelectronic control systems, basically ASIC circuits that have been designed in order to operate at 4 Kelvin or below. And this is the type of technology that actually brings in things like GlobalFoundries, one of the large semiconductor manufacturers, who themselves are not even sure how to solve this problem. Now, that's all well and good, and we can certainly understand where the noise is coming from in this particular case of cosmic radiation. We can do these remote experiments, but is there a way to get around this in the first place? And this is one of the things that makes QSC unique within the national ecosystem, is that we're investigating new types of ways of creating qubits as well. One of the ones that is most remarkable is the use of topological quantum states. So these states are believed that they will be more resilient to local noise sources because they're going to encode information in a way that it's redundantly stored across the material. So a local perturbation to my source, like a cosmic ray coming in, won't necessarily erase all of the information. There'll be a way to recover it. Now, there's a particular type of particle called a Majorana fermion that's actually known to be its own antiparticle. This formalizes the concept that we can actually create topological states by creating these types of Majorana fermion particles. If we are then able to braid together the Majorana fermions, we can start to transform their state. And you can see an example of braiding over here. What I mean is, depending on the order in which you actually rotate the particles around each other, you'll get a different topology. That topology is how the information is encoded, and so my ability to create these particles and manipulate them serves as the basis for what's known as topological quantum computation. Now, there's a lot of good hints about where these Majorana fermions could be created. One example is in the use of superconducting quasiparticles that come in the form of Majorana modes. We are, within the QSC, attempting to discover these Majorana modes within some novel quantum materials where they've not yet been found, and use that as the basis for trying to create these topological qubits, which would then go into the development of topological quantum computers. You'll hear more about this, I believe, in our next talk. Professor Michael Manfred will talk about the emergence of non-abelian anyons. But what I want to emphasize are the really cool pictures. So you'll see here an example of some of the things being created at Purdue University for the development of topological quantum information. One of these, this particular type of, well, it was called an anti-dot device, but it took me a little while to realize an anti-dot is just a hole. But this is basically, these 4 holes now become the places where we can store Majorana fermions, or at least the Majorana modes, that can be used as the basis for creating topological qubits. Similarly, we can start to interface those types of superconducting and topological insulating materials with conventional quantum computing devices. That's a strange phrase to say, conventional quantum computing devices, but we're at that point in our development of the technology where that becomes a standard by which we can compare things. And we can look at their interactions and how they can be used to, in fact, influence each other. We can also look at some somewhat exotic materials like quantum spin liquids. And you'll see up here at the top right an example of ruthenium trichloride. And this is a material that has been looked at many places, but at Oak Ridge National Laboratory, we've actually started to fabricate this into a type of design that may enable us to harness entanglement that is inherent into that material itself. So basically, the electrons in the ground state of that material exhibit entanglement that could serve as the basis for topological quantum computing. These are new materials in this space. These are new endeavors, new discoveries that we're creating within QSC in order to advance the idea that we can be more resilient towards noise than conventional technologies. We're also taking advantage of things like the spallation neutron source. This is the brightest source of neutrons in the world. It's recently been used for a very remarkable demonstration of witnessing quantum entanglement in these spin liquid samples. And what I'm trying to say here is that by this measurement, they were able to confirm, to witness, that entanglement actually existed in this sample of a quantum magnet. It means that if I were holding that material in my hand, I'm effectively holding entanglement, right? It's intrinsic to the material itself. It's part of that material's existence. Now, admittedly, it's under very, very cold temperatures and extremely high magnetic fields, so you probably aren't going to hold on to it too long. But it is an example of what's so remarkable about pursuing these types of discoveries is that we can start to see these technologies in a new way. Then finally, bringing it all full circle again, we're using quantum simulation as a way to understand those materials. So our conventional supercomputers are going to have a hard time with anything that's intrinsically entangled. So using quantum computers to provide feedback on what are the material properties, how can we validate those properties through quantum simulation is an important part of what we're doing. So let me just summarize real quickly. We've focused on the demonstration of these controlled interactions between topological quantum states. For this, we're creating new quantum materials. We're creating these states to try to validate them, and then ultimately to create new types of topological qubits. In quantum simulation, we're looking at the development of methods to create new predictive simulators that can be used from quantum algorithms. This is going to give us insight into the development of quantum materials as well as many other application areas. And then finally, in the area of quantum sensing, we're creating these new instruments that can be used to characterize materials, but also look for low mass dark matter. And that's not something I've had time to go into, but we can certainly talk about that more as we go forward. Collectively, this is the QSC at a technical level. This represents the type of work that we're doing and what our goals are for the next several years. Now, the other piece that we have to focus on is how do we get these ideas out of QSC and into the broader community? And one of those is technology transfer, and I've talked about our 3 partners that are critical to this. In all these cases, we're developing these new technologies in-house. We're going through the process of transferring those back to industry in order to support this broader QIS ecosystem. So again, focusing on the training and understanding of these concepts within places like the summer school is our platform for making sure this happens. And then beyond our own scientific agenda, the development of this workforce in the broader context is an essential mission for the QSC. The summer school, the Quantum Information Science Virtual Career Fair that's coming up in September, multiple workshops that we're having, as well as the internship and postdoc programs that we support are key ways for us to ensure that you are getting the opportunities that you need to move forward. Okay, so last slide, promise. QSC is the home for 3 critical topics. It's a unique resource within the United States and, frankly, I think around the world. 1, the development of topological quantum information. And this includes the development of the materials and the understanding of the devices that we would need to make that into a computational platform. 2, scientific quantum computing, which is harnessing those computing platforms for scientific discovery. And then 3, the development of scientific instrumentation for QIS, which includes not just our cryogenic control systems, but many other types of sensing modalities that I haven't had time to cover today. I know you'll hear more about all of these topics during the remaining lectures of the school, but I'd be happy to take any questions that you have at the moment. In the meantime, thank you very much for the opportunity, and thanks again to our organizers for putting on such a great event. My name's... Is it on? Oh, okay.
Hello? Okay. Thank you so much for the wonderful and inspiring talk. I think we have maybe 1 or 2 minutes if there's any questions. Otherwise, yeah.
I'll take an easy one.
Yes,
Oh,
please. Here.
Professor Kais, you certainly don't have an easy one.
You talked about simulating a quantum circuit on the frontier. What was the maximum number of qubits you can still simulate with that machine?
That's a great question. So on Frontier, I think the most that we've simulated up to so far is 26 qubits, which is honestly relatively modest. Based on the memory requirements and that simulation method, I think 50 qubits is the max we could do. There are alternative methods that actually can scale to thousands of qubits, but they give up some of the quantum mechanics in the process. So there's a spectrum on this, but I'm thinking 50's the limit here. Thanks, that was an easy one.
I guess with that, we'll move on. But first, I'd like to say my name's Colton Fruling. I'm a postdoc here at University of Purdue. I work in Professor Poltoseva and Professor Schleiv's group, and I'll be the moderator for this session. And maybe I might need some help getting the slides for our next speaker ready, if someone would help me with that. I think they should be. Slides, which here's a couple slide presentations. Make sure he knows.
Sure. I'm this guy, yeah.
That's it.
But go to presentation. Oh,
Say it.
yeah. Can we
Yeah,
get rid of that thing?
Okay,
How do I advance? Oh, yeah.
great. And with that, I think we'll get started. It's my great pleasure to introduce Professor Michael Manfra, who is currently the Bill and D. O'Brien Distinguished Professor of Physics and Astronomy, Professor of Electrical and Computer Engineering, and Professor of Mechanical Engineering at Purdue University. Manfra is also the Scientific Director of Microsoft Quantum Lab, West Lafayette, part of Microsoft's effort to build topological quantum computer. He worked 10 years in the Semiconductor Physics Department of Bell Laboratories in Murray Hill, New Jersey. Professor Manfra obtained his PhD from Boston University in 1999 and his AB degree from Harvard University in 1992. His current research interests include molecular beam epitaxy, of ultra-high purity semiconductors, topological phases of matter, electron transport at low temperatures, and high magnetic fields of mesoscopic structures and quantum computing. And with that, thank you and welcome.
Thank you very much. It's great to be here and the opportunity to speak. And I think it's apt that I'm following up on some of the topics that Travis was mentioning, specifically the emergence of topological phases in condensed matter system and the anyons that can be found in these systems that may or may not, but we're working very hard to have utility for computational purposes. So my goal here is pretty modest. I'd like to, for students and people new to the field, is to try to convey what an anion is in real life, not just cartoon form, but where we might find them and how we might measure them. And the work of my group and others over the last few years has made strides in this direction. And so I'm here to tell you that anions are real, they have measurable properties, and we have model systems in which their fundamental properties can be explored. The other point I'd like to make that is tied to the Quantum Science Center and this rather large network of collaborators and experts coming from different fields is that in order to make the progress I'm going to show you, it's not one thing. It had to be developments in materials, device technology, and measurement, and we were fortunate enough to be able to do some of this here at Purdue, but it wasn't one thing, and they all have to work together to make real advances. So I hope that point comes across. Okay, before I really get into it, I want to acknowledge the people who do the work. The leader of the group is Dr. James Nakamura, my former graduate student, now is essentially a staff scientist, my collaborator. Jimmy is one of the driving forces behind the work I'll be describing to you. But of course, he works in a team too. There's materials and device fab and modeling and a lot of things that have to happen. So Dr. Jeff Gardner, Saeed Falahi, and Shuang Liang is a graduate student, and these people really made it happen with Jimmy in the lead. So I'll tell that story. Okay, so you'll hear a lot about, in different contexts, topology and anions, and I hope I can try to give you sort of a simple, down-to-earth explanation of what we're talking about. And so we all know, we learn in our freshman physics courses, that elementary particles come in two types, either fermions or bosons. Fermions, of course, examples include the electron, muons, quarks. They obey the Pauli exclusion principle. What does that mean? No two fermions can exist in the same quantum state. They're not very friendly actors. So this comes down to a symmetry property of the underlying wave function. If I have fermions and I exchange or permute their locations, the wave function is multiplied by a phase factor of -1. Now, bosons, examples being integral spin particles, photons, Anderson-Higgs boson gravitons, those particles have integral spin and obey bosonic statistics. And when you permute the position of two particles, at least in 3D and above, the wave function is multiplied by a phase factor of 1. You get the same wave function back. And in 3D, for a long time, that's all there was. That's what we know particles, it's tied to the spin statistics theorem, and when you have a certain kind of angular momentum, you get fermions. With other angular momentum, you get bosons. And this dramatically impacts the behavior of these different types of particles in aggregate. When you bring them together, as I said, fermions obey the exclusion principle, and using basically the Pauli exclusion principle and a little bit of symmetry, you can explain a lot of 20th century solid state physics, band filling, Fermi levels, and you go a long way. Of course, bosons can flock together, and some of the more dramatic examples include superfluidity and Bose-Einstein condensation. These are very dramatic, observable effects associated with the underlying statistics. Now, in the the late 70s, but early 80s, it was recognized theoretically that while this description is true in 3 dimensions, in 2-dimensional systems, and actually some 1-dimensional systems, we can have objects that actually interpolate between these 2 extremes. They're called anyons, and this comes about, it's a play on words, they can have any statistics. Frank Wilczek coined the term, and what he was looking at is actually relative angular momentum in 2 dimensions, and found that it can take, in these 2-dimensional systems, can take on fractional values. And as a result of that, actually the statistics can take on fractional values, and he dubbed these anyons. Now, of course, these are very unusual particles or composites in that they can carry, as we'll get to in a moment, fractional charge, and they can have fractional braiding statistics. In lower dimensional systems, it's more appropriate to talk about braiding, the braid group rather than permutation group. And when these objects undergo rotations around one another or braid, the wave function is not the same modulo factor of 1 or -1. It actually picks up a non-trivial phase factor. And the archetype example of this turns out to be the fractional quantum Hall effect in 2-dimensional electron gases. And that's what the subject of what I'll tell you about today. So quasi-particles in the fractional quantum Hall state, the primary one being the Laughlin state at filling factor 1/3, I'll tell you what that means in a minute, carries the fundamental objects in the system carry a fraction of the electronic charge, and it's quantized. This is a weird concept. You had your basic units, the fundamental particles, of course, are electrons. That didn't go away, but the objects that matter in this 2D world, in the energy regimes that we can explore, are objects with a fraction of the electron's charge. And it's a sharp quantum number. Concomitantly, they're not fermions or bosons, they have fractional statistics. And in the particular case of 1/3 that I'll discuss, that fractional or statistical angle is 2 pi over 3. Now, in this case, you'll hear, I'll talk about different kinds of anyons. These are abelian anyons. You'll also know examples of non-abelian anyons. They're just different, they adhere to different representations of the braid group, but they're all anyons in which fractionalization takes place. And this fractionalization of statistics and charge is one of the most interesting phenomena that we can explore in condensed matter physics. It may also have utility for computing, but the main focus of this talk is to look at some of the physics. Okay, so you have to bear with me. It'll be a little bit of an introduction, just except for the moment that I tell you that this fractional quantum Hall effect exists, and its excitations have fractional charge and statistics. So the simplest experiment you can do, it's quite simple. You take a piece of semiconductor, a heterostructure, gallium arsenide, aluminum gallium arsenide, which has a 2-dimensional electron gas. You can also use 2D materials, anything that supports electronic system that is essentially 2-dimensional. And you do a very simple experiment. You cool the sample down to low temperatures. Does this have a pointer, or maybe I should use the other thing? see if I can do this with two hands. You have a slab of this material, there's a 2-dig in it, you force a current through it. Now, we've cooled it down into Dilfridge, so about 10 millikelvin, and you just monitor the voltage that develops along the length of this sample, that's called the longitudinal voltage, and you measure the voltage that develops across the sample. We're going to apply a perpendicular magnetic field, and because even classical physics, there's a Lorentz force, a Hall voltage develops perpendicular to the direction of current flow. And classically, this is, nothing much should happen. The Hall coefficient or the transverse resistance should be linear in magnetic field. If Drude were doing this back at around 1900, it just should be linear in magnetic field and inversely proportional to the density of the electrons in your sample. Concurrently, the longitudinal resistance should have no magnetic field dependence. It should be a boring old straight line. In modern samples at very low temperature, of course, that's not actually what happens. You see something more akin to the data I'm showing you here on the right. And this is a modern, extremely high quality sample that we measured recently here at Purdue, grew and measured. And in the Hall trace, the Hall voltage, the Hall resistance, there is a linear term, of course, there is linearity, but that's interrupted by these very flat regions, extended flat regions, where the Hall conductance doesn't change. It's quantized to extremely high accuracy in units of h/2e. Okay, so instead of having just a straight line and a horizontal line, what you really get in the longitudinal resistance is this spiky behavior. A lot of the time, the resistance is 0 along the sample, and then there's these big resistance spikes. When the resistance is 0, that's when these very flat plateaus occur in the Hall resistance. And this is the signature of the quantum, that's the phenomenology of the quantum Hall effect. Now you see I've labeled some numbers here, this factor we call nu. Nu is something that's called the filling factor. Its value is basically the density of electrons in the sample to the number of flux quanta in the sample. What measures is how many electrons you have and how many states do you have available. Now you all know your basic quantum mechanics class, what happens to a non-interacting electron when you put in a magnetic field. The continuous spectrum breaks into a discrete spectrum of Landau levels, the single particle physics. And as you go to higher field, the degeneracy of those states, Landau levels, increases. And you can drop more and more of your electrons into lower Landau levels. So the integer quantum Hall effect, where this filling factor is 1, 2, is explained by very simple single particle physics. It's the quantization of Landau levels, and when the Fermi level moves through a gap between these Landau levels, that's when you see these features in the magnetotransport. But if you look closely, there's a lot of other filling factors, non-integer filling factors, where you see seemingly the same phenomenology, especially in the regime that's, say, in this sample, above 6 Tesla. You've completely filled the lowest Landau level at nu equals 1. 1 electron per state in the Landau level. Here, at higher field, you have more states available than you do electrons in your sample. And you may have heard in your courses and research about flat bands, how important flat bands is. Well, this is the prime example of a flat band. All the electrons have the same kinetic energy state. They're all in the lowest Landau level. There is no kinetic energy in the problem. The whole dynamics is determined by interactions. So it's as if you took kinetic energy out of the problem, and the electrons now need to arrange themselves in order to minimize the Coulomb potential. And surprisingly, the states that are formed in this regime give you phenomenology of quantization, just like the integer quantum Hall effect. Well, if the integer quantum Hall effect is electrons in Landau levels, it turns out here that the analog are these fractionally charged anions with fractional statistics. Okay, and that's the subject matter I'm going to tell you about. Now, oops, gotta get the right one here. When the fractional, I want to give you some perspective for time. The fractional quantum Hall effect was first discovered by Sui and Stormer and Gossard in 1982. Robert Laughlin, within a year, had, through just brilliant guessing, had posited what the underlying wave function should be for this state. And part of his analysis led to the conclusion that there's a ground state that's separated by a gap to the lowest lying excitations, and these quasi-particles, language that's brought over, say, from Fermi liquid theory, these quasi-particles are very different. They carry a fraction of a charge. There's electrons in the system, but the fundamental objects behave as if they're charge E/3. Now, that statement was made in 1983, and if you ask Bob Laughlin, he'd say, well, that's obvious by quantization, so it exists. But how do you actually measure a fraction of a charge? That took some serious development in quantum shot noise technology and experiments. And so the first demonstration of fractional charge by quantum shot noise occurred in the late 90s. Actually, my former colleague from Bell Labs, Rafi DiPicciotto, did this experiment when he was still a student at the Weizmann Institute. So look at the time interval. That's about 15 years or so. Well, 1 year after Laughlin's first writing down the wave function and saying the quasi-particles have fractional charge, others, including Bert Halperin, Frank Wilczek, realized that these quasi-particles also have fractional statistics. And I can't go into too much detail, but that statistical angle for these Laughlin states is related to the fractional charge. And so if I'm looking at a 1/3 state, the fractional statistical angle would be 2 pi over 3. Now again, look at the dates. By 1984, as far as the theorists are concerned, it's a done deal. I'm giving you a talk in 2023 about this topic, so it gives you a sense of the time interval and the efforts of a lot of people, not just my group, but many people over the years to actually have measures of these quantities. So you can say they're real, not a mathematical construction. So what do I mean? Again, this is a cartoon, but for the students, what do I mean by it has fractional braiding statistics? I will represent a quasi-particle by these little vortices, these little cartoon vortices. And imagine I take one of them and rotate it around the other. Now this isn't an exchange, this is a braid, so you might consider it 2 exchanges. But I come back to the same state. The quasi-particle that was here originally is now back in the same position. And you'd say, well, nothing can happen. There's no observable associated with that because it looks exactly the same. In fact, for these anyons, that's not the case. There are measurable consequences to this development of a statistical phase. Okay, and so just keep in mind that nu equals 1/3, the anionic phase should be 2 pi over 3. Now the story becomes, how do you get there? How do you measure this? And that's what I'll tell you about now. Okay, now a point of clarification that there's lots of, topology enters condensed matter physics in many different ways. And there's, topological classifications of band structure there are symmetry-protected quasi-topological phases. There's a whole variety of things. When I'm discussing topological states, for me, in my own language, it means something specific. That there's a strongly interacting ground state separated by a gap to any excitations, and those excitations are anyons of one type or another, be it abelian or non-abelian. They're all the same thing, or just different flavors of anyons. Now, the ones I'm going to focus on right now are primarily abelian anyons, but of course, in the fractional quantum Hall effect was the first theoretical proposal for non-abelian anyons in condensed matter as well. And there's these special states where at half filling, at 5 halves, that's supposed to support Ising anyons, and that is the simplest version of non-abelian anyons and are associated with the Majorana modes that Travis spoke to earlier. Of course, there's other varieties of anions too, higher order ones, and they may be associated with this 12-fifth state. So, what I want to give you is a sense that this platform of 2D gas in the level of purity and quality you can make it now is a really nice platform for trying to work out some of the basic physics of these topological phases that support anions, both abelian and non-abelian, and different varieties of non-abelianness. Okay? So the precise quantization at half filling is different. It's not described by the Laughlin wave function. The theory of that was developed later on by Moore and Reed, Nyack and Wilczek, Reed and Green, and involves some fairly fancy physics, but is describing phenomenologically the same phenomenon. Okay, gotta push the right button. So again, to give you a little bit of the background and how something goes from sort of playing around toy model to reality, the first discussion in condensed matter, was Frank Wilczek in a paper in 1982, where he was considering a composite object, a charged particle with vortices in 2+1 dimensions. So there's a charged particle, and he's attached these vortices to that particle, and then considers their quantum mechanics, basically, and working out angular momentum and things of that. And in the process, he realizes that through the spin statistics relationship, that these will be have anionic statistics. There's a toy model in 2D that will support anions. And at the time, it was very abstract, right? There's this funny thing, there's a charge, and he just by hand attaches vortices and then looks at them as he moves them around. And he says a funny thing. Although practical applications of these phenomena seem remote, they have considerable methodological interest and shed light on the fundamental spin statistics relationship. Okay, that's 1982. And then shortly thereafter, Bert Halperin notices that in the fractional quantum Hall effect, these states described by Laughlin-like wave functions actually are a prime example for anions in a two-dimensional system. The appearance of fractional statistics presented in this context is strongly reminiscent of the fractional statistics introduced by Wilczek to describe charged particles tied to magnetic flux tubes in 2 dimensions. The key insight, the key connection is that little toy model Frank came up with actually describes what the basic objects are in the fractional quantum Hall regime. Those charged particles with vortices attached are the quasi-particles. And so there's a real example in nature, in a gallium arsenide, aluminum gallium arsenide hydrostructure, where the particles are exactly mapped to reasonable approximation onto that model. Okay? And Frank Wilczek and Orovas also, a year later, showed that they had fractional statistics using a methodology that you modern students would be more familiar with. You use the adiabatic theorem, essentially calculating a Berry phase. And that would be something, this calculation would be pretty straightforward for modern students of condensed matter physics. At the time, of course, this was all new. All right. So what do we really mean when we claim to measure anions? Well, here's the Laughlin wave function. I won't go into great detail, it's just, but the defining feature of this is the way it works is it puts zeros right at the positions of the particles, the electrons. That's how it minimizes the Coulomb energy and is identified as the ground state. It does exactly what Wilczek was talking about. It puts vortices right at the position of the particle. Okay, this Jastrow factor, this is the wave function at 1/3. If I create a quasi-particle, one quasi-particle, the wave function looks like this. There's this extra factor, zero, Z0 here is the position at which we're creating the defect, the excitation. And so this essentially, in the Laughlin state, the charge and the vortices are tied together. The quasi-particle removes the charge from that vortex region and creates this fractionally charged particle. okay? So it's a really good mapping of some toy model ideas onto reality. Well, this is still theory, but we'll show that it actually works. Okay, so I told you shot noise was used to first determine the fractional charge, but the prediction of fractional statistics was made at the same time, and it hadn't been done. And so the question is, well, what measurement can I do that's sensitive to this phase? And what we use is the electronic analog of the Fabry-Perot interferometer from optics, okay? And this is the device. There's lots of details, but I'll try to just give you a flavor right now. The blue region is the two-dead gas. There are source and drain contacts. That's where current comes in and goes out. And these yellow lines are surface gates. The surface gates deplete the electrons under that region of the gate and define the interference chamber here and the electrical analog of beam splitters, quantum point contacts here and here. So in the quantum Hall regime, current flows along edge states. It circulates in these chiral modes. So if I operate this device, the surface gates have defined my region of interference and my beam splitters. So the particles come in, they're mostly transmitted, but some are backscattered at the first QPC, going to the other edge. Most of the current continues on through the interferometer and also goes around the loop, and there's another small scattering amplitude at the second QPC. And what we measure is the modulation in that current that flows through this system as a function of parameters, be it B field, voltage, temperature, okay? And the interference path is here. This beam recombines with the beam that was first scattered at the first QPC, and the modulation in the conductance is sensitive to the relative phase, and that's how we're gonna measure. So the surface gates define the electron interference path, quantum point contacts act as the beam splitter. So if you're familiar with optical systems, this is what we do in the quantum Hall regime with charged particles. The backscattered, or actually the current, is proportional to a few terms. These are the square of the transmission elements at the two QPCs, but what's important is that there's sort of this cross term, proportional to cosine theta. Now theta there is not the statistical angle, it's actually the interference angle. But we can operate this device in the following way. If I had just boring old electrons and I had two paths going around here, there's flux through this region, so the trivial phase would be the Aronoff-Bohm phase. Okay, so the theta would be proportional to the area of the device, the magnetic field, that's flux, divided, and it'll be periodic in the magnetic flux quantum. That's just H over E. So we can measure interference by measuring the electrical conductance across the device. We operate the device by changing area. These two T gates we can squeeze or pull apart the electrons so we can make the chamber smaller or bigger, or we can vary magnetic field. And if we plotted the conductance as in a multidimensional color plot, we'd expect to see the following. These lines, red and blue, represent lines of constant phase. And you see this sort of barbershop pole development as a function of flux and plunger gate. And those lines of constant phase is how the phase develops in this space and is indicative of AB or Aronoff-Bohm oscillations, and that tells us a lot about the system. Now, if we actually go to the fractional regime where we have these anyons and we have a localized anion in the system and anyons circulating around, things become more interesting. The AB phase is scaled by the effective charge. So the effective AB periodicity will change by, say, a factor of 3 from bare electrons. Most importantly, the phase is also sensitive to the number of localized quasi-particles in the interior of the device and the statistical phase angle. So how does that give us sensitivity? Well, imagine that we change the number of localized particles, or quasi-particles. Those are integral. It can change by 1, -1. what would happen to our nice little A-B pattern? Well, there'd be a jump, a phase slip. It looked like a glitch in our system. Okay, it may look like noise, but there should be a demonstrable impact of the addition or removal of quasi-particles from the interior. All right, so that's going to be what we look for. The theory of all this was worked out in the late 90s and, by Shimon, Kivelson, Sandy Wen, and further elaborated on by Halperin and collaborators much later. These are sort of the two standards to go to understand the operation of these devices. Okay? Now, again, why the heck? It sounds easy, right? Why am I talking about this 40 years later? There must be something hard. And the hard part is that's an abstract description. We're dealing with mesoscopic devices that have real mesoscopic physics involved. Specifically, small objects, my interferometer is really a quantum dot, and it has a finite charging energy. And these circulating edge states going around the perimeter have a velocity, and they can decohere or reconstruct if that velocity is too low. So these factors combine to make it extremely difficult. Many very good groups have tried and made innovations along the way, but I hope is an important point for the students is it really took an innovation in heterostructure and device design to make this visible. So what we did is these charging effects I talked about can be mitigated by, instead of having one 2D gas, we have three together. This acts like a big parallel plate capacitor. Basically, it reduces the charging energy of the system because these two layers up and above the primary quantum well can screen the long-range Coulomb interactions that give rise to the charging energy. So we have a mess. We have three quantum wells, each with their own two-dimensional electron gas, and we really care about the one in the middle, but 25 nanometers away, there are high-density two DEGs on either side that make this nice, quench the charging energy and also make the edge profile sharper. But how are we going to measure anything? So we have to make a fancy, complicated device to do that, but you can, and we borrowed techniques that have been developed over the years to do this. So if we hadn't made this innovation in the materials, we wouldn't have the data. And so part of the Quantum Science Center is to bring together, for topological materials, the developments of material synthesis, device fabrication and design, measurement and theory. So this is an example of how it can happen, hopefully not in 40 years, but 5 years with all the smart people from the Quantum Science Center working together. All right, so how does this thing work? We have a subway system of gates, but our mesoscopic structure is just this little guy up here. These gates serve a purpose to cut off contacts. So we bias these gates. We can cut off the screening wells from above, the screening wells from below. We can look at transport just through the primary one, but these big sheets of charge, essentially metals, are still able to screen. They exist everywhere inside under this tiny little mesoscopic device. So we eliminate the parallel conduction through lithography and we adapted a technique that was developed by some of my colleagues from Bell Labs a long time ago for a different purpose, but it works here too. All right, so I can't resist. Everyone likes to make these fancy graphics now. So this is what it looks like, where the device is thin, there's gates below, there's gates above, different gates have different purposes. Now, if we zoom in, we'd have this little circulating whirlpool with some vortices in it. Reality's a little different. So this device has to sit at the bottom of a dilution refrigerator to get down to 10 millikelvin, and the sample itself is not quite as pretty. Here it is stuck to the board with the wires coming out, but you can see the actual sample itself. In the interior, that is something that looks, we hope, like the cartoon I showed you. All right. So what happened? We started out in 2018. In 2019, we were able to show that you can do AB oscillations in the fractional quantum Hall regime for the first time through this innovation in device heterostructure and device design. We got AB oscillations, but we didn't see the phase slips we wanted to. And that's because our design was going the right way, but not completely. Actually, we overcooked some stuff. And the theorists, Adi Stern and Bert Rosenauer, came back and told us, you shouldn't see it because of certain things we did. So we said, okay, we'll go back and change our device based on their suggestions. We modified the device, and then in 2020, on this modified device, we actually did see the AB oscillations, this nice barbershop hole, but then you see these discrete jumps. And those jumps are not noise. I can show you why they're not noise. And they correspond to actual phase slips associated with the introduction or removal of quasi-particles. And when you do the analysis, it comes out that these phase slips actually yield an anionic phase of 2 pi over 3 within our experimental limits. And so, to the best of our knowledge, this was the first direct observation of braiding statistics for anions. Okay, that continued in 2022, and this is important for people trying to make the connection. I want to take something from a concept to a device, and then have a device that's not a one-off, but I actually understand and control the parameters, so I could have something. Based on what we learned there, we modified the device characteristics again in a way, controllable way, and we are actually to show what impacts the formation of these quasi-particles and extend the region over which we observe the effect. And we see, it's a lot of detail, but there are other features that are tied to the existence of anions in a compressible and incompressible regime. That's a lot of detail. But if you look at the zoom in here, these phase slips are clear. That's not a glitch. That's data, and we see that. And then we actually see a transition from what's called the incompressible state to the compressible state, where the behavior changes abruptly, and that's also anticipated by theory. Most recently, we've now moved beyond 1/3. It was great we could show it at 1/3. It was the easiest example. But does it have general utility? And it can be extended to other fractions. And now we have recently done this at 2/5, where the charge and the phase angle are not the same. The charge, you're at a filling factor 2/5. The charge is E over 5. The statistical angle is -4 pi over 5. So things are complicated. It's much more difficult data analysis, and there's 2 edge modes. But we have extended this technique. This is on the archive and is under review at PRX right now. So the reaction of the research community was really positive, more than I was expecting. And in some ways, it's not some statement about the work we did. It's just there's been a huge community of theorists and experimentalists who've been interested in this problem for a really long time. Lots of people contributed to it, and to finally have evidence for it that was relatively unambiguous was pretty exciting. For me, the fact that we can go beyond and apply it to other states, and now it's being used for graphene structures and other things, is really the rewarding part. Can we go further and probe not just abelian anions, but non-abelian anions? Okay? I don't know how I'm doing on time. When am I supposed to wrap up?
10:10.
Oh, I'm already over? Okay.
So interesting, I couldn't.
No, that's okay, that's okay. I was going to show you a little bit more details, but for the Quantum Science Center people, I do want to emphasize how we got there. Materials, device fabrication, measurement theory, right? There's not one of them. All of them are needed, and they have to work in concert. So, there's complicated growth, there's fab device development, and then the measurement capability, low temperature measurement capabilities. And luckily, I was able to do this all at Purdue, but hopefully it'll happen faster and more often within the context of the Quantum Science Center. Now, I was lucky, I had a lot of support from Purdue. I also have a lot of support from Microsoft Quantum. So, there's been a lot of things that work to our advantage. And of course, when I came to Purdue, one of the primary reasons, or not, one of the reasons was the Burke Nanotech Center. So a lot of this work relies on the facilities at the Burke Center. And so all working together is what allowed the breakthrough, okay? So I'm going to skip through these because I've already sort of explained it. Those are details. I already went too far. So I'm just trying to get to the summary. So in summary, through a combination of materials development, device fabrication, and measurement, we've been able to show direct observation of anionic braiding statistics. Novel header structures and the device design facilitates new observations, extensions to probe other properties and to other regimes of interest. And what I'm really happy about is we've been able to push this beyond the primary one-third Laughlin state into hierarchical states, measure the charge, and the statistical angle in a very complicated system that bodes well for probing even more complex systems containing non-abelian anions. So with that, I'll conclude. Thanks.
Is it on? Yeah, thank you so much for the interesting talk. It was fascinating. Are there any questions from the audience? Yeah. Oh, okay.
Hello. Thank you for the great talk. So, as you mentioned, I think Wilczek coined anion. As a non-expert, I noticed this is very much like fractionon. I'm curious, this is sort of a theoretical question, I'm curious if there are irrational possibilities for anions. It would be sort of interesting because you'd be able to do multiple braidings and never get back to a +1 or -1 phase. So I was just curious if there's any work on that.
Well, I'm not quite sure of the terminology. You're referring, people coin new terms all the time. I'm an old guy, I can't keep up. But the property, the final property that you're interested in is exactly the property of non-abelian anions. So maybe you're referring to something in a particular context that I'm unaware of, but if it's non-abelian, it doesn't actually just pick up a phase factor, it's actually a rotation within a degenerate manifold. The state, there's a degenerate manifold of states, a nearly degenerate manifold of states, and the operation of braiding makes a rotation within that vector space. And that you get a new state that's still degenerate, and that's the basis of topological protection of quantum information. So there may be all sorts of different flavors of this, but what you described is the principle underlying, or the interest in non-abelian anions.
Thank you.
But you can point me in the direction, I'll take a look at the paper or something, but I just don't know the term right now.
Let's thank our speaker one more time, and then we'll have a short break and reconvene about, I think the schedule says 10:25, so.
Fives. 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 Fives.
right, I think we're probably getting ready to start. If everyone find their seats. It's my great pleasure to introduce Suzanne Yellen, serving as the Vice Director of the Max Planck and Harvard Research Center of Quantum Optics. Professor Suzanne Yellen's group studies theoretical quantum optics and quantum information science. Their group research directions include quantum control of ultra-cold, quantum control of ultra-cold polar molecules, investigation of novel coherence-based optical elements, single photon nonlinear optics using dipolar molecules and dipolar systems, coherent metamaterials and negative refractivity, coherent control of condensed matter systems, as well as superradiance. And with that, I'd like to welcome our next speaker.
Hello, good morning. It is my pleasure to be here. It's a great room, but it doesn't have a clock, so I brought my own. Okay, so I'm going to talk about analog quantum machine learning. This is by now already a huge field. And I should also say that somehow the order of this session is a little bit backwards, because the speaker after me will talk about classical machine learning for quantum, and the speaker after me will talk about the particular experimental setup that is our main kind of idea of what we are using. So in particular, we are thinking about the analog quantum machine learning using present-day hardware. And I should say that the lowest line of my text is cut off. So that might happen once in a while, that there's just something. Here you just don't see that we are at Purdue, and today is April 27th. So the obvious question is, people are doing all this quantum computation and people doing all this machine learning. Can we put this together? In particular, the question is, can quantum computer, as compared to a classical computer, speed up or enhance machine learning algorithms at some point? And just to give you the answer to that right away, it's a big, we don't know. And there's a lot of things that are being done heuristically and done on really small scale, but in general, there's for some algorithms you can show, yeah, in principle there's enhancement or speed up, but that remains to be seen, as it has to be mostly for quantum computer for that matter. Okay. So, in particular, I will be concentrating on neuromorphic computing. And neuromorphic computing you see here on the right side. Our model sits in each of our heads. So here is a model of how the neurons in the brain hang together. So they have these nodes, and then there are the axons, which are the combinations between the two nodes. And as we all well know, our very own analog computer in our brain is very resilient to noise and disorder. It works analog, and it's evolved to excel at learning tasks and a certain type of tasks. So how can we translate that into a physical system? So here I still have this slide that's already somewhat old. It relates to NIST technologies. By now, I think that a lot, in particular of the programmable quantum simulators, are already somewhat beyond what we understand as NISQ, noisy intermediate scale quantum. And this consists of a few hundred qubits, which is actually right now being upgraded to a few thousand. It's decoherence limited, it's scalable analog computation, and the experiments are moving towards full control. And you can, in principle, already see even here that there is a certain similarity of this kind of architecture of these neurons that we are looking at, and for example, atoms in a Rydberg simulator, which we will see in Misha's talks later. So in particular, if we are looking at quantum algorithms that are inspired by the brain, the idea is we want to reveal the analog computational power of near-term devices. We want to have it scalable, and we potentially also want to reveal the physics advantage, the physics behind possible quantum advantage. So that's the task that we are going for in this talk today. So for that, I would like to start with a little bit of a definition slide. So you all have heard neural networks. So neuromorphic computing refers, the term neuromorphic computing refers just to brain-like. And this can be done in principle definitely classical, which people do since quite a while, and also quantum mechanical. Then there is this term recurrent neural networks. Recurrent neural networks means there are cyclic connections in your AI system. Most AI that we know and love, like for example AlphaGo and the typical kind of speech and image recognition, is purely feed-forward. Whereas the recurrent has cyclic connection and is therefore necessarily a little bit harder to kind of sequentially describe, but is also more amenable to any kind of general 2D or amorphous structures. And then there's reservoir computer, and reservoir computer is a special case of recurrent neural network with fixed connections, and I will tell you that in a second. So here is the general idea of a recurrent neural network. So we are starting we are starting with these neurons, which are just here classical spins. So this is just a classical description. The spins have connections between them, which are in principle specialized for spin N and spin M, is called J and M. And then we designated a few of these spins as input spins. And another few of the spins, then there is some evolution, and another few of the spins are designated as output spins, and these output spins can then be somehow be modeled into a solution which is written in this vector y. So in general, these recurrent neural networks, the idea is that these J and M are trainable, and that this calculation from the output to the solution, W out, is trainable. But training these connections in general, even classically, is very expensive. So people came up with the idea with the reservoir computer, where they say there are fixed connections where we, between any pair of neurons or spins, we either have a connection, then it's J, or we don't have a connection, then it's 0. And we cannot touch this anymore afterwards. This is also for the first kind of, I would say, generation of idea of reservoir computing is exactly the quantum model, and I will get to that in a second. But before I go to that, I would like to show you how you typically train a classical reservoir computer. So in particular, the center part of this is the so-called update rule. So the update rule means every spin gets updated during the training, depending on A, spin-spin interaction, and B, the environment. So what you just saw there in the right corner was you put the input, you let it evolve for some time, and then you get an output. How does this update rule go mathematically? So we assume that every spin, for example, spin N, has a local environment, which could be, for example, we are all physicists, right, can be described as a magnetic field, which is given by these interactions, which are the synaptic weights in the brain. and biases, which are typically seen as the external stimuli often. And then the rule is very simple, and here this gets cut off, and this is of course bad. So if the rule is, if this environment is larger than 0, then nothing happens to the spin, and what you can see here, if it's smaller than 0, then we flip the spin. Okay, and this is how this evolution, during the evolution time happens. That's all we need to know. And then at the end, one reads the output, and one, for the reservoir computer, one trains on the output only. So let me just say something about the training cycle, because we need that for the quantum as well. So the goal of the learning is to optimize a set of parameters, which, for example, could be all the connections and all the parameters that go into W out, in order to give the desired output. And the one part is this updating, which I just explained to you. And the other part is the optimization. So where you calculate a loss function, where the loss function typically is, for example, the overlap of the desired outcome with all of the training data sets. And find a new set of parameters. And the way how one does this is, for example, via gradient descent or a similar kind of forwarding, stepping mechanism. And then one resets the parameters, and one goes through the update again, etc. And you go through this as often as needed. By the way, this is, sorry, the whole talk is set such that I can stop at any time, so please do interrupt me with questions at any time. I need to make sure that okay. All right, so how can we quantize this? So here the first thing that we do is we need to reset the update rule such that it follows quantum mechanics. So what we see here is a Hamiltonian, and this Hamiltonian is the Hamiltonian of the full system. But if you look a little closer, is that you see again this Hn, which is the local magnetic field, which is the same as before. It consists of the connections and the external stimuli, which just goes with the depending on the state where the system is, which we usually describe as sigma z. In addition, however, we need something that flips our spins. Right? And our spins now, of course, are quantum spins. And this flipping the spin is done via a sigma x, not very surprisingly, and using some kind of driving field. And the update rule now is basically exactly the same as before. Namely, if the h is very big, the spin state doesn't change. If it's very small, it flips. And the way it flips is that we have, and very big and very small is now comparing these two parts of this Hamiltonian. The flipping is done via a pi pulse, where we just let it evolve for a time tau, such that omega times tau gives a pi pulse, and that kind of flips our spin. So what we have done now is we have exactly recreated the classical situation, right? So that's always the first step. Can we actually do as well as classical? So yeah, in principle, yes. So there's of course people who have kind of come up with this before, so we were not the first who had the idea of quantum reservoir computer. Here's a couple of references which are very, very far from comprehensive. And typical applications for quantum reservoir computer is entanglement detection, time series prediction, and memory. Because they are also, except for the entanglement detection, is typical quantum tasks. The other two are very typical kind of brain-like tasks. But the thing is that all of these earlier ideas require large-scale universal quantum computation, which we don't have and won't have for a while. And what I am going to show is how can we do that really using what we have right now and what we might have, let's say, within the next year or two. Okay, so here, that's the same training cycle that I showed you before, but please note that I added the word quantum here. So the update rule I just explained to you, so we let the system evolve, this time under quantum mechanics. Please do note that the optimization has to be still done classically if we don't have a perfect quantum computer. So we make a readout or measurement, and we do the optimization basically the same way how people have done that classically, and then we feed it back into the quantum computer. Here is the big question: why is that potentially better than what we can do before? Okay, so there are 3 easy aspects where we can imagine that we potentially get an advantage. The first one is that we have both interference and freedom of measurement basis, which, for example, can be used for error detection and correction. I'm not going into detail with that. These error correction schemes, they're worked out in our paper, which is also cited here on the bottom, which you can see. But it's basically the same type that has been proposed many times in other quantum computing schemes. The second is that we can go into an arbitrary measurement basis in this, and this is actually something which is very, very easy in this scheme, and I will show you briefly how that works. And obviously we can do efficient stochastic processes, because this is an intrinsically stochastic machine. So let me just briefly tell you about this measurement basis idea. So I showed you this update rule. This is just the same picture again that I showed you before, where I told you in particular that we need a pi pulse to switch the spin. But nobody tells us we have to stop with a pi pulse, right? We could do a pi over 2 pulse, or we can do a 3 pi over 4 pulse, or anything like that, right? And this allows us to enter a much larger set of states of the system. And this one doesn't show that this is useful. It just kind of shows that the expressibility of our system goes up immediately with that. Okay, so let's just keep this in mind. There are, in principle, ways how we can do better. So now I show you a couple of examples of, first I show you the system, and this is the one slide kind of system that Misha is going to talk afterwards for 40 minutes about, so if you don't understand something, don't despair. So what the Rydberg arrays are arrays of systems that can be in principle described as 2-level systems. A ground state and excited state, where the excited state is in the Rydberg. And if they are in the Rydberg states, they interact via the van der Waals interaction. And in particular, the interaction goes via the so-called Rydberg blockade. The Rydberg blockade idea is the following: if this radius here is pretty big, the van der Waals interaction is pretty weak, so we basically need the same energy to get from 0 excitation to 1 excitation as we need from 1 excitation to 2 excitation. However, if there is a very strong interaction between these 2 Rydberg states, this interaction, of course, adds to what we would have to excite, and at some point this is just out of range. So that means that we can actually, for up to a certain distance, only excite 1 atom in a certain radius. And that's basically the interaction scheme of this system. This can be all nicely implemented, and I'm not going to talk about that because we have Misha speaking about that. What I want you to look into is I want you to look into this Hamiltonian. And this Hamiltonian turns out to be basically pretty much exactly the kind of Hamiltonian that I showed you before. So here we have our synaptic rates, here we have the external biases, and here we have this kind of flipping availability. Okay, so what they have in their experiment is exactly the tools that we need in order to implement our idea of the quantum reservoir computer. Okay. There are a couple of example applications, and I'm not going into any of them. Quantum error detection, I talked briefly about. Multitasking, that's, for example, where we can learn, for example, an AND, a NOR, and then I think an AND and an OR and a NOR gate simultaneously for different pairs of qubits, and then afterwards test whether that works, and it does work. And finally, we also look at memory, and I'll show you one slide for how, for example, you can do this. So here the question is, we basically give 2 inputs which are done via detuning between 2 input states. 2 inputs into the input state of the system with a time difference which we call T delay. And then we read out and see whether the system can still recognize which of the 2 detunings was larger. That's it, okay? Please do note here, I think is also the right time to say that. Right now, up to this point, we haven't run this on a quantum computer yet, so it's all done via simulation. And we can simulate only a very small system because we have to go through a training cycle. I mean, the highest that we can go is somewhere on order 10, and depending on how long you are willing to wait with your calculation. But everything that I show you is done with a really, really, really small quantum computer. It turns out that we looked at that both in the non-blockade regime, which gives this red curve, and in the blockaded regime, which gives the blue curve. And you see that the outcome is actually pretty good. I mean, we get around 90% accuracy, even for our tiny quantum computer. Please do note that, of course, if you do the time delay much longer, of course, it goes down eventually. Okay, so this is a little bit of cheating. One can also go much longer if one goes into the so-called quantum scar regime, but I don't want to go into this here. So here we have done one a little bit bigger task where we tried to show actually handwritten digit recognition. And here we have trained 10,000 samples, tested 1,000 samples, and we got an accuracy of 92%. And what you see here is that this orange one is our solution. As you see, this is actually the error, so this is 8% in this case. All the other methods are various classical methods, and you see one of them is particularly bad, one of them is actually somewhat better. But please do note that what we compare is a Rydberg array, a simulated Rydberg array with 15 atoms, so this is basically the highest that we could go, that we where our parameters are the parameters that you can experimentally put into the Rydberg atom, where we compare with a classical machine with 200 neurons with of the order of 20,000. Yeah.
You're treating the field classically, right?
Again?
The field, the electric field, the light classically.
Yeah. Try it again.
You're treating the field classically.
Still? No. Now you can. Go ahead.
You are treating the field classically, right? Basically, my question is that when suppose the spin flips, it can still decay, right? Animate a spontaneous photon.
Yes.
So that might cause more errors. So won't you need...
So you mean the driving field?
Yeah,
the driving field can be treated classically in this case, yeah, because that's actually pretty strong. Yeah. I don't know what you could do with single photon fields or so. That's an all completely different question here. Okay, so our qubits are all in the atoms, not in the field.
And they do not decay into other...
They do decay, but they don't decay so quickly. So
Okay.
these Rydberg states are relatively long-lived. But of course, the point is to keep the training long enough that even if some of them decay, that this still does not make the solution worse, right?
Okay.
And that for that, you need a certain redundancy. And in principle, the idea of, and I should have said that in the beginning, so in principle, the idea of these big kind of these reservoir computers is that you in principle can make them easily big enough that you have quite a large redundancy and they are actually pretty noise resilient. We cannot put that in our simulations because we cannot make the simulations so big. But here is also a good time at this view graph that exactly this scheme is actually, I think, implemented at Quera as we speak. So let's see how this comes out. So I think this is the first time that we actually tried this out. Okay. Yep. Our 15 atoms, yes. The real Rydberg array is of course much bigger, and it will have whatever coherence you guys have at Quera, right? Okay. So yeah, that's what I just said. Okay. One kind of in between, one of the things that we are following very briefly is that there are quite a lot of ways how you can enhance a quantum circuit with a classical circuit. And one of the tricks that we are using kind of on the side is that you can do a lot of quantum circuits that, however, are very easily classically simulable, like, for example, so-called Clifford circuits. And if you don't know what that is, don't worry about that. And put these two together, which in principle enhances easily the size and also the expressivity and the trainability. And we have actually tried this, and we have done a little bit of quantum chemistry, but I don't want to go into details here. I just wanted to say there are still other ways than making the experiment better. And of course, we try to do everything at the same time. All right. So these quantum, as we have shown in this paper that I cited before that you didn't see, that works, but we don't quite, this is all heuristic. We haven't done any proofs here. So the question is, can one do this provable? And can one actually build quantum algorithms on such a machine systematically? And in order to answer all of these questions, a good question to ask, what is the smallest building block of such a system? And that's what the next 5 minutes or so of my talk are about. So here, let's briefly go back to classical, because that's an idea that people came up already classical. So you have some kind of artificial neural network where you say, okay, let's take the smallest building block of that. So the smallest building block is highlighted here. It has n inputs and 1 output, and all the inputs are not connected to each other, but only to the output. That's the so-called perceptron, and this name perceptron, I have this was coined some kind of 30 or 40 years ago already. And the perceptron by itself, especially classically, is actually pretty weak. It cannot approximate all the functions by far. But the idea is that if you put many of them together, and of course we can kind of divide our whole system into perceptrons, you can basically do everything. And the idea is here that the output on each single perceptron is again this kind of function that we saw as the update rule before. But what we want, or what Dave wanted in the classical case, is a nonlinear function, which is, for example, a sigmoid of this update rule. This has the big advantage that it's very, very noise resilient, as long as one remains in this, basically in this half where we are on the positive side of the sigmoid. And now the idea is, of course, quantize this thing. So here is this classical perceptron, again, all the inputs summed up in order to calculate this h, that's the same that you saw before, that's passed through a nonlinear function, and out of that we produce some output, which basically says either yes or no. The quantum perceptron, in principle, is the same thing. We have this local function, but we have this driving field, but we don't have a nonlinear function, because this is quantum, right? There is no nonlinear function. So in order to do anything which kind of is useful, we have in that case to at least a priori, we have to add some pulses to the time evolution. So from now on, we assume that we can pulse the system, and part of the examples that I show, we pulse globally, and partially we even have to pulse single qubits. So this is a little bit harder. So how can we, just in between, how can we implement this? So here, ideally, we have two different kinds of qubits, for example, the blue ones and the red ones. If we assume tweezer arrays, that could be, for example, different Rydberg states. It could be two species atom arrays, or it could be reconfigurable architectures. The latter is already there. People, I mean, in Quera and in Misha's lab, they can kind of move stuff around. But other people have actually already implemented all of the other ideas. So in principle, this quantum perceptron idea is readily applicable. But why should we? So, first of all, one can show that the quantum perceptron is actually a universal quantum computer, for which we need an entangling gate, a single qubit gate, and identity gates. So the entangling gate is the most important, because you will see this again. So what you do, the red qubit is this output qubit, and you drive this very hard. If you do this, you create an effective Hamiltonian which connects the input qubits in the following manner. The single qubit gates, well, you need single qubit rotations. So if we need that, we need this single kind of accessibility. Some of that can be done with global rotation. And the identity gates, well, if you really need that, unfortunately, you need to use some decoupling gates. What does that tell us? That means a quantum perceptron can be used as a universal quantum computer, but it's not very efficient. Right? So this is only to show you that in principle this is possible. This is not to show you that this is the best way how to run it. The best way how to run it is still analog. Okay, that's what I just said. So let me just show you that here this gets a little bit technical also in the paper that you again also cannot see. This is another paper than the one that I cited before. You can formulate this quantum perceptron as a quantum circuit where we have all the input qubits are the n first qubits, and the output is the n plus first qubit, and only the last qubit is measured. And in between, we assume that we can have single qubit rotation and this kind of combined update roll type evolution, and then the kind of the learning and the stepping is done classically as before. So we have shown that training works well, and we showed energy measurement. I will show you that in a second, and quantum metrology. That's is the second but next slide. So how can we do an energy measurement with a quantum perceptron? So here is exactly the case that I showed you before. If we drive this output qubit very hard, we get a total Hamiltonian which consists of HIJs, which connect I and J input qubits indirectly, but such that you can write them directly. And the total Hamiltonian for all of the atoms actually looks as it looks up here. And this is, I mean, you just need to write it down and look at this. So we get, in particular, the one with the 0 is actually an O, and is the output qubit. And what we get is that we get this input with the positive superposition of 0, 1, minus the input times the negative superposition. So this is, of course, a somewhat limited Hamiltonian, but if we allow ourselves to put up various pulses in various directions, we can make a much more general Hamiltonian, and that one, of course, doesn't do everything, but it does already quite a lot. That's what I just said. So here, again, you don't see the bottom. So what we do what is nice about this is that here all the rotation are global. So that's actually relatively easy to do in the experiment as it exists now. And then we have this evolution of whatever Hamiltonian we put together here. And what we get out at the end is an expectation value for our measured output qubit, which actually is exactly the energy expectation or proportional to the energy expectation value. So in order to kind of measure the energy expectation value of your quantum state, you just have to do this measurement often enough. Okay, which is actually rather remarkable because energy measurement, as easy as this is for us to calculate in quantum mechanics, is actually relatively hard to do on a quantum computer. Normally you need to do full state tomography, etc. Here we basically do it by measuring a single qubit. You have to measure it a couple of times though. So that's the first thing, and the second is we use exactly the same setup and the same Hamiltonian. Sorry, I'm just trying to keep track of my time here. The second is where we use this exactly the same Hamiltonian. But now if you look at this Hamiltonian a little bit closer, you can see that we in principle can time reverse or reverse for now the input Hamiltonian just by flipping the output qubit between plus and minus state. So how does that help you to do metrology? So there is some set of ideas which don't come from quantum information theory at all. I think first and foremost is Vladan Vuletic's group in this, which I think I have also cited somewhere here, which you can see, where you can use the idea of quantum Fisher information in order to really do really good metrology. So how does that go? You start with an input state, which here, I'm sorry, I should have read it. An input state psi, which is on the input qubit, and the output qubit in the plus state. Then you let this time evolve with some Hamiltonian that in the kind of traditional way of running that squeezes our state. So everybody knows that metrology can be done better with squeezing, okay? And I'm not telling you how, I'm just telling you. Turns out that there are ways how to entangle the system or scramble it that work considerably better, but only if you actually can, for squeezing in order to kind of project it back to the original case, you have to unsqueeze it again. In case of general scrambling, for which you can, for example, have a really, really complicated Wigner function, we have to basically time revolve it backward in order to kind of get to read it out decently. And that's exactly the idea that we have here. So we time evolved it. So at the end, after the first time evolution, we have a scrambled state, but still the output qubit is untouched. And now we make our measurement. For example, we try to measure some kind of dark matter or something like that. And then we flip this output spin, which is kind of independent. And then we time evolve it again. But here, the time evolution, of course, now goes with minus h, right? So it actually effectively time evolves backwards. So what we come out with is with this kind of unscrambled state, which is, however, now changed by the fact that we have done this sensing before, which gets us from psi to psi prime. And here we are from, the difference that we now see is between psi 0 and psi 0 prime, which is the original state, which has a potentially much amplified difference, and how much it's amplified is determined by the quantum Fisher information. So this whole cycle is actually, as I said, is done by Vladan Vuletic's group and others. But what they cannot do so far in a general way is time reverse the Hamiltonian, and our system basically supplies this. And since I'm out of time, I think I will, so one of the things is that we cannot, this kind of Stepping is very hard, and we have kind of come up with a way how this can be done much better, but I'm not going into this. So let me see whether I can. I think I don't have any other chance than just go through all of that. I wanted to show you some quantum chemistry, and if anybody is interested in quantum chemistry, I'm very happy to tell you that, but not now, because otherwise Dana is really mad at me. Sorry. This is via Zoom, then I have to skip to. So here I just would like to show, so the people in the upper row are my students and postdocs who were mostly kind of responsible for that in this winter picture is the rest of the group. And please do note that this is Valentin who is with you guys now. And there's also the quantum chemistry, which is a different set of people. But I want to just thank you at this point.
Yeah, thank you for a very interesting talk. It's really wonderful and exciting things. Are there any questions? Yes.
Thanks for the talk. So in the first half of the talk, you said you simulated AND, OR, and NOR gates with the quantum neural networks. I'm assuming that's within the limits of the 15 atoms. So my question is, how many atoms would you need to simulate an XOR gate? And if it's physically possible to engineer that?
The point is the gates themselves are just meant on 2 qubits each, right? But the learning is done in principle on a network that's much bigger. So the way how we have done that, we have, I think qubit 2 and qubit 3 is AND, qubit 2 and qubit 4 is OR, qubit 2 and qubit 5 is XOR. And the rest of the network is for learning. But the rest of the network in this case that we did where we got to, I think, 80 or 90% or so, is, I think, a total of 8 qubits only, right? So the overhead in that case is somewhat minimal. So in principle, the idea is you can do much better if you have a bigger network.
Thank you.
If there's no other questions, let's, oh, there is? I'm sorry. Yes, yes.
Thank you for a very nice talk. So so on the quantum memory side of things, do you have any idea how it's, of course I know that it depends on what kind of network you have, but how does it scale with the number of qubits?
Very good question. All of these scaling arguments right now, I can just not tell you. I can tell you some where we are guessing. The quantum memory, however, I think mostly depends on the decoherence of your system. And we are, if one has an active system, you can in principle kind of do that longer. That's a little bit, physics is a little bit similar to kind of, you know, spin echo techniques, but you are limited. And I think at the end, it's also, you need a large enough system, so the system needs to be somewhat larger than the amount of input that you want to store. But usually, that is then not a question of time, but it's a question of noise. So the larger your noise is, the bigger your overhead has to be. My guess is the overhead is probably linear, but there's no proof to that yet. Okay.
Let's thank our speaker one more time.
Thank you.
Good to see you. Okay.
Connecting to our system.
Let's see if this works. Yeah, oh good.
I'd like to introduce our next speaker. Our next speaker is Professor Dana Anderson. He's a professor at in the Department of Physics and Electrical and Computer Engineering at the University of Colorado. He's a co-founder and former CEO of Inflection and serves as the Chief Strategy Officer of the company. A GILA Fellow, Professor Anderson's research spans a spectrum of topics, including atom-based precision sensors, atomtronics, RF sensing with Rydberg atoms, quantum signal processing, and machine learning in optical and atomic systems. Welcome and
Thank you.
thank you.
Gesundheit. It's a pleasure to be here, and I also want to thank the QSC in particular. It's been very rewarding, very productive to be collaborating with colleagues at Los Alamos, at Oak Ridge, and elsewhere. And it's a pleasure to be back again at this summer school. I think it's an incredibly wonderful and unique opportunity to see what's up in quantum science in general, and the Quantum Science Center in particular. And here at Purdue is just an outstanding place to be doing your research, if that's where you're carrying out the research. The rest of you, I hope I get a chance to speak with you at the various events today and tomorrow. So, as you heard from the last talk, the order of these three lectures might not be ideal from the point of view of going from classical to quantum. We're going to indeed talk about using classical machine learning on a quantum system. And it's driven by a very practical interest in making better sensors. So let me give you a particular example, and it might be useful to, because my slides are dark, to bring down the shades a bit. Might be easier to see some of this material. But when GPS is unavailable, so GPS is mostly how you know where you are. Your phone knows where you are, you know where you are when you're in an airplane, and so on. And the question is, how do you get around when GPS is unavailable? And the one way to get around and to know where you are without having any outside information, so no RF in particular, no GPS, no imaging, say, no LiDAR, etc., that's with inertial sensors. And so they include, typically when people say inertial sensing, they mean accelerometers to measure acceleration, for gyroscopes to measure rotation. There's actually a wee bit more, but this is what most people refer to as inertial sensing. So knowing where you are is carried out formally with an inertial measurement unit, makes sense. And I thought I would just, since this is meant to be an educational event, give you some guidance of what is used in the community and the literature. Inertial measurement units are characterized in terms of performance grades, from instrument, that's more or less what's in your iPhone, let's say, to when your iPhone tells you that your phone is rotating or accelerating and so on, tactical, navigation, and strategic. Strategic is the most precise instrumentation for determining where you're going and where you are. And I just thought I'd show you a spec sheet, just like you might buy for some device in the lab. You can get a spec sheet for strategic grade inertial sensing, and just to characterize things where we sit. So they're characterized in things like angle random walk, that's essentially diffusion noise, and things like bias stability. And to note, the bias stability is 1, 2, 3, 4 significant figures in degrees per hour. So after an hour, you're 10 to the minus 4 angle off of where you thought you were or where you started, for example. That, if you think about it, that's quite outstanding precision. There's also an accelerometer performance, but in an inertial measurement system, it's usually the gyro and not the accelerometer that limits performance. And to give you another example, so being underwater is a good example of not having GPS. A strategic grade system will typically give a very good operating strategic grade system uncertainty in where you are by about 1 nautical mile in 360 hours, all right? So several days. So that's a commercial seat. Nothing special about it, except you got to go find it on the internet. And one of the most challenging GPS-denied environments is space. And the question is, how does one navigate in deep space in particular? You know, this Star Trek and all the shows you love, Star Wars and so on, they don't bother with that, telling you how you know where you are. And it's in fact incredibly difficult to know where you are and where you're going in deep space. It's done basically by radio ranging, which is expensive, it's slow, it's a very poor way of navigation, and of course, when RF isn't there, it doesn't work at all. So how do you navigate? It's a lot harder than you can imagine, and a whole lot of things get in the way of navigating well, and even the highest performance navigational system you could manage to acquire today is not good enough for navigating very long in space. And in particular, one of the things that gets in the way is dark matter, possibly, because it has a gravitational pull. A whole lot of other things get in the way. Planets, asteroids, stars, black holes, not just because they're opaque or something like that, but because they have gravity. So the fact is, ideally one has an inertial system to take acceleration, rotation, and gravity gradients to manage the equivalence principle. And gravity gradients are just sort of a combination of accelerometers, but nevertheless, as we'll see, they have a different level of precision. So again, I'm trying to scale you and motivate you for why getting better sensors is a compelling thing to do. All right, so if we think we're going to be traveling around in space, very much we want to know where we are with better sensors. And so today we'll address the questions, what does quantum sensing bring to the table? So as an example, I mentioned gravity gradients. It's the only way to determine the presence of gravitational field is by measuring a difference in acceleration with distance. Here's a rather trivial illustration. You well know if you start with two objects from rest, they start out at different distance from the center of the Earth, for example. Well, starting at the same rate, the first one will begin accelerating faster because it sees a larger gravitational pull. And if you don't measure the gravity gradient and you didn't have outside information, you could crash because you don't know that you're accelerating in a gravitational field because you're just falling. All right, so gravity gradients are the other key to being able to navigate in space, for example. I think maybe I'll skip this. I think you're familiar, I hope, as those of you who are physics trained, that it's Einstein who says you can't really distinguish between, say, on Earth, the force that's holding you up against gravity versus an acceleration of a rocket given by the same number, g, as the force you feel on Earth, for example. And likewise, there's free fall. You can't tell when you're free falling because there's no measurement there's no local measurement you can do that tell you that you're falling in a gravitational field. And just to scale you there, the US and Europe have had two series of missions, I should say, one called GRACE, that's the US, one called GOCHI in Europe, to measure the Earth's gravitational field, in particular for Earth monitoring. And so the top one is GRACE, which consisted of 2 satellites whose distance between them was measured very carefully, and they have accelerometers inside. Or GOCHI had separated accelerometers, separated so that you could determine what the gravitational gradient of the Earth's field was. And using this technology, they measure the Earth's gravitational anomaly, it's called, how unspherical is the gravitational field of the Earth. And why is that useful? Well, for example, over time, because of climate change, we lose water from the polar ice caps, from Iceland. And this is the only way that you can quantitatively measure the water loss, the mass loss from these large ice accumulations. So you'll see here, this is what the GRACE mission measured per month, the decay in the mass you're seeing on the curves, and the images are images of the gravitational change of the gravitational field of the Earth due to the polar water being lost from these bodies of basically ice. All right, and so one of the things we are interested in doing is in future missions for Earth monitoring of improving the measurement of the Earth's gravitational field. So we seek a gravitational gradient. They're measured in what's called an ETVOS. I'll tell you what an ETVOS is 10 to the minus 9 per second squared. And they want to be able to measure it somewhere between 100 and 1,000 times better than they did during these early missions. And so this is an extremely challenging number. And the only way we can imagine doing it is by taking advantage of atom-based quantum technology. So, in fact, in many ways, we are reliving a period of evolution of laser technology that started in 1963. 1963 saw the first laser gyroscope, and it was a meter on a side, and this guy who first did it said, I did this despite my managers saying it would never work. He wanted to prove them wrong. A mere 20 years and 30 years later came the laser gyroscope, and a little bit after that, fiber gyroscope. And those are the instruments you saw on the data sheet for providing strategic performance for navigation and guidance and things like submarines and other critical applications of navigation in a GPS-denied environment. So these things are based on the Sagnac effect, and these are actually quantum devices, to be all fair. They're not quantum 2.0, but they're certainly quantum devices because they're based on lasers. They're based on the Sagnac effect, and the way to think about a laser gyroscope is that it lasers in two directions around a ring, here shown as a circular ring, and if nothing bad is happening, then the two laser frequencies are the same, and they form an interference pattern. And the way to think about this thing called the Sagnac effect is if you're rotating left or right, you merely go over the nodes and antinodes as they stay stationary and the whole device, and maybe the spacecraft it's sitting on is rotating. You can just measure by interfering these two beams going over these nodes and antinodes, and therefore for a given rotation rate, you simply get a beat frequency proportional to the rotation rate. And the other technology that was developed mostly in the 80s and matured in the 90s and so on was the fiber gyroscope, which uses the same physics, but instead of having a resonator that lasers, you inject light into two directions. And effectively, the one that's going along with rotation and the one that's going against rotation have different speeds. So the one going against rotation looks like it's traveling a little faster, with rotation a little lower to make a complete round trip. And thus you get a phase difference instead of a frequency difference, and that phase difference is proportional to rotation rate. And it's really the fiber gyroscope that has dominated by now the development. All right? So that's the basis of gyroscopes. Now let's talk about sensing with atoms. All right? So atom interferometry, I'm not going to go deeply into it, but just an overview that atom interferometry provides a superbly sensitive instrument to measure accelerations and rotations. And the basic way that they go is just like optical interferometry. You take a beam of atoms instead of a beam of light. You split that beam into two using, instead of, say, in light, you use a half-silvered mirror. You would use a pulse of light. And so on this axis, horizontal axis, is time. You use a pulse of light, And then you'd use another pulse of light that serves as a reflector, and finally a third pulse of light that serves as a recombiner, and you measure the relative number of atoms that come out these two ports, and from there you can determine a phase shift. There is no phase shift if nothing's happening, but if this system is either accelerating or rotating, you'll get out a phase difference, meaning different numbers of atoms out these two ports. All right, and as I say, it looks just like optical interferometry, and the process of interferometry is the same in both cases. You split, reflect, and recombine atoms that are propagating. So, taking the gyroscope as an example, what would it take to achieve high performance? Let's imagine that we can somehow get atoms to go in a circular path in both directions. If you were asking, I want a strategic grade device, I would need, it turns out, a loop radius of about 0.5 millimeter. I would need about 1,000 atoms per second staying in this resonator 1 second. This is just an example, lots of design choices. I had a velocity of about 1 meter per second. The point is that a very tiny atom device, 0.5 millimeter in radius, to get strategic grade performance. And this is enormously smaller than the laser gyroscope or the fiber gyroscope. Except, of course, I haven't shown all the lasers. That's the truth in lending disclosure. I have a lot of work to make it a practical instrument and make it a small instrument. But I want to talk about how we do that. So we're going to leverage what I consider humankind's most quantum technology, and that's the optical clock. So I have a diagram here. Don't worry too much about if you're unfamiliar with Allen deviation. It's a way of measuring performance as a function of how long you integrate a signal. And what I've drawn here, and by the way, down is good. So this is basically uncertainty, and the smaller the uncertainty, the happier you are when it comes to a clock. And what I've drawn up here, this, where it says CS, cesium clock, that shows the performance of the machine, of the instrument that keeps world time at NIST and the Naval Observatory, and similar things around the world for telling what time it is. All right, so that's the world timekeeper up there. I want to tell you where in this diagram sits the most accurate clock. It's not really a clock because it sits in a lab and it doesn't tell time, but it's a timekeeper for when it's operating. It is, roughly speaking, 1 million times better than the world timekeeper. And that's a clock in the lab of my colleague Jun Yi. And it's now reaching an instability of less than a part in 10 to the 20th. It's just unbelievable to make a measurement whose uncertainty is less than a part in 10 to the 20th. All right, so it's 1 million times better than the standard atomic clock technology. And how does that clock work? It works, among other things, by trapping ultra-cold atoms in a lattice formed by 3 pairs of interfering laser beams. So it's called a lattice clock. And the key is here for us is that this clock demonstrates that holding atoms in a lattice can be done without really upsetting the atoms so much. They can sit there and they can tell time to extreme accuracy. So the atoms are cooled to near absolute zero. They're trapped in laser beams. And the point is, holding atoms against vibration and other annoying forces is in fact very straightforward to do. Let's first start with a pair of laser beams traveling vertically. And atoms, if this is detuned to the red of a resonance, atoms like to go in the high intensity regions. And this is what can hold atoms up against gravity here on Earth. And you can generalize this to 2D arrays and 3D arrays and so on. And they're essentially perfect periodic arrays of atom traps. And the key is, from a practical point of view, atoms are held in place with tens to hundreds of Gs. all right? So it's like bricks and mortar. Even though the atoms are in vacuum and seem like they're floating around, they aren't. They're held very, very tightly. So that makes it practical for sensing applications. And then, but if atoms are in the lattice, how do you use them for sensing? Because after all, in interferometry, we saw the atoms moving. And the answer is, you learn how to shake the lattice in just the right way using machine learning techniques. And so if you imagine an egg crate with a bunch of marbles in it, if you learn to shake it right, you can get those marbles to move, and you can get them to move in some reasonable way. In the case of atoms and wave functions, we're interested in carrying out interferometry with atoms that are held in a lattice, but nevertheless carry out all the steps of interferometry. So experimentally, this was first demonstrated a few years ago, 2018, and now working on a system that's entirely rebuilt to make it more capable. So we train atoms stuck in an optical lattice to become sensors. All right, and we do two kinds of systems. I want to say two kinds of learning, but the one is called optimal control, and optimal control people don't like to say that they're doing machine learning, but I don't like to have to put too many words in it. We still call this a machine learning technique for the sake of giving talks and so on. And the other one we use is reinforcement learning, which is much more of a traditional neural network class of machine learning algorithms, algorithmic approaches to doing, solving this kind of problem. So, lots of reasons why this makes things very useful. And in particular, the goal is to build something which is, here's the laser gyroscope. And I couldn't make this little ball small enough to make the represented in size. The core sensing volume is just reduced dramatically. As I said, the truth in lending disclosure is we still have to reduce the size of the lasers and so on. So here we go now into what we're trying to accomplish with machine learning. So an optical interferometer is produced by taking a laser beam, splitting it in two with a half-silvered mirror or polarizing beam splitter or what have you, and then combining after propagation and after reflection from two mirrors to measure their phase shift by measuring the light out two ports. Atoms, the same way as I showed you earlier. And so we'll make an interferometer sequence by actually shaking the lattice. So think of sine wave, think of an egg crate that we're moving back and forth. And we're going to shake it, first of all, to cause atoms to split. The wave function will split into two, will allow them to propagate, will then reflect the atoms. So if they were traveling to the left, they reverse the momentum and go to the right. If they were going to the right, they now reverse their momentum and go to the left. So we make a mirror, let them propagate, and finally we shake the lattice to recombine them. All right, so we're carrying out machine learning to learn how to shake a lattice to make a very precise, and eventually a very precise sensor. So again, two approaches. One is optimal control. And optimal control relies on having a model on the other underlying system. You say, I have a perfect lattice, and I have Schrodinger's equation, I know my physics, I can compute everything. In the case of machine learning using reinforcement learning, it's model-free. I don't know about Schrodinger's equation under the hood. I just know that when I give an input, I get an output. And I try to get the right output for my given input, say. And I learn how to get the system to behave through this machine learning, reinforcement learning algorithm. There are, in fact, lots of type of machine learning. You just heard from Professor Yellen about the system with Rydberg atoms. There's supervised, there's unsupervised learning as well. And as I said, here we're going to do reinforcement learning. And it's really fascinating, I must say, to realize what you can do with the reinforcement learning in with a real experimental quantum system. All right. So the framework of reinforcement learning is you have some environment. This is your lattice, this is your atoms. You don't really know the physics underneath, but you have some actions you can apply. When you apply those actions, you make a measurement, and based on that measurement, you reward the system for, hey, good job, or that's too bad, we're going to start over, go back to the beginning, and so on. So again, you don't have to know how the model works to make reinforcement algorithms work, but needless to say, the more you do know about your system, the better of an algorithm you can design for the reinforcement strategy. Okay, so we're going to teach now the optical lattice to become a sensor. So first, to tell you, we make observations of the state of the atoms trapped in an optical lattice by turning off the lattice light and letting the atoms fall, and then we take their picture. And when we do that, when the atoms are released from the lattice and then fall, the images then become the Fourier transform of the spatial wave function. And of course, we're doing quantum mechanics, we only get the square of the wave function. And atoms thus appear in discrete momentum states determined by the lattice spatial period. So what we should see when the atoms are in the ground state of the lattice is mostly the atoms have no momentum, 0 h bar k, where k is given by the laser wavelength. And then I'll get a little bit of a small number of atoms in each of the plus and minus 2 h bar k. Okay, h bar k is units for momentum, as you probably know. And this is what the ground state of our lattice should look like. And here is an image, and we'll magnify this up. And it is a little bright, but you see there's a very strong spot in the middle, and then there are two satellites. I'm not sure if you can see them from the back of the room. Two satellites showing plus and minus 2 h bar k. So I'm not going to go deeply into the learning algorithms or the optimal control, but just say that when you do these algorithms to say split that ground state function into a new wave function where the atoms are going equally in opposite directions, they come up with very different solutions. So this is time, this is the position of the lattice in phase, and this is about pi and minus pi, and the reinforcement learning comes up with this way of shaking the lattice. The quantum optical control comes up with something crazy for doing the same thing. Notice the time here is about 70 microseconds. These are all real systems. So two completely different solutions for how to shake the lattice. Nevertheless, they both work. So again, we're shaking the lattice. This is phase versus time. And so some way the lattice is shaken. I see part of this is just barely cut off the bottom there thanks to Zoom, I think. So here we go from the ground state, and with those shaking functions, this is what we get. We get momentum mostly in the minus and plus 4 h bar k with a little bit of satellites and others. So this effectively is a beam splitter with most of the atoms going equally in opposite with momentum 4 h bar k. And by the way, as I said, both learning algorithms come up with similar results, so I don't show separately all of them. And these are details that somebody asked about the experiments themselves. And now, let's watch over time during the shaking what happens to the atoms. Here you see they're in the ground state. The vertical axis is the momentum. Here's time. And here's some snapshots redoing the experiment and taking pictures at different times during the shaking. And here you see initially the ground state, and then some stuff happens, and at the end of the sequence, we have all the atoms going in the two momentum states equal and opposite. So here is some pretty 3D plots. I actually don't like them that much because for me they're hard to see what's happening when. But here on the left-hand side is time, is momentum. In the semi-vertical axis, horizontal is time. And this is theory, and this is the experiment. And you see that the features, what's happening to the 0 h bar k momentum state, for example, and what's happening to the plus and minus 4 h bar k, They're qualitatively very similar in experiment and theory, and to us this was rather remarkable that the match was this good. So this is a simulation, that's the actual experimental data. So when we wanted to split the atoms, we had as a target a wave function. We wanted to go from the ground state of the lattice to a pair of atom clouds that were propagating in opposite directions. When we do a mirror, the target is not a wave function. The target is a unitary operator that changes momentum from going to this direction to going that direction and vice versa. So it's different when we want to make a mirror than it is when we want to make a beam splitter. And once again, optimal control and reinforcement learning both come up with answers, but they're totally non-intuitive and totally different for making mirrors. But it turns out they work roughly equally well, although the reinforcement learning takes a little longer than the quantum optimal control, as it turns out. And so to test this, instead of exciting atoms from the ground state into a pair of clouds going opposite directions, we teach the system to go from the ground state to a highly asymmetric state, just one cloud going to the left, let's say. And so initially, what we have here is the ground state. This is time, this is momentum. The ground state, so almost everything's in the 0 h bar k here. And this is a function of time again, and we split the atom, we transform the wave function so that most of the atoms are propagating with minus 4 h bar k. And then right here, we turn on the shaking that's meant to do reflection, and you see this minus 4 h bar k transforms into almost everything being into plus 4 h bar k. And then we test it with the opposite momentum cloud to make sure it's behaving as a mirror. As I said, start with the ground state, get a minus 4 h bar k state, and see by the end it goes into a plus 4 h bar k. So this is teaching a mirror. And then we can stitch them all together to have a complete interferometer. So we have a beam splitter, we have some propagation time, we have a mirror, and then a propagation time and a recombiner. Same with optimal control. Again, completely screwy, completely different. Both do the same thing. Both give very similar results. So we put it all together, and then we can apply acceleration, which is what you see here. This is acceleration, and this is theory, and this is experiment, and this is momentum here on the vertical axis, acceleration now. So this tells you what the clouds look like at any given acceleration. So roughly here is 0. This is minus an eighth of a g to plus of an eighth of a g. This is theory, this is experiment, this is reinforcement learning. And these are the equivalent of fringes that you get in a normal interferometer, except the fringe pattern is much more complicated because there are many more ports, as we say. We also do quantum optimal control. Again, so this is now an accelerometer showing theory and actual measured experiments. So these are data, these are simulations of what happens. And the point is here is that in both machine learning types, simulation and experiment agree, at least qualitatively, and at least around low accelerations. And there's a fingerprint. So if you look at any given acceleration, say minus 0.075 g, the pattern that you get by taking a vertical strike is unique. So looking at that image, you know what the acceleration is. And this is a very small interferometer, by the way. It's measuring, a good fraction of a g, and it's just a couple of microns. Very short interferometer so far. What does it take to do high performance? Well, the next steps actually is to do the same thing, but in 2D, where we can make, this is going extra slow, where we can split the atom wave function to go in both directions, and we have a two-dimensional lattice, we can make them go in a circle and carry out Sagnac interferometry. And I already told you how small that can be and get strategic grade performance. So the summary is there's compelling demand for inertial sensing capability beyond current technology. So for space applications, for GPS denied scenarios, Ultra-cold atom technology, atoms and optical lattice offer unprecedented sensitivity. It demands a high degree of control, which we do by keeping the atoms in optical lattice, subject the atoms to forces tens to hundreds of Gs, and then controlling those forces through machine learning to control the wave function and the various operations that they undergo. So with that, I hope I've motivated you why the connection between machine learning and sensing actually has something to bring to the table for future technology. Thank you very much.
I'll open the floor to questions, maybe one or two questions. Yes or no? If not, I have an interesting question, or at least, so the data that you showed was all in one dimension, at least the Fourier transforms were all in one dimension, but you have a three-dimensional lattice.
Right now, we just have a one-dimensional lattice.
I see.
And the next step for a gyro is a two-dimensional lattice, and then three dimensions to get all 6 axes of acceleration and rotation.
Okay. Yes.
So how sensitive is this to small changes or to noise or something like that in your case? And is it a difference between the learning and the optimal control?
These are very good questions. So how sensitive? First, I will say that the one parameter we have is the lattice depth. If you keep the lattice depth, you measure that, and you keep it the same, I will say that next week's learning gives you the same result as last week's learning. So that part is good. Now, the other thing to do is to include in your learning algorithm robustness against, say, laser noise, et cetera, et cetera. That's been done by others in others' contexts. We have not really implemented that yet. Okay. Does that answer your question?
Question. Do you think these ideas can be used to understand how birds navigate and finding their magnetic north?
How birds navigate? Well, I understand they navigate by magnetic field, for example, and the magnetic sensors. What I don't know so well is, so they have that information, how they know where they are. I think you want to go to the previous talk about how these things then get a memory for where they've been before. I mean, you know, that is truly neuromorphic. And
Checking it's like vibrations of these elements, so somehow the question is using the same idea of vibration.
poor birds, I hope not. I'm kidding. I don't really know how the birds end up. I know how they sense the magnetic field in principle. I don't really know how they learn. Except by what we're just accustomed to is the same ability of humans to learn and memorize. But I don't think it has, you know, remember our memory is inside of a classical computer. It's not inside the atoms. And in that sense, I think the memory for the bird is likewise in its brain. But certainly it's a fascinating question. Okay?
And let's thank our speaker one more time. Okay, I think we'll get started. Our next speaker, and before our lunch break, is Professor Mikhail Lukin, whose group at Harvard University focuses on theoretical and experimental studies of quantum optics, atomic physics, and quantum information science. The emphasis of the studies on quantum systems, including or consisting of strongly interacting photons, atoms, molecules, and electrons. They're developing new techniques for controlling quantum dynamics and studying the relevant fundamental physics phenomena. And with that,
Thank you so much. So it's a great pleasure to be here again. I'm really kind of fascinated to and looking forward to learn about what Quantum Science Center has accomplished, and it's of course great to see, both old friends, also new faces. So I will talk today about building quantum machines, and this is the first talk in the school about that. And I will make maybe a short introduction. So as most of you by now know, this is a major worldwide effort, and it involves now, players in industry, academia, and government labs. It involves also very different platforms. And all of these platforms are making amazing progress towards building things like quantum computers. Where is this field now and what are the big challenges? So I would say the key outstanding challenge in the field can be summarized as something that I sometimes called ultimate quantum rivalry. And in this kind of ultimate quantum rivalry, you could say, it's a competition between the different platforms. Actually, that's not, in my opinion, true. It's really a competition between two forces of nature. One is the force of controllability. So you would like to keep all of the systems under complete quantum control. You cannot make often, and if you do quantum algorithm, you cannot make a single error anywhere, otherwise your result is useless. But at the same time, and this control is achieved now in many of the systems at a level of few isolated qubits. But at the same time, we would like to scale the system up. And these kind of forces of controllability and scalability, they are actually in contradiction in many areas of science, technology, but more generally human activity. And at this point, in quantum in particular, they really collide at the full force. So where is this field currently now? So I like to call this time that we are living in now is what I would say an era of quantum discovery. So basically, there are now machines which are big enough, quantum enough, programmable enough that we really can use them as tools for scientific explorations. And I will show some examples of this. And so basically, what it involves is essentially executing tasks that modern classical computers, even supercomputers, cannot do, and it typically involves experiments, with hundreds of physical quantum bits. And then what we can do is we use the system to basically test and implement algorithms and study applications, mostly scientific applications. But also we learn about how these kind of larger scale systems behave, and it helps us to basically build bigger and better quantum machines. So I will focus on one specific approach to building quantum machines. It will involve arrays of isolated neutral atoms. And I should, from the get-go, start that the number of qubits in this system is really not the main problem. So every time we start our experiment, we use something which is called magneto-optic trap, which allows us to capture tens of millions of laser-cooled atoms. So each of these atoms can host a qubit. So the key challenge is to learn how we can control and manipulate these qubits. So the number of physical qubits is essentially unlimited, so the key challenge is classical control. So against this backdrop, a few years ago, we kind of initiated a research program in which we built this kind of quantum system literally atom by atom. So we start with very low density gas of such cold atoms in a vacuum tube. And then what we do is we shine the focused laser beams into this vacuum tube. So, and with each of in these laser beams, essentially what they do, they basically attract the atoms to the point of highest intensity. And so if the atoms are cold enough, they can grab and capture these atoms. And we focuses laser beam so tightly that each of these so-called optical tweezer can at most grab one atom at a time. So it can, when we typically load, we either load 0 atoms or 1. So if we load more than 1, then these 2 atoms cannot just fit in this trap. They get ejected through something which is called light-assisted collision. And so in our experiments, we don't just start with one beam like this. We by now starts with thousands of beams, and basically we try to load all of these atoms at the same time. But on each given shot, we don't load all traps. So what you typically have is something of the type showed here. Some traps are loaded with single atoms, some are not. And so basically the system has an entropy. So to get rid of this entropy, what we literally do is we take a picture of atoms, which is loaded, figure out which traps are full and which are empty, and either eliminate the empty trap or just refill them with the atoms. And after that, we can actually move the atoms around and create any sort of arrangement that you desire. So this is all done with optical techniques. So, you have an optical resolution limit. So typically, in our experiments, the atoms are separated, the trapped atoms are separated by few micrometers. At this point, they don't talk to each other, they don't interact. To make them interact, what we do, we excite them into states with large principal quantum numbers, the so-called Rydberg states. At this point, the atoms start feeling each other, they start interacting, and that's what we can use to do things like quantum logic or engineer the interactions. And this is an approach involving collaboration of 3 laboratories: my laboratory, laboratory of Marcus Greiner at Harvard, and the laboratory of Vladan Vuletic at MIT. So just a few more words about this Rydberg interaction. So the reason why we like Rydberg atoms is because they have very long lifetimes and also very strong interactions. In fact, if you excite the atom to the principal, to a state with principal quantum number 100, the interactions between atoms, the van der Waals interactions between atoms, such atoms are larger than those of the ground state atoms by 14 orders of magnitude. 14 orders of magnitude is a large number, and if you are clever, you can use it very, very well. So one specific approach which we use is something which is called Rydberg blockade. So the idea basically is the following. So if you have 2 atoms which are sitting very far away and you start exciting them resonantly, then they will just undergo independent excitation, independent Rabi oscillations. However, if you bring the atoms close and still try to excite them resonantly, what happens in this case is that eventually this interaction between atoms takes over, and so you will be able at this point to excite one atom or another, but never both at the same time. So this phenomena is called Rydberg blockade, and basically the essence of that is that the simultaneous excitation of 2 atoms is blocked when the atoms are closer than this Rydberg blockade radius. So it turns out that it's actually a very good mechanism to entangle atoms and do quantum logic. The reason is it's actually very robust. At this point, this excitation and entanglement is insensitive to motion of the atoms and the exact position, simply because if they are under blockade, you just can excite one and not the other. So to summarize, in what follows, I will describe experiments in which we basically prepare the arbitrary arrangements of the atoms, and then we subject them to laser pulses which change the atomic internal state. Sometimes we excite them to Rydberg state, sometimes we just rotate the spin state, we change this hyperfine state of the atom, and then after this coherent evolution we will just take the picture of atoms, but we will at that point take a picture in a state-dependent manner. We will only image atoms, for example, if they are in one state and not the other, and it allows us to do a projective readout. So I should mention now that this effort is now a worldwide effort. So I think, I stopped basically counting. There are several hundred experiments under construction, and actually there are at least 6 companies which are trying to commercialize this technology. So over the last 2.5 years, in our lab, we have been running what we call generation 2 of atom array. In this, so we by now have transitioned to generation 3. I will talk about it if I have time at the end. So in this case, what we do is we use special light modulators, basically a computer-generated holograms, to create this kind of arrays of tweezer light beams. So basically, what you can do by just programming on the computer, you can use it as a diffraction grating, just reflect the light on a certain angle, or if you sort of generate a light pattern, you can generate these patterns of the light, basically a large number of very homogeneous kind of light potentials, which when we project into the vacuum chamber looks like this. Right? So in this case, it's actually about 1,000 of these optical traps. These special light modulators are actually amazing devices. I think they are similar to those which are used now to, for example, project this light in a projector here. But there is one disadvantage. They have one disadvantage. They're actually slow. It's very hard to kind of dynamically change this. So basically, to dynamically rearrange atoms, we use a second set of optical tweezers, which are created by two acousto-optic deflectors. So acousto-optic deflector is a device where you actually put in laser beam, and then you insert a kind of radio frequency tone or number of tones. And basically, for each radio frequency tone, due to acousto-optic effect, you shift the direction of the laser beam. So acousto-optic deflectors is devices which are used in the barcode scanners in supermarket, for example. And so with this approach, we can actually use the system to move basically columns and rows of atoms kind of independently and basically rearrange the traps. And all of that is computer controlled. So in this kind of second generation, we basically, can create system like this. So there's basically various regular arranged patterns. We can also create an arbitrary configuration of atoms. So here is, for example, your program, what you want. You want atoms at these positions. You press the buttons and, here there are the atoms. So at this point, we were able to basically start with about 600 traps, and each of them is filled with 50% probability. It results in about 300 sorted atoms, and each trap is actually filled with reasonably high probability, 99.5 and above. So what can we do with that? And sort of one kind of natural application is literally realization of the idea of Richard Feynman that Travis talked about this morning. So what he envisioned is a system where we can actually, kind of put single atoms at will, kind of at any point in space, and then create some interactions between them. So in this case, interactions are those which are mediated by this Rydberg blockade. And so this is actually a Hamiltonian, so it's an Ising type Hamiltonian, where in this case ground and Rydberg state form the effective two-level system, so you can drive it coherently. This term is a laser detuning. It acts as a kind of chemical potential. And so what we can do, we can basically adjust the Rydberg blockade, for example, adjust it to a nearest neighbor, and then start playing with this chemical potential. When this chemical potential is negative, actually you don't, it's energetically unfavorable to excite any of the atoms. So basically all atoms are in the ground state. But if you now, for example, sweep the detuning, if you change the detuning from negative to positive in a kind of slow way, you can find, in this case, you find this state which is basically a perfectly ordered, in some cases, in some shots of the experiment, you find this perfectly ordered antiferromagnetic pattern. Right? So this is basically indicating that these interactions between atoms govern some kind of new phase which is created. So admittedly, if you repeat this experiment many times, you don't always see a pattern like this. So you often see some domain walls, some dislocations. So you can now have to analyze this data in different ways. You can analyze them from the point of view of correlation function. So it's a density-density correlation function showing that you basically have correlations spread across the entire array. But you can also analyze these images individually. You can, for example, ask what's the probability of this perfect order, this one or maybe a complementary order shifted by lattice side to appear. So actually, it turns out that even though this probability is relatively small, it actually decays exponentially with system size. Still, it's the most probable from all microscopic states of the system. And what's especially interesting is by using these tools, you can study, for example, the dynamics of how rapidly correlations grow. And actually, this allows you to really probe the physics of quantum phase transitions. So this is an experiment what we did early on, where basically we just go with different speed across this phase transition and watch how rapidly correlations grow. And it turns out that under certain conditions, all of these different curves, can be collapsed into one. And actually, this is a consequence of something which is called universality associated with the quantum phase transition. So all of this dynamics, it turns out to be governed by just two numbers. These two numbers are known as critical exponents, and this is a way to measure those. So basically, like doing experiments like this, for the first time we observed what's called 2+1 Ising quantum phase transition. This is a quantum phase transition which is described in the books, but no one has able to ever see it in the lab. And this, this is what, for example, we observed here. So this kind of illustrates a little bit the tools and techniques which, we use in our experiments. And so basically with this system, for over 2.5 years, we had actually a lot of fun. We have explored various different orderings, various different phases. We studied non-equilibrium dynamics by keeping the system far from equilibrium. We actually made some discoveries. We observed a phenomenon which is by now called quantum many-body scars. So I think last year in this school I talked about our experiments demonstrating for the first time topological spin liquid, and we actually even created a kind of a small baby version of topological qubit. So this has been kind of a challenge in this field in over 50 years. So basically it was suggested by P.W. Anderson in the early 70s and have up to that point have not been observed in a lab. And actually we are also interested in experiments like what Mike talked about braiding, but we would like to do this braiding under fully controlled way. So we'd like to create anyons, capture them, move them around, and basically see these changes done in a kind of deterministic way. But I'm not going to talk about that. Today I will focus on two kind of more recent projects, one involving the use of this system to accelerate combinatorial optimization, and another one is a kind of a new development involving a new architecture for programmable universal quantum computers, which in particular involve this idea of quantum error correction. I should say here also, and it's unfortunately kind of cut from this slide here, is that we have now more than one machine in town. So in fact, across the river from where our Harvard lab is, we have a startup company which actually built its own machine. It's actually called Aquila, and this Aquila became publicly available last November. So it's actually available online, and I think many of you have already played with that. So it's actually really a tool for kind of scientific discovery, very much in the spirit of what Travis was talking about. So I'll mention a little bit that at the end of my talk. So let me just real quick talk about one example of how we can use this machine. And this is an application to solving optimization problems. So more specifically using quantum machines to try to accelerate the solution of optimization problem. So the specific optimization problem we'll focus on is called maximum independent set. And it's a very simple problem to formulate, but actually a very hard problem to solve. So specifically, this is a graph problem where we have some nodes or vertices of the graphs connected by these links, or sometimes they're called edges. And the problem is the following. So you'd like to color these nodes, these vertices, red, for example, and you'd like to color as many of them as possible, but you are not allowed to color the two vertices which are connected by the edge. And so what you see is immediately if you start, with some coloring pattern, at some point you run sort of into, a contradiction. So you have to start from scratch. So it's kind of a little bit gives you a feeling why this problem is hard. So what's shown here is one specific instance of this problem, which is called maximum independent set on a unit disk graph. So here, again, this cut. So basically here all vertices which are within given distance are connected. So it actually turns out that even this instance, to find exact solution in the worst case is actually very hard. It's actually a NP hard problem, but actually it turns out that these kind of problems are all, there are many practical applications in areas like networks, logistics, and machine learning. But more importantly, if you have followed my talk up to now, you will realize that there is an intrinsic connection between this classical problem like this and the Rydberg blockade problem, because in Rydberg blockade we basically are trying to excite as many atoms as possible, but we cannot excite the atoms which are subject to this blockade constraint. And so indeed, it turns out that the cost function of this problem is actually equivalent to the classical cost function of this blockade Hamiltonian. And actually, this is a very important observation because it allows us to very efficiently encode this problem into our Rydberg system. So I should say that the effort to understand if quantum machines can help solve this problem faster is a big, major effort in quantum information science. But up to now, these efforts have been restricted either to analytical proofs, which actually is very difficult, or to running circuits either on the D-Wave machines, which actually don't have quantum coherence, or on machines on quantum computers at a very shallow circuit depth. So what we would like to do and what we set out to do is to try to see if we can go to basically effectively deep circuits through this very efficient co-designed encoding. And so here is how we do it in practice. So we start with the encoding where for each vertex we actually put one atom and we create the connectivity by just adjusting our blockade radius. And so at that point, what we do, we just start, kind of exciting atoms and trying to basically see how many of them we can excite subject to the Rydberg blockade constraint. And there are basically different types of pulses which we can put. So here I will focus on this, what we call a variational adiabatic algorithm, where we try to kind of go, basically, from this state to this, in some sense slowly, right? By just, adjusting our excitation pulse, Rabi frequency, and detuning to try to sort of stay adiabatic. But, still you have a lot of variational parameters. You can kind of, slow down, accelerate at different speeds. So to basically implement this entire protocol, we use closed loop optimizer. And, if you look at this closed loop optimizer, of course, you need to kind of figure out what's your scoring function, what's the thing that you want to optimize. Two things you can optimize. One is approximation ratio, basically a size of mean independent set, the size of MIS, or you can optimize the probability to basically find the actual MIS solution in a given run. And basically, with all of these tools, what we have done is then we just, threw hundreds of instances of this problem to the system and let it kind of evolve, let it work. And this is what we have done within the framework of this DARPA ONISC program. And actually, we have really learned a lot about both classical and quantum hardness. It turns out sometimes the graph of similar size, just you make small changes, it becomes much harder, orders of magnitude harder. So there are different aspects. So I could give, one big talk about this. So let me just focus on one thing, is where we try to really benchmark how this quantum machine compares to the kind of well-known general purpose classical solver called the simulated annealing. The simulated annealing is essentially a procedure where you try to classically cool to the Hamiltonian ground state by stochastically flipping the spins. In order to really kind of do a fair comparison, we kind of optimize the simulated annealing for this specific problem. And so here are some examples. So basically the curves without the data points are examples involving just classical calculation, classical simulated annealing. And these other curves with data points are our experiments running on the quantum machine. And what you see already here, so this is now approximation ratio as a function of the circuit depth. What you see is that, there are different types of instances which appear kind of in a very different way. So for example, if you look at this kind of high energy or low approximation ratio regime, all of them are sort of going in parallel. However, if you go to this kind of deeper circuits, high approximation ratio, you see that in some cases, the classical machine really gets stuck. And it gets stuck and stays there for a very long time until it kind of finally solves the problem. So, in some cases, this quantum evolution does not really see this kind of, this obstacle. So what's going on? So first off, why is classical machine get stuck? So it turns out that the instances where it gets stuck are instances where the system has a lot of approximately good solutions, but very few actual solutions. And so basically what happens is the algorithm just starts doing a random walk on this kind of hyperspace of approximately good solutions, and it really has to come very close to that to actually solve the problem. So, okay, with this understanding, what we have done now, we selected the graphs, which are particularly hard for classical machine, and then, again created, some, about 100 of these graphs, and then flew them to our quantum machine. And so actually, by the way, so it turns out that the reason, so basically, using this kind of idea, you can actually define something which is called hardness parameter. In fact, you can show that, you can show that this algorithm, scaling is exponential in this hardness parameter scales exponentially with the system size. But anyway, so what we have done then, we just picked the hardest 2% of hardest instances and threw it on our quantum problem. And here we see a very interesting behavior. So in some cases, so classically, it always kind of gets stuck. So there is this long plateau. But quantum mechanically, sometimes quantum system gets stuck, but sometimes it just solves the problem. So again, what we need to do, we need to look at many instances and look at, for example, performance versus, like, in performance is proportional to a solution versus this hardness parameter. And what we see is that in many cases, quantum machine really outperforms classical, but not in all cases. In some cases, quantum machine is actually worse than classical. So what's going on? What controls quantum hardness? Maybe not surprisingly, the quantum hardness is controlled by minimal spectral gap. So the reason why we know it is when we run the optimizer, our optimizer slows down exactly at the point where the gap is lowest, at least for instances where we can calculate the gap. And then again, what we can do, we can just plot, for example, the probability for the quantum system to find the maximum independent set as a function of this minimum gap. And what we see is that in many instances, this probability really collapses very nicely to something which is, you probably know from elementary quantum mechanics, Landau-Zinner scaling. But in some instances, there is no collapse. And actually, it turns out that the instances where there is no collapse is instances where basically our evolution is too fast, where we cannot basically go slowly enough to really spread the correlations across the entire array. So we are kind of violating the speed limit. So if equipped with this knowledge, we can actually sort out, these different instances, and so and look, for example, for average kind of scaling. So if you plot all points, what you see, classical scaling blue and quantum scaling red are the same. But actually, if you look at this deep circuit, the regime where the quantum machine really sees the entire graph, we see superlinear, nearly quadratic speed up. And we already used this knowledge to start basically kind of exploring, theoretically, why, this algorithm works like this. So this is experimental discovery. So and it turns out that actually you can, prove that, if you do things properly, you can, in these cases, you can have provable quadratic speed up. It's similar to Grover's algorithm, but I emphasize that this is done now for practical problem. So this Grover search is not actually practical. Moreover, we are looking now at instances where potentially we can have faster than quadratic speed up, and this relates to something which kind of called overlap gap property. It's actually important in computer science, and we of course are interested to scale up and explore, different types of graphs. So one example of these graphs is kind of is a general graph which does not obey this unit disk constraint. It actually turns out that you can use the so-called gadgets, basically lines of atoms, to kind of encode these general graphs into unit disk graphs with at most quadratic overhead in number of atoms. Actually, it turns out that this is actually much more general. You can encode not just maximum independent set, but you can encode this kubo, or you can actually even encode integer factoring into this kind of solutions of this problem. So the key challenge basically becomes to scale up to is to control errors. So how am I doing? 5 minutes? Okay. All right. So let me just talk a little bit about that, and that actually brings me to a different kind of architecture here. So we knew from very beginning that this encoding into ground and Rydberg state is not maybe the most optimal. So it is much better to basically utilize the hyperfine levels of the atoms, where you can basically encode qubit and it can live there, for many seconds or minutes, basically limited by a vacuum. And then in this kind of approach to implement the interactions or to implement logic gates, what you do is just use a short pulse to excite the atoms to the Rydberg state and then bring the atom down. And this is actually the idea which we developed in around 2000, kind of at the sort of when we initially thought theoretically about using Rydberg atoms for quantum computing. But actually, over the last 20 years, the road to kind of implement this approach has been a bit rocky. And the key thing was that somehow it was very hard to implement this kind of, approach with sufficiently high fidelity, in particular 2-qubit interactions, like 2-qubit logic gates. So the kind of big breakthrough was about maybe 4 years ago, and led by these two individuals, Harry Levin and Hannes Pichler, who actually developed a new type of the gate, quantum gate, which actually shows, that there is a lot of, like it's for the students, if your advisors and, grandfather advisors fail to do something, there is always an opportunity to still solve this problem. And so, but basically the physics here is that, in this gate, you just want to imprint a conditional phase on this state 1-1. Basically you would like to imprint a pi phase shift. And what Hannes and Harry figured out is that one can do it by just shining 2 pulses, which actually, create a kind of a special kind of type of dynamics on the Bloch sphere, which kind of exactly implement this pi rotation. And then we, like the following day after they came up with this idea, this was implemented in the lab, and it already resulted in a fidelity which was 97.5%, 2.5% error rate, which, is not perfect, but it sort of, we could start doing experiments with them. And so one set of the experiments we have done with the system involve developing this kind of new reconfigurable quantum architecture. So in this case, what we do, we encode the qubit into this hyperfine state, and we do this logic operations. But once the qubit is encoded in hyperfine state, what you can do, you can start moving atoms around while keeping the coherence alive. And the simple example of that is shown here. So suppose you start with atom pairs, you basically create the Bell states, and then you move the atoms around, and you still check whether this Bell coherence is still there, and what you see is that basically it's unchanged. So it gives rise to this idea of this kind of new architecture where connectivity is itself kind of a living organism. It changes during the process of the computation. And with that, we actually immediately had a lot of fun. We created some complex states. We started doing error correction. We, in particular, did experiments on topological error correction. I will talk a little bit about that. And then we also kind of developed this hybrid analog-digital kind of architecture evolution. This is the kind of stuff that Susanna talked about, which is you could use it to do, for example, things like quantum machine learning. Let me just very quickly talk about that. So the 30-second primer on quantum error correction is you would like to use redundancy. So instead of just having one logical qubit encoded in one physical qubit, you would like to use many physical qubits to encode one logical qubit. And in this case, it's shown with the basically black dots. These are kind of physical qubits. And then what you do, you need to basically do checks. You need to check if you made an error. And this is done by using these ancilla qubits. And actually, what's shown here is an example of something which is called toric code. So it's basically you can use here topology to protect the information. But you would say, well, okay, in a two-dimensional architecture, it's very hard to realize this. It's true. But what one can do, one can unfold this, and resulting here is some graph with non-local connectivity. But by using this atom moving, we can actually implement it. And the idea here is to use kind of like a movable, quantum head, if you want, and just to kind of move it around to kind of enable this non-local connectivity. So in our experiments, our quantum head in this case is connected from 8 qubits, which we move around, and these red points are quantum logic operations. And what you see here is this non-local move, then we move them around and we basically read them out to detect what's called the syndrome, error syndrome. And so basically, using this approach, in this case, we actually can encode 2 logical qubits. One is a product of basically operators going around one direction, and this another one going around another direction. In fact, not only you can encode these 2 qubits, but you can also, in this case, do error correction or error detection. One of them, you can basically, error correct to unity, while another one is not quite, So this actually is very exciting because there are many new opportunities for implementing error correction, also for exploring different modalities of quantum computation, and also doing this hybrid analog digital approach. So just real quick, we are now basically finishing, actually we almost finished generation 3 upgrades, where we have a lot of different things. We have now approaches for multi-channel, fast atom controls, important piece of engineering. And we also work on this faster detection, We also work on this kind of hardware efficient detection and correction. Maybe Danila, who is here, can talk about our effort to do networking. So here is the status. So it's actually, we're now working with over 1,000 atoms and can rearrange them. But one key thing is that as you scale the system size, you also always need to worry about the quality of quantum operations, in particular about fidelities. And this is one of the points where this neutral atom kind of lagged behind up till very recently compared to other architectures. So even with this Levin-Pichler advance, these gate errors, for example, have been below what's called threshold for this error correction. So to make error correction useful, your operations should be sufficiently high fidelity, such that if you scale the number of atoms, you actually gain. And moreover, I would say we did not fully understand where our errors were coming from, so it was a kind of like at a percent level of discrepancy. So we now have solved this problem, and the solution involved both new theoretical insight, new gate ideas, and just technological improvement, using more powerful lasers, using cold atoms. So here is the results, which I think there is an archive reference here, posted a couple of weeks ago. So we now basically, can, create these new types of gates and start benchmarking them. And actually, the result is, fairly high fidelity. But moreover, with this kind of benchmarking, we now can develop new families of protocols. So in this case, the family which we use was inspired by theoretical work by Guido Pupillo group. Instead of 2 pulses, we now use single pulse, but we do this kind of very fancy phase variation, but there are other pulses which one can create, and basically all perform quite well. I would like to emphasize here and that in this case, these operations on 10 atom pairs have been done in parallel, and actually all of these atom pairs perform very, very well. And there are no cosmic rays, I should say. So we still see small correlations, and there's very small, but certainly not as bad as what, for example, superconducting qubits. So, and with that, we can immediately scale up. So here are the operations on 60 qubits in parallel. Again, fairly high fidelity, but again, what's most important, that basically all of these gates perform in parallel and perform very well. So these are actually literally what we see in a lab. So in this case, what you see is 2 types of Bell states. And when you do imaging, you basically, one of the states, let's say 1 is bright and another 0 is dark. So in this case, what you see, there are always atom pairs, but you only see singles when you image. So here you see almost pairs. And this is actually really quite exciting developments. We now understand our errors much better. The path, I would say, to high fidelities is very clear, but even at this level, there are very, very special opportunities for starting to do experiments with error-corrected logical qubits, and doing algorithms and stuff like that. So just to very briefly mention that, as I already described, there is a second machine in town now, and that's in our company, Quera Computing. So they had a big moment last year where this machine kind of went online, so it was a little bit of hello world moment. And this is basically a system of the type that I described, but it can be now programmed through the AWS bracket, so you basically log in and, you program it in a few steps, define systems geometry, define the pulses with which you excite the atoms, and then you can analyze the results, and you can either use both Python and actually Julia-based interface. And I think what's important that it really is as the first machine operating in this kind of era of quantum discovery. It's, over 100 qubits. It's actually impossible to simulate at least directly. And I think we already are seeing some very cool new scientific results coming out. And, still we are looking for new collaborators and partners. I think I really used up my time. And I would like to thank you for your attention, but also thank the people whose blood and sweat resulted in this work, both from my group and also from Quera. Thank you very much.
Yeah, thank you for an amazing talk. Very interesting things. Are there any questions? Yes.
Yeah, I would like to ask you about the spin liquid, where we know it's characterized by long-range entanglement.
Exactly.
I mean, at the end, you show us how one can realize quantum gates and measure entanglement. Is it possible to do the same trick and look at long-range entanglement in the spin liquid that you created before?
Yes. So, yes, indeed, this is one of the things on our sort of agenda. So, in fact, in this paper, in the paper where we used this kind of atom-moving architecture, we reported the measurement of entanglement entropy. So, and one could, for example, directly pretty much apply this approach to this spin liquid realization. You can just take two copies. The way how you do it, you make two copies and basically then bring them together and do pairwise Bell measurements between atoms on a copy, and then from there you can extract entanglement entropy. And so using this approach, in principle, you can extract topological entanglement entropy. The challenge, I can tell you right away, is that this topological entanglement entropy is really not very experimentally relevant, friendly quantity, because fundamentally, the errors, any error you make in a system affect this topological and entanglement entropy in a kind of exponential way. And oftentimes, for example, if you look for topological entanglement entropy, you look for basically a constant on the top of the kind of scaling which depends on surface area of the system, but the errors affect this quantity in a kind of proportional to the volume of the system. So we believe, nevertheless, it should be possible for kind of small enough systems to make this kind of measurements and extract topological entanglement entropy, but we already know now that there are more scalable approaches to doing that. So for example, we have a paper on arXiv, which actually is a collaboration also with Susanna's group, where we use something which is called local error detection. So it's a kind of a method, it's a kind of basically renormalization group type method, which actually utilizes the ideas of error correction to identify and distinguish, for example, topological phases from trivial, from other ordering. So that, to me, that's a much more promising approach. And we believe, in fact, in addition to what is on arXiv, we have now new results. We believe that this method is like super general and super powerful, including in particular it applies to non-abelian anyons. And it would still use this kind of hybrid to do, in general, to implement this method. You prepare the state, but then you still need to do quantum logic on the top. So it would still utilize these ideas, but in a different way.
Just one A quick question. I mean, you talk about a two-level system, which is qubit. In this technology, can we also generalize it to qubit? Instead of just two, can we generalize it to qubit?
Yes, yeah. So, in principle, yes. I mean, of course, what you do there, you can start thinking about this kind of lattice surgery. I mean, more often people think about that as kind of multi-qubit interaction by just controlling things, for example. So the kind of baby version of the qubit we realized was literally like it was a specifically designed lattice with the hole in the middle. And with the hole, there is non-trivial topology. There are two degenerate states. You encode a qubit, you know. But of course, if you have few holes, you increase your Hilbert space. And you can either think about it as qubit, or you can think about this as a pair of qubits. And this distinction in this topological system is a little bit, you know, it's not always one-to-one. But the answer is yes, yeah.
And those Rydberg arrays in 1D can be mapped to these PXP models, and you see scar-like structure.
That's correct.
So, but here you are using 2D arrays, right?
Yeah.
So can you see scar-like structures in these arrays and maybe use it for an advantage to the reservoir computing that was the talk, last talk?
Yeah.
Can you use it in those?
Yeah, so this is, okay, let me just repeat the question. So basically, I mentioned it very briefly, but in kind of in one-dimensional systems, we observed something which is called many-body scars. So let me just explain what it is so that people understand. So imagine you have a piece of ice that you throw in a boiling water. So what would you expect? You expect that ice would melt, the water maybe cools a little bit. So we did similar experiment in the quantum domain, going across quantum phase transition, where instead of thermal fluctuations, you have quantum fluctuations. So we took a crystal and literally changed the parameters very rapidly to sort of go away from this crystalline state. And then what we saw is indeed crystal melted. But then if we waited a little bit longer, miraculously the crystal reappeared. And it melted again, it reappeared. So, and this is the phenomenon which is called many-body scars. So we observed it initially in one-dimensional systems, but in one of the papers, I think I mentioned in 2001, we actually showed that the scars persist in 2D systems, in particular in bipartite lattices, you know, very robust scars emerge. And moreover, what we showed is that if you start kind of driving the system, you can even stabilize scars even further. And actually, kind of our recent work in progress now shows that this phenomena often persists even if you go away from bipartite systems. So it's actually quite general property of this of systems with constraints. So these scars is really something kind of very special. And you know, these scars, I think it's actually, I would say that it's the first and so far the only real true scientific discovery made with any kind of quantum machine, quantum computer, quantum simulator. And it's actually very interesting, and I think there is a lot of potential. It's actually, there has deep, people still don't understand when these scars appear, but you know, it's clear there are some connections to things like lattice gauge theories and so on. So I think this is really a very, very exciting direction.
So you mentioned how the efficiency of the quantum optimization depends on the gap in the Hamiltonian representing the problem. So my question is, does this, like the size of this gap, does it represent the classical, like how classically difficult it is to solve the problem, like the complexity of the problem classically? For example, like a small gap would be like an NP hard or an exponentially complex problem, or are they not related at all?
Yeah, so I mean, like this, of course, your question is at the core of whether you can get quantum speed up or not. And basically, to answer this question, what, like the study which we did, which I think will appear on arXiv very, very shortly. So we basically try to analyze, so we understand, you know, what makes classical simulated annealing hard. And that's this kind of hardness parameter, that's this kind of landscape, where you sort of are stuck, before you find a good solution. So, and it turns out, you can prove mathematically for the wide class of the instances, of these hard instances, the gap, if you do things right, the gap will scale as a square root of this hardness parameter, giving rise to this, basically quadratic speed up. So it turns out that it applies to wide class algorithms, simulated annealing, quantum Monte Carlo, like parallel tempering, all of these kind of approaches. With regard to that, there is this, quadratic increase for the gap. Of course, we would like to see more than quadratic increase, and that's why we are looking for some of these more exotic instances, for example, instances which have overlap gap property. So the instances of the type that I showed do not have overlap gap property, if you know what it is, But with overlap gap, I think it's much more interesting, but it's also not clear if you can get the speed up in this case.
Thank you.
With that, I think we'll thank our speaker one more time, and then we'll break for lunch. Morris, maybe you say something about lunch. I don't know. What's the... Cheating, right? Because the spin decoy here, you like repump it and repump it and repump it and repump it. You can repump it many times, so indefinitely.
No, by my name. No, I was born in Russia, but I grew up in Israel and Israel in 2007. Right? Things that will definitely bite you, definitely eat you, but I can assure you will definitely survive. I think when Americans talk to us, when Americans visit and they talk about the danger of the species, we always remind them that more people died from gun shootings in the US per year than combined all animal attacks in Australia. No, but no, it's safe really. So I don't have an answer, basically. I think it's a bit, yeah. We haven't actually measured an hour. I think it's the knowledge of how to do it. That's what everybody says. I think that's straightforward to you as an expert.
Hello, check. Okay, welcome back everyone. Hope you all had a nice lunch. My name is Karthik. I'm a graduate student in Professor Shalev and Baltaseva's groups here at Purdue. And I'll be the moderator for this afternoon session. Our first talk in this session is by Professor Igor Aharonovich. Professor Igor Aharonovich is working on cutting-edge research into quantum sources that can generate, encode, and distribute quantum information. A professor in the School of Mathematical and Physical Sciences at UTS, Igor investigates optically active defects in solids with the aim of identifying a new generation of ultra-bright solid-state quantum emitters. His contributions to the field include the discovery of new color centers in diamond and hexagonal boron nitride, and the development of new methodologies to engineer nanophotonic devices from these materials. Professor, you have the floor.
Thank you. So thank you very much for the kind introduction and also for the invitation to visit Purdue and the Quantum Center. It's my first time here, and it's very, very impressive just to see this breadth of knowledge and expertise and facilities. So I'm grateful for that, and using the same opportunity, I would like to invite you, of course, to visit us in Australia. We are exactly 12 hours in delay. So if I'm a bit incoherent, I apologize. So we don't really have a quantum computer based on defects in solid just yet, and the talk in the next kind of 40 minutes or so is really going to be around providing you this motivation and inspiration
to look a bit more carefully into defects in solids. So our interest is to study and come up with new single photon sources based on defects, and particularly in a hexagonal boron nitride. So the main motivation stems from this vision provided by Jeff Kimball and revisited by Ronald Hansen a few years ago about the quantum internet. And so here you would like to have, or you would want to have, some sort of a memory access and then some sort of a flying qubit interface and a way to store the information and then communicate. And you can think, of course, that you would need a single photon source to do this communication in the channel. And of course, the most trivial quantum system here would be a trapped ion, or a trapped atom, as you've heard from the previous speakers. And really, indeed, with rubidium, for example, the group of Rampe realized this elementary, what we call quantum network between two distant nodes. And later on, also in diamond, people realized this NV centers entangled between three different nodes. And this is really kind of the foundation of your multi-parted quantum network based on defects in solid. And so what we are asking ourselves is, what is the most interesting and the most promising system that we can scale up to generate or to realize more than one or more than two nodes and interfacing them? So it's really important here to kind of emphasize we're not building a quantum computer per se, like you've heard before. We don't have 100 or 200 qubits entangled, but what we really want to have is towards this aspiration of having a quantum repeater, for example, where we need to generate an entangled photon source and then distribute entanglement from node to node. And so the question is, again, how we scale up and what is the kind of the most versatile solid-state quantum system. So we need a few components. So you need, of course, some sort of waveguides and phase shifters, et cetera, et cetera. And I put here just 5, but of course there are many different prerequisites before you can realize such a dream. And so you need, of course, the quantum light source. This is where our expertise, this is what our group is working mostly on. And then you, of course, want to interface this quantum light source with an array of waveguides and cavities and networks. And you need to bear in mind some sort of memory and scalable approaches and, of course, tuning and manipulation of your source. Right? So it has to be tunable either in frequency or in phase, et cetera, et cetera. And then, of course, you want to put your detectors on chip, and everything should be nanofabrication compatible. So it's quite a long list of demands, and I will show you in the next 40 minutes or so that hexagonal boron nitride is actually a very promising platform to realize all of these components. So it's a good way forward to think about using this platform. So just, I guess, because we are at the end of the day in a school for quantum, so I just wanted to revisit very briefly what is a single photon source in a way. So you can have basically two different categories of single photon sources. The first ones that were discovered many years ago, they're based on quantum dots. And this is just a detuned energy state between your valence and the conduction band. And if you localize them either geometrically or by strain or by size, you can have a single photon source being emitted. So this is your standard gallium arsenide, indium arsenide, gallium nitride quantum dots. And of course, more recently, the 2D material family, the WS2, et cetera, et cetera. A more kind of, from my point of view, a more interesting system is this, where you have an artificial atom in solid, so an artificial defect. So the most common one is your nitrogen vacancy center in diamond, where the system is isolated very deep within the bandgap. So we are talking about, let's say, 5 or 6 EV material. So diamond is one of them, hexagonal boron nitride as well is another. And you will have a ground and an excited set very deep within the gap. And when you trigger them with a sub-bandgap excitation, like this green laser here, you can then have a single photon source. And so over the last kind of 10 years or so, there were quite a few platforms that has been subject to the studies and been realized single photon sources, including here from silicon nitride, for example. So, and then to measure this, you doing a very basic interferometric measurement, and if you have basically no clicks at a specific time frame, so this is called an anti-bunching measurement. If you have no clicks here, that means you have only one photon in your system, which is the evidence of a single photon source. So you will see this kind of G2 measurement quite a bit in my slides. Okay. So why hexagonal boron nitride? So as I mentioned, we're looking after a wide bandgap material, and if you look at this diagram of different semiconductors or wide bandgap materials, you can see that, of course, diamond is here above 5 eV, gallium oxide is another one, aluminum nitride, and also HBN. Out of all these families, HBN is the only system that you can actually also exfoliate into 2D materials. Now, we in Australia like easy life. We don't have MBE reactors. We don't want to grow high purity materials. We like to exfoliate Scotch tape and $100 HBN, enough to generate a generation of PhD students. So it's a cost-benefit analysis here, and so we decided to look into HBN. So it's actually quite interesting material as well from a polariton point of view. So if you want to generate phonon polaritons, not related to quantum at all, but it's one of the best materials to generate phonon polaritons. There is a lot of literature on that. And also if you're thinking about UV quantum, so typically we actually pushing infrared, but if you for some reason want a quantum source at the UV range, then hexagonal boron nitride is the only system because you have a almost 6 eV band gap, bless you. So we looked at that. Another, of course, advantage is that because of the 2D nature, you can stack different layers on top, and there is this emerging phenomena of twistronics. And you've probably heard about the magic angle graphene, where you twist 2 graphene layers in a particular wavelength and you get superconductivity. Well, it turns out that it also applies for very deep defects within the band of HBN. So you can actually twist HBN and see that this twist angle influences the emission properties of very deep defects. This is a rather non-trivial phenomena because in principle it should only affect your band, your electronic states. So this is not our work, but I just put the references here in case somebody is interested. So all in all, this is a very kind of interesting platform, and we started to have a look into HBN, and I just want to highlight 3 works, what makes this really, really unique. So this one is actually from Purdue, from the group of Professor Shalaev and Professor Boltaseva, on really you taking an HBN flake and you just scan with an AFM tip, making these notches, and then you can generate single photon sources straight away. And if you think about it, this is quite unique, right? You don't need to do any implantation, you don't need to do patterning, you don't need to do any arrays. You deterministically generate your emitters where you want them, whenever you want them, in basically any flake. It's not really available in any other system. The other work is here from Professor Stefan Hoffman in Cambridge, and what they did is, again, people really want arrays, and so what they did is they took an ensemble of emitters inside the boron nitride, and instead of patterning it, they patterned a graphene underneath. And what graphene does for you, it creates this non-radiative recombination, so you actually turn your emission off. And so if you now put this graphene mask on top of your multicolorful HBN, you basically create an array, and again, every spot here is basically a single photon source. And the final work is from our group. This is about strain, and you can see here that you can strain HBN at room temperature and shift the emission by about 12 nanometers. This is some tens of MeV. This is the largest kind of record tuning of a quantum system at room temperature using purely strain. Okay, so you really just strain it. Because it's a 2D system, you can strain it quite a bit. Again, not possible. Any of these experiments are kind of not possible with any other normal 3D type system. So I hope I gave you enough motivation why we are interested in HBN. And so I will discuss basically 3 different topics, all related to emitters. I will talk about cryogenic spectroscopy of the most common visible centers in HBN. I will then show you some result recently on the blue emitters and on spin defects. And maybe if there is a time, I will show you some practical applications of quantum key distribution that we also did. So at this point, we kind of can grow routinely HBN in our lab. So we do it on just copper films, but you can also grow it on silicon nitride or any other material, basically. And typically, you would get this distribution of emitters around 600 nanometers. It's not really emitting at the same wavelength, but around 600 nanometers, and most of them would have this narrow line and a typical anti-bunching measurement. You can also localize them by growing on pillars. This is not strain-activated emitters. These are just emitters that are grown on pillars, and if you focus on the pillar height, your confocality is basically giving you the array. So, of course, there are emitters everywhere, but because you focus on this plane, you basically only see the array. So this is all at room temperature, and you can basically kind of set it up in a week or so and get as many single photon sources as you wish. So the question really is, well, are they good? Can we really try to do resonant excitation and generate indistinguishable photons? And this is where troubles begin. So typically, I mentioned we excite them with a green laser and do this non-resonant excitation. We look at the emission and the red. What we want to do now is to excite them resonantly. It's really to go coherently from ground to the excited state and then measure the photons to see if they're coherent or not. And so the results here are not that great. So if you work under very low power excitation, you have somehow narrow line width. This is about 1 gigahertz. So it's about 10 times broader than your natural line width. So the natural line width for HBN emitter is typically around 100 megahertz, about 3 nanoseconds. And so you can see that it's spectrally diffusing quite a bit. And of course, if you increase the power, you just basically get nothing, just noise. And if you take this individual scan, they're actually quite good, but overall, the lines are very broad. So how do you solve this problem? So again, bearing in mind that we know that it's a spectral diffusion and we know that it's a 2D material, the easiest way to do is, well, just to do some Stark shift. So if you apply a field, you can actually then stabilize the lines. So we did it. So here is your HBN capping layer, HBN with emitters and some graphene, and you put it all together. I never believe the students when they just randomly put these lines, whether the graphene is actually there or not, but let's say it is. And so what you do then is you look at the emitter and apply bias. And interestingly enough, when we found emitters and we applied bias, nothing really happened. However, when we found places where there was no emission, okay, a dark place when there was no emission, when we applied bias, we suddenly saw the luminescence appears. So, and it was very reproducible. So again, this is not electroluminescence. The green laser is always on. But when we apply bias, we suddenly see emission and off and on and off. And here's an example. So no emission. When you apply the bias, suddenly you see luminescence. And of course, it's a single photon source. So what is actually happening here? So to understand that, we took a very dense sample of emitters, very, very dense, and we recorded one confocal map with many different systems. So this is this is basically as a function of wavelengths. And you can see here many different emitters appear at different voltages. So for example, here one appears at 20 volts and then disappears. Here is one appears at about 15 volts and disappears. Here is one appears at 40 volts and disappears. We could not go above 40 volts because the device is basically fried. So 40 volts is basically the maximum. But interestingly, at the negative regime, you just have a monolithic increase in emission intensity. So this behavior indicates some sort of charge transfer or spectral or charge change. So for example, if you're going from NV minus to NV zero, or some defect from a minus charge state to a neutral charge state. So we came up with a model. This is to scale. So we have a 20 nanometer cap of our HBN, and we have a 20 nanometer HBN with emitters, and you have two different charge transition levels. And when you apply a bias, you will get the first transition level going above the Fermi level, and will become optically active. That's where the emitter turns on. And when you apply even higher voltage, then the second charge transition level will be optically active. And then the emitter will go off because this is a not emitting state. So for some defects like NV minus and NV zero, both charge states are optically active. But it doesn't have to be the case. You have some defects that are not optically active, and that is exactly what is happening here. Now, this is also why some emitters turn on at different voltages, because obviously as you closer to the interface of the capping layer, the closer you are, the lower the voltage you need to cross the level. Now, at the negative charge state, at the negative bias, you would basically create these hot electrons or hot carriers that will go over the conduction band of the HBN and will always recombine at the most favorable defect or at the most favorable charge state, and that's why we see monotonic increase in emission intensity. Now, this effect is actually quite easy to check, because if you now switch your excitation laser from green, and this is about 2.4 eV, yeah, because we have about 4.6 eV to the vacuum and about 2.3 from the conduction band, you should basically kill all your luminescence and not see any signal, and that is exactly what's happening. If you now, starting with the 532 nanometer, you find an emitter that is turning on here at minus 20 volts. If you switch from 532 to red, which is much less energetic, you basically see no emission. Okay, so why did I waste your time 5 minutes to tell you about that? Because if you look at the literature, you will see that for other defects in solid, if you remove the surrounding charges, this is done with silicon carbide, this is from David Avshalom group, and if you create a depletion layer, you can actually get a very narrow line width in your emitters. And so in our case, we don't have really a PIN junction, but under very negative bias, we kick all the charges to the edge. So we should have an emitter which is free of surrounding charges. And in principle, you should get very narrow line widths.
And so that is exactly what is happening. Even off-resonant, we already see Fourier transform limited lines. This is just limited by our spectrometer. Yeah, it's about 100 gigahertz. And if you then do resonant excitation under minus 40 volts, you see this 150 megahertz lines, which is roughly Fourier transform limited, the natural line width of HBN. And if you then reduce your voltage to 0, you basically see just noise. So a rather cumbersome way, but we still got a very narrow line with HBN that are suitable basically for further kind of quantum measurements. And in parallel, there were also two groups from Harry Atwater and from Jian Li that basically reproduced these results, also with a very similar design. Okay, so now the part where we try to integrate these emitters with some photonic media, and so we, after a few years, kind of optimize the fabrication. This is all in HBN, so we can make this, I think, beautiful 1D photonic resonators, and you can really tune the cavity mode all the way from about 400 to 800 nanometers, so exactly where we want it to be. And so then you can choose, for example, a emitter right at about 600 nanometers, and you can condense a gas and tune the mode into your emitter, and you can see this enhancement. And so this is kind of a Purcell enhancement of a single photon source in HBN. Now, I should say that here we perform all the measurements at 70 Kelvin. So we don't actually need to go to 4 Kelvin like most other sources, because the emitters in HBN are quite narrow. And so you can already see the effect of the Purcell enhancement already at about 70 Kelvin. So yeah, so this is basically now done, and the guys went really nuts with making a lot of things that are beautiful but not so useful, also not so much working. So we tried inverse design, that didn't work. The waveguide, the taper waveguide actually works, so we're now trying to couple light outside from the chip, and of course the beam splitter is also working. So now what we're trying to do is basically put an emitter here and try to do on-chip excitation and on-chip collection with those emitters. Now, here we stumbled on a very interesting problem that initially I told you how amazing HBN is because you can just exfoliate and make all these devices, but actually now this is kind of backfires because the biggest flake we can ever exfoliate was about 100 micron square, maybe 150 micron squares, and so we're really at this point limited by the material that we get to fabricate these devices. You cannot actually exfoliate larger flakes. There is no large crystal of HBN that is 3-inch wafer. So for those of you who are interested in the materials development for quantum information, this is the problem number one, is really getting large area, multi-layer HBN. Okay, so I will shift gears a little bit to talk about a more recent blue emitters. The reason why we call them blue is because they are factually blue. So I showed you before that we can grow these HBN emitters and they emit at various wavelengths, around 600, but various wavelengths. Well, it turns out that you can actually find specific flakes that have a very particular properties at the UV range. We will skip that. But if you irradiate them with an electron beam, you can actually get exactly the same emitter at exactly the same wavelength. This is 436 nanometers. And more importantly, you can scale the emission up, which means the more you irradiate, the more emitters you create. So you can see here from a single photon source all the way to an ensemble. And this is really cool because this is for the first time you can actually create the same defect deterministically and go from a single to an ensemble, and you can see that they emit exactly the same wavelength. That means that the property is already going to be quite good. There is almost no variation of spectral diffusion. Another important thing here is you don't need to anneal. So typically for most defects in solid, after you make them, you would need to anneal them to kind of relax the lattice and maybe move a vacancy nearby. These defects, you irradiate, you create them, you don't need to anneal them at all. And that's beautiful because you can create them, you can see them when you create them. So we have this system called cathodoluminescence. It's basically a fancy word to say you have a hole in your electron microscope because the electron beam goes through. Then there's a parabolic mirror that takes the light out, and we can collect the light in situ when we make the emitters. So this is the cathodoluminescence map. And so the last thing is that you can see that the intensity, the radiation dose and the intensity of the emitters is going linearly, which means that we don't have any limiting parameters diffusion-wise in the material, which means that we activate the defects that are already in the material. So we have some hypotheses on what the defects are. but let's keep it to maybe after the next coffee break. So when you do low temperature spectroscopy now, you can see that the emitters are all emitting exactly as I mentioned at the same wavelength. The spread is less than a terahertz. So for those of you who are following the literature in diamond, there's a lot of hype around, for example, silicon vacancy or germanium vacancy, these group 4 defects that are always emitting at the same range. This is actually much better by about a factor of 5. There's almost no residual strain to push these emitters around. They always emit at exactly the same wavelength. And as you would expect, when you're doing resonant excitation, you can see straight away lines of around 2 gigahertz. As you can see here, in fact, every single line here is basically a coherent Fourier transform limited line, and just averaged over a number of scans, you get 2 gigahertz envelope. This is without any repumping, without any devices. This is just purely exfoliated HBN that we irradiated with the electron microscope, put in the cryostat and measured. And when you're doing resonant G2 function, you would see this, these waves here. These are Rabi oscillations, and this tells you that the system is highly coherent. And so as we were trying to do two-photon interference with these defects, we read about it on arXiv, and that's kind of very common these days. When you do an experiment, you read about it on arXiv. This is from the group of Deltail, who actually were the first kind of to engineer these defects on demand. And so they actually measured two-photon interference from these defects already. So tremendous progress in the span of about a year and a half to basically engineer this new type of defects emit exactly at the same wavelengths to then generate indistinguishable photons. And so now really is to go and integrate them with cavities. So we have some preliminary data. This is very same SEM image. So this is at the blue. So we have about 11,000 Q. I just want to emphasize that making cavities in the blue is hard. So the cavity engineering kind of scales non-linearly with the wavelength. So at 1.5 micron, it's easy. At 600, it's doable. At 400, it's very hard because the absorption and other losses. So I think the highest ever photonic crystal cavity, 1D photonic crystal cavity, was made in gallium nitride at this wavelength, and it was about 4,000. So we are actually not that far away, and I think we can do a bit better. So this is just the mode. We can then go take the same cavity and put it in SEM and irradiate right in the middle and create these defects exactly in the middle. So here is an example of the emitter at room temperature and at 5 Kelvin. And then you can actually tune it into the resonance of the mode. And you see this is off resonance, and on resonance you'll get this enhancement. So the tuning is very crude. It's done by laser power. We could not really condense gas in that time, and any fields are basically not shifting these emitters. They're quite stable. And designing the cavity mode down to basically a nanometer is still quite challenging. So we hit it close, but not close enough. So tuning is still a challenge, but nevertheless, you can already see that just by power, you kind of heat the sample locally, or maybe create some local charge changes, and you can kind of couple this emitter to the cavity mode. So a very interesting system. The biggest issue is the wavelength, not so convenient to work with, but nevertheless a great single photon source. We don't know anything about the spin just yet. So for all of those that have an ODMR set up on standby, I can give you the sample, go and measure. Okay, so the last bit is going to be about spin defects in HBN, and this was predominantly motivated by quantum sensing applications. For those of you who are following the NV literature, there is of course all this hype about room temperature quantum sensors. People from many different groups engineered them, and Lockheed Martin even built one for their submarines. Many different achievements. Now this is all based on the very basic spin physics. I'll just do one slide, introduction to NV Center. Basically you have a nitrogen vacancy in diamond, and there is a splitting in the ground state, which is about 3 gigahertz or 2.8 gigahertz, which is controlled with a microwave. And so the idea is that when you excite with a green laser, you can excite either from 0 or plus minus 1, and then it will decay either to the 0 or through the metastable state, which is a long-lived state. And so because of that, when you swipe your microwave, you will see a deepened luminescence just because this transition takes much longer than the direct emission. And of course, you can then apply magnetic field and split these levels, and then your emission will be then your signal will be split. And so this is what's called optically detecting magnetic resonance, or ODMR, or optical EPR. Now, for the community that works in single photon sources, the first question is always, well, does your source have a spin? And typically, if you say no, the people will turn around and walk away, which do not take any offense on that, that's fine. But we were looking for spin defects in HBN, and so the story was, in 2018, I was sent by the management of the university to Brazil, to University of Madigueira in Belo Horizonte. And that institution specializes in neutron irradiation. That's predominantly the thing that they do, in neutron irradiation and EPR. And I brought them an HBN crystal and I told them, please irradiate with neutrons. And they said, why? Neutron of HBN was done from 1975. Indeed, I will show, there's a reference here. And so I said, just do it. And so we irradiated with neutron. The crystal becomes pink. Those of you who don't have money for pink diamond, take an HBN, irradiate with neutrons, you'll get pink HBN, looks beautiful. And so indeed, you see this beautiful EPR spectra. This is spin half system, known from 1975. That's the oldest EPR signature of a solid state defect, I think, overall. Perhaps the Ruby is maybe a year or so older. And so nothing new, but if you irradiate for 16 hours, and I still don't know if the student did 16 hours because it was a weekend or just forgot, but whatever, we got it. So for 16 hours, you see these new peaks appear. And when we took the sample back to Sydney and looked at optically, we saw these emission lines appear as well. Now this peak is asymmetric, so it means that it's a high spin system, 1 or 3/2 probably, not like this heartbeat type, which is a spin half. And so back then it was clear that this should yield an ODMR signature. And so over the next year, I was just looking for people to help with ODMR because we are not an expert. We were not experts back then. And so indeed, with the collaboration of Vladimir Dyakonov from Würzburg, they took exactly that same sample. This is again the same emission line. And when you apply magnetic field, you apply microwave, you would see at 3.5 gigahertz this deepened luminescence. And when you apply field, this peak would split like a perfect spin 1 system. Now, I should say that we were scanning this basically blindly. So you just start and you just scan until your setup allows you, and you hope, or you pray. Now, because you have ODMR and you have these small peaks, this is actually hyperfine, and you can already straight away know what the defect is. And this is the beauty of ODMR or EPR systems, that EPR can tell you directly what the emitter is. That's why it's very important to create them as an ensemble so that you can do EPR on them. And so this is a high resolution EPR measurement, so you can see the number of peaks corresponding to the nitrogen hyperfine. You should have exactly 7 peaks as you see here. And again, if it was, for example, a nitrogen vacancy, you would expect to see many more lines. And so this is kind of an unambiguous, well, not kind of, this is an unambiguous proof that you're actually working with a boron vacancy negatively charged in HBM. Now, since it's just a missing boron, that means that it's very easy to engineer. And so straight away, quite a few groups just exfoliated flakes and irradiate them with ions, with lasers, with basically everything that people had on hand. And you can see this emission forming exactly the same region. Initially, we tried different ions. Of course, intuitively, it's very clear that the smaller the ion, the better it is, because you don't want to destroy all the lattice. You just want to knock off one boron. And so then we can kind of combine it with our engineering capabilities of HBN. So we made bullseye structures. There is no cavity here. This is just a lens, basically, like a planar lens. And we can pattern quite a few of those. And you can see a much better ODMR signature straight away. And of course, much better signal to noise ratio in terms of your optical luminescence. We were trying to go to singles. I would say kind of unsuccessfully. You can try to put this boron nitrogen between silver cubes and a metallic structure. I think that actually the results from the group in Purdue here are much better. The Shalaev and Poltoseva, this and Tong Li, they showed much better enhancement. And as I mentioned here, the group of Tong Li also demonstrated nuclear spin polarization straight away, and also very high contrast. I think this is probably the largest contrast of any solid state system you can have in ODMR, so it's over 50%. So all this is great because you can now have a 2D material-like system for quantum sensing at room temperature. And so indeed, people started to look at this kind of quantum microscopy, so you can put some sort of a magnetic material just on top and image the magnetization. So these are two examples of magnetization switch where you just switch the magnetization direction just with an ensemble of boron vacancies. You just take an HBN, make VBs, put your material on top, and image. You can also image currents in graphene and many other different things. So people always say, well, is it better than the NV? No, it is not, but it is comparable. So it really depends on what you want to do and how do you want to do it. For planar wide field microscopy, it is actually quite appealing and quite competitive just because of the ease of making the samples. Of course, we don't have single VB boron vacancy yet, so that is something that the NV is still much, much better. Now, of course, we're also limited by this thing, which is the nuclear spin, and in boron nitride, we are in a very bad position because both boron and nitrogen are not spin zero systems. So that is a problem that we don't know how to address, except of like, I don't know, find a different host. How am I doing with time? Okay. So I do want then in 5 minutes to kind of show you one application, since we are talking about quantum, and so far I just kind of walked you in this HBN La La Land. And the application that most people kind of start with in the quantum realm is QKD. There is a big debate whether QKD is useful or not in the long term, but the reality is that this is kind of the most commercialized system so far in terms of quantum technologies. It's also quite cute and educational wise, like for a proof of principle wise, very important because it shows you that you can actually use the quantum principles to transfer information securely. So the way it works in a very naive way is you have a single photon source and you then randomly select a polarization, transmit the information, and then you communicate over the public channel what polarization state you use, but not the actual state of but not the actual signal. Yeah, so you just select randomly the polarization, and then you compare which polarization state you used, and then you generate the key. So this is a very crude way to do a secure information transfer, and there are many companies that are doing it commercially. There's two here, and they do it based either on attenuated lasers or on down-converted sources, but single photon sources are always a good promise for that, but never really gotten anywhere, predominantly because there was never a good single photon source that you can actually use reliably. And so we, as most of the people that work on quantum, we package the source into a small box. So this is Helen, who carries the box around. You will know that we intentionally designed it so that only half the box is occupied. This is, I think, probably the world's smallest confocal microscope to date. The idea is that we can put here either a second system or all the lasers and the detectors and the electronics. So far, it's just empty. And at the end of here at the source point, we made an HBN, but not just an HBN. We incorporated it with a solid immersion lens. And what the solid immersion lens gives is just a factor of 10, basically, in emission. And it's all fiber integrated, so you can, you can see that the collection is done with the fiber, so this box is then fiber coupled to whatever that you want to do. So the performance of the source is quite good. It's stable over basically, I mean, we measured 6 hours here, but we used the same source from 2021, so it's over 2 years almost now. It emits at 600, but we can have any other source as well, so different sources. And the interesting part is we only use sources that have a very pure emission. So this is G2 under 0.1, so 0.07 in our case. And with these sources, we can now do quantum key distribution. So we then fiber couple that box. We do the demonstration at room temperature outside the lab in an office. So it's basically compatible with the environment. So you send the information from ALICE. There is a polarizer and a selected polarization using EOM, and then the Bob collects it. Now the sad part of QKD is that I don't have any kind of data to show, except you need to believe me that this is the original image, the encrypted image, and the decrypted image. So this is Bluey. For those of you who have kids, that's the Australian cartoon for kids, quite famous actually. If you haven't seen it, I highly recommend. It's better than South Park, I think. Okay, so how are we doing with QKD with HBN? This is very important to kind of benchmark. So I put here a few examples of different sources. This is really based only on single photon sources. There is no point of mixing technologies with attenuated laser, etc., because different techs have different problems and different advantages. So for the single photon sources only, first of all, we are working at room temperature, so not cryogenics. We work at around 600 nanometers, but also 700 and 800 we already demonstrated. The source purity is over 99%, and we only can go to 1 megahertz. Now, this is problematic because our sources are actually very bright. So we can measure up to 500 kilohertz under 20 megahertz excitation. So we're working at pulse. But the problem is that when you work at this visible range, there is no suitable EOMs to drive your system because you need to synchronize the EOMs. There's just not fast enough EOMs that are currently available on the market. And so as a result, you basically have to go and reduce your clock rate down to about 1 megahertz. So when you reduce your clock to about 1 megahertz, you basically have about 15 kilohertz count rate, which is your communication rate. Now, then it's really important to decide how pure is your QKD because you can, in principle, just send the signal ignoring all the noise and all the attacks. But it's very important to actually implement all the defense protocols like sifting and et cetera, So when you implement everything, we're going back to kind of a laughable count rate of about 0.25 kilohertz, but this is an absolutely secure communication. And we protected basically against most of the kind of conventional attacks. Of course, we can not do this and then get a higher rate. So the point here is that the HBN sources are now kind of ready to be deployed for proper QKD systems. The biggest bottleneck is the EOMs, and we are currently trying to convince a few of the big manufacturers to engineer an EOM for us. Okay, so just to summarize, I showed you new coherent emitters, which are the blue spectral range. I showed you some nice results on the spin defects and imaging, and also on our kind of pathway forward to engineer these scalable photonic crystals and cavities to build up this on-chip platform. And of course, nothing would have been possible without the great team. Before COVID, we had 11 countries, 11 nationalities in the group. After COVID, shrinking a little bit, but nonetheless, quite a good gang. I think Noah, who may not be here, is working nearby in Chicago as a postdoc. And the rest are still with us. And also, just one slide on those who work on HBN. We're going to have a small workshop in June. If anybody is interested, let me know. And of course, thank you for your attention.
Thank you, Professor, for the very exciting talk. Any questions from the audience?
Yeah, thank you for the. Thank you for the talk. So you're using HBN as your single photon source. Can you talk about the difference between using that and say like a different TMD? Is it just the different wavelength emission?
So HBN, the difference between TMDCs and the HBN is the operation. So the HBN operates at room temperature. Most of the TMDCs require cryogenic temperatures. In the WSC2 TMDCs, it's only strain activated, so you really need them to put on something which is not planar, which is a problem. And MOS2, you can engineer them. So it can be planar. The MOS2 and WSC2, they always emit at 1 wavelength, and typically the emission is very, very dim. So the brightness is an order and a half less than the HBN.
More questions? More questions from the audience?
Nice talk. Thank you very much, Igor. I guess 2 questions, if I may. One is these neutron irradiated defects. You mentioned your boron nitride has about 20% boron 10 naturally, 80% boron 11. I think boron 10 is the one that has a much larger neutron absorption cross-section. So are those VB minus defect primarily at location boron 10? Do you know?
We don't know, but because there are boron vacancies, we presume that the neutron will kick out the boron, not the nitrogen.
So the
interaction is better with the boron, yes.
With boron 10 particularly?
Yes, yes.
Okay.
We think.
So in other words, if you had a enriched boron 11 BN, I don't know if you try, it will not work so
so well?
Actually, there is a work from the French group with Jim Edgar. They did B11 and B10 doping, controlled HB11 and HB10. You can generate boron vacancies in both crystals.
By neutron method?
Yeah.
Okay. Another question is, when you create this electron beam induced effects, maybe you showed us, I missed, you showed some cryogenics, but these emitters work all the way at room temperature? And what is the structure, do you know the structure of these defects?
These ones. These ones? Yes.
Yes.
Yeah, so we think, we don't know for a fact, but we think it's a split nitrogen. Split nitrogen means that you have either a missing nitrogen and then two nitrogens, one on top, one at the bottom. So like that. And the flake of the HBN is here. Do I have any piece of paper? Can I work for me? So if this is your HBN film, you'll have one atom hanging above, one below. It's called a split configuration. And the split nitrogen, we're not sure if it's nitrogen or carbon, but it's a split configuration. With the configuration, we're very certain, and we know that because of the Stark shift. So if you put electric field on these defects, the behavior you would see horizontally versus the behavior you would see vertically is very different. And that tells you the orbitals of the defect. And so when you do that, in this case, you get a quadratic behavior. In this case, you get linear, in this case you get quadratic, in this case you get linear, and that's why we know it's a split type behavior.
Is that data at room temperature?
Sorry?
Is that result at room temperature?
No. This is room temperature, yes. The Stark shift is cryogenic.
Thank you.
More questions?
Thank you again, Igor. On the topic of the blue emitters, is the 2 gigahertz line width that you measure at cryogenic temperature, is that homogeneous or inhomogeneously broadened? And how far is that from lifetime limited?
I think it's inhomogeneous. I think the natural line width should be around 200 megahertz or so. So we are about 10 times away. But I think it's because of this spectral diffusion. Every line here, every individual scan is a homogeneous FT limited.
Right. Sure.
Any other questions from the audience? Okay, let's thank our speaker one more time. Our next speaker is Akshay Murthy. Akshay is an associate scientist and deputy head of the Qubits and Materials Department in the SQMS division at Fermilab. He coordinates the materials characterization efforts across the SQMS Center. These efforts help inform future pathways for systematically improving coherence times in superconducting qubits. His group uses a variety of chemical and structural characterization techniques such as electron microscopy, time of flight secondary ion, mass spectrometry, atomic force microscopy, and X-ray photoelectron spectroscopy to identify sources of loss and decoherence. He previously obtained his PhD in material science and engineering at Northwestern University in 2020. The floor is yours.
All right, thank you. Can everyone hear me? Okay, perfect. So my name is Akshay Murthy. Thank you for the introduction. Thank you for the organizers for having me. Thank you for Travis and the QSC team for having us. So my name is Akshay Murthy. We'll be talking today about the advancements in superconducting quantum hardware guided by material science. I'm the deputy head of the Qubits and Materials Department, the SQMS division there. So before we get started, before we get drill down into the materials, I think it's worthwhile to spend a little bit of time in terms of the high level discussing qubits, discussing the theory behind them, to get a little bit of a good perspective in terms of when we actually discuss these systems. So at a high level, in terms of what we're looking at in terms of a qubit, there's a couple of main requirements that we need. For instance, we need to have a quantum two-level system, so these are indistinguishable states. We need to be able to create these arbitrary states, so for instance, zeros and ones. Additionally, we want to be able to measure these quantum states through various hardware, as well as being able to couple multiple qubits and then have a scalable architecture. So when we have all 5 of these, then we can actually start to perform very interesting quantum technology. So in terms of this, there have been a number of platforms that have been identified for this purpose. These include things like superconducting circuits, quantum dots, color centers, some of which have just been discussed. We also have trapped ions, neutral ion atoms, as well as topologically protected systems, which is something that's been doing here at QSC. And for today's talk, I'll be focusing primarily on superconducting circuits. So in terms of superconducting circuits, just to provide what we're looking at, these typically consist of metal thin films, such as aluminum, tantalum, niobium, that are patterned onto a substrate such as silicon or sapphire, seen here. These are typically done through techniques such as photolithography or electron beam lithography, so they're very amenable with your traditional silicon integrated processing techniques. Here's a couple of images. So here you can see an optical image of a circuit provided by Rigetti Computing. So this is a startup company that focuses on superconducting qubit technology, as well as electron microscopy image as well. Now, what makes this technique so valuable, or what makes these qubits so valuable, is that again, they're one of the more mature platforms, as well as offering the ability to be transitioned readily into an industry-ready platform. Now, it can also be considered, in terms of these qubits, we can also try to look at them from a circuit model to understand exactly how they work, how they function. So we can start with is the circuit model seen here, where we have a LC circuit. So we have a linear inductor in series with the capacitor. If we then take the charge and the flux coordinates as operators, and we can get a Hamiltonian that's represented here, where we have the charging energy as well as the inductor energy. We can now simplify this to this equation seen here, where A dagger A represents the annihilation and creation of particular states, and through that we get the energy landscape seen here, where we have what is known as a quantum harmonic oscillator, or these states seen here. Now the issue is, if we're trying to do any sort of quantum computation with this, even though this is a well understood system and we're able to interrogate from various states, because it's linear, the microwave radiation, the microwave frequency that we've used in order to excite from 0 to 1 will also excite from 1 to 2 and 2 to 3 and so on. So there's no way to individually interrogate particular states. So we need to go one step further. Particularly, we need to add a nonlinear element. So here we add a Josephson junction, and it says, which has this equation seen here, and it adds a sinusoidal term to the equation, and as a result, we end up with this new energy landscape seen here, where the computational subspace is defined as follows, 0 to 1, and you can see how by adding this nonlinear term, we have a difference in terms of energy spacing. So now we can individually interrogate this system. Now, while this is great and all, the challenge with superconducting circuits is that although we're able to place the information in various states, it does not remain there indefinitely. Rather, over time, due to sources of noise, such as that's seen here, it actually leads to what's known as decoherence, or loss of information. These sources of noise can be internal, so they can be the materials, the components that we're actually dealing with, or they can actually be external, such as stray radiation. But nonetheless, they can lead to things like energy relaxation, so that's T1. And what that means is that if you have a state, a quantum state, here, this eventually decays to a ground state. And we can see here, in terms of an actual measurement, if we have it in the one state, over a period of 85 microseconds, we see that it actually decays. So this is very problematic, because that means that we know we have a finite amount of time over which we can actually process, manipulate, and do anything interesting with this information. There's also dephasing. This is the idea that once we place information in a particular state seen here, where we've applied a phase, over time this is an incoherent, and what we find is that this also decays and leads to an incoherent mix of 0 and 1. So how do we address this? Because the key challenge with superconducting qubits is the ability to increase this coherence time. Well, there's a couple of different methodologies. One is the ability to simply reduce the noise sources. And actually I'm seeing here there's a I say at the top left corner, there's a bit of an issue here. Is there a way we can map this go away? At the top left, it says. Oh, okay. Okay. All right. So there's a couple different ways that we can. If I unshare it, will it work? Because it is blocking all the titles. Yeah. No, I mean the. No, it's fine on here. Oh, there we go. Okay, thank you. All right, so there's a couple different ways that we can actually protect from noise. One is to actually reduce these noise sources through what's known as materials fabrication improvements or through electromagnetic environmental engineering. So this is something at SQMS we've been working on quite heavily, and this is what I'll be primarily talking about today's talk. Additional things we can do are introduce intrinsic noise protection. So this is the idea of manipulating the Hamiltonian. So I showed what the Hamiltonian looks like for the transmon qubit that we're dealing with, but we can modify it in particular ways in order to make it more insensitive to noise. So there's many groups that are working on this as well. And then finally, there's the idea of error correction. So this is the ability to detect and correct error. It can be done feedback-based, or it can be in an autonomous fashion. But for today's talk, I'll be focusing primarily on the identifying noise sources and being able to reduce them. So for today, I'll be primarily discussing the idea of using materials and fabrication improvements to do so. But because we are heavily working on environmental engineering, I wanted to flash a quick slide in terms of how we're thinking about this. Because ultimately, improvements in terms of the environment engineering combined with the actual improvements on the fabrication side will have to work hand in hand in order to get a scalable qubit. So on the environmental engineering, what we're thinking about is the idea of using a 3D qubit platform. So here we leverage the fact that niobium superconducting cavities, such as the one seen here, have extraordinary T1 lifetimes on the order of seconds. So for instance, on qubits, we have lifetimes in the order of, superconducting qubits, we have in the order of lifetime of 60, 100 microseconds, if not a little bit higher. But these are, if not 4 orders of magnitude higher. So what we do is we then to couple these transmon qubits with these with the cavities, place them by placing them inside in the region of high electric field, and then we can either use the transmon itself to store the quantum information and then drive using the cavity, or we can do the reverse, where we store the quantum information within the cavity itself and then use the transmon for driving and readout. So through this way, we're able to really connect and leverage the long lifetimes associated with 3D cavities with the nonlinear capabilities of the transmon to get lifetimes that are now approaching millisecond values. Okay, so back again to the main focus of the talk, and that's the idea of what causes quantum decoherence in superconducting qubit systems. Well, a large part of it is just the materials itself. So one of these main things is amorphous materials. Now the issue with amorphous materials is that although we can want them, they're largely non-avoidable. Rather, they're very prevalent throughout our entire architecture. For instance, the elemental superconductors that we're dealing with, niobium, aluminum, tantalum, the moment we take them out of vacuum, place them in ambient conditions, they oxidize immediately. These oxides are highly amorphous and can lead to noise even at low temperatures. Additionally, we have things like interface. These include things like grain boundaries or the interface between the metal thin film and the underlying substrate, which can lead to scattering of charge carriers. We also have things like impurities, whether they're precipitates or interstitial atoms, which impact the underlying superconductivity properties of the system. So in general, achieving operation of superconducting qubits really requires a detailed understanding of the inherent materials that are present in the system. So what we do is we've taken high-quality superconducting qubits produced by Rigetti Computing. So these are state-of-the-art in terms of coherence times, they're multi-qubit systems, and we evaluate them with a wide variety of different techniques, because what we really want to do is get a comprehensive understanding of the particular defects that are present in our sample, how many are present, where they are, in order to get a much more better sort of roadmap in terms of how we want to proceed in terms of improving systems. So these include a wide variety of different superconducting techniques, such as those seen here, as well as structural and chemical techniques. So these include things like electron microscopy, X-ray techniques, atomic probe tomography, time-of-flight secondary ion mass spectrometry, as well as some other additional techniques listed here. So today I'll be talking about how we leverage many of these techniques in order to get a comprehensive understanding of our systems. So first I'll discuss by talking about the surface oxide. So surface oxide is something that has been studied in niobium quite heavily over the last few years, and it's been very clear at this point that simply having the presence of this oxide leads to a significant deleterious impact in terms of performance of these systems. So what we wanted to understand is, one, why does the surface oxide amorphous, which leads to the issue, and two, exactly how does it impact performance in terms of if there's any way that we can engineer it or improve it moving forward. So the way that we did this was we sectioned thin lamella from superconducting qubits. So we took a superconducting circuit, we sectioned it using an ion beam, and here we see a cross-sectional image where we see the niobium thin film on the underlying silicon substrate with various interfaces labeled. We then used an advanced electron microscopy technique known as scanning diffraction, where we raster the electron beam as a function of position across the entire sample in order to capture the diffraction pattern at each position. This allows us to get rich chemical and structural information with sub-nanometer resolution and allows us to isolate particular defects that are inherent to these samples. So first, here we can see a chemical map of our structure. We see the niobium oxide on the niobium. Kind of see that. I think the color scheme isn't the greatest right now, but you can kind of see how it's present there. We then captured electron diffraction patterns from both the oxide as well as the niobium. So here we can see from the niobium oxide, and here we see the niobium. And what we find is that the niobium has a 6-fold symmetry, which is characteristic of the zone axis along which we're probing, whereas the niobium oxide, we find is it has a ring characteristic diffraction pattern. What this means is that it's amorphous, whereas for the niobium, we see a crystal pattern. We can take this one step further by selectively filtering signal from this ring to get this map seen here, where the brighter blue is representative of the oxide that I was just referring to, whereas the underlying purple is the niobium metal. So by doing this, we were able to actually see what this oxide looks like, which would be extraordinarily difficult with other techniques. For instance, if we looked at it here, it's not clear where the oxide ends and where the niobium starts, but here with nanometer level resolution, we're actually able to disentangle this. And we find it's roughly 5 nanometers in terms of thickness, but it's not uniform, but rather it goes up and down. For instance, here, it exhibits a thickness around 10 nanometers or so. So it's very undulated and very extended throughout. Okay. So now that we know this is amorphous, however, that it requires advanced electron diffraction techniques in order to be able to detect defects. For instance, if let's say we had a crystalline material such as that seen here. In this case, it's very easy to be able to pinpoint what defects you have, where they are, and how many you have. For instance, if this structure represents different atoms, here we can see a very ordered region, but wherever these circles are seen here, we have something missing. Rather, we have a single atom missing here, so it's a vacancy. Here we have and then here we have a different atom in that location, so we have a substitutional defect. But in the case of amorphous materials, because there's no long-range order, it's impossible to tell just by looking at an image whether you have a defect there or whether that's just the characteristic structure. So it requires different techniques. And one of these techniques that's useful for this is what's known as fluctuational electron microscopy. So fluctuational electron microscopy is sensitive to medium range order in disordered materials. What does this mean? Well, in the case of a disordered material, even though it doesn't have a long range order, what makes it useful, what's interesting is that in many cases they tend to have some level of medium range order, meaning on the order of 1 to 2 to 3 nanometers, there's some level of some concentration of oxygen, some concentration of carbon, some concentration of niobium that are present within that particular volume. So what you can do is you can take that level of information, compare it to a neighboring region, compare it to a neighbor region to get a qualitative understanding of how defects are present throughout. And this technique's perfect for that because what it allows for is by using a probe size electron beam that's on the order of this ordering, so on the order of 1 to 2 nanometers, we're actually able to make it much more sensitive on this length scale. So namely what we do is we take diffraction patterns here, we then convert down to a radial distribution function, and we're then convert and are able to get a radial distribution function. So a radial distribution function is the probability to find specific atomic pairs as a function of pair separation. So what that means is that you can see that here where each of these different peaks corresponds to a particular bond in the underlying lattice that's seen here. So by taking a radial distribution function for each of the different, in each location within a single sample, you're able to understand exactly how much you have variations, where you have in terms of the sample, and then go from there. So in practice, what this involves is, here we have our sample again, we've captured a diffraction pattern, and we've converted to these radial distribution profiles seen here. So within this, there's a ton of information that's encoded. For instance, the peak position or the peak center corresponds to the number of bonds for a particular configuration that's present there. The intensity or the height of this peak corresponds to, the intensity corresponds to the number of bonds. The peak center corresponds to the bond distance. And the peak width corresponds to the level of disorder. So in practice, here we've seen a peak that corresponds to the niobium-oxygen bond. If the niobium-oxygen bond was very well ordered, we would see a sharp peak around 1.7 angstroms. Instead, what we see is breadth here. We see that this peak extends over a few sub-angstrom regions seen here. So what we can do is, by being able to map the peak width as a function of position, we can actually tell how ordered or disordered the particular sample is with this level of resolution. So here we've done that. Here this map corresponds to the peak full width half maximum of the radial distribution profile taken across the entire oxide. And here we can see that the light blue regions correspond to where we have a lot of disorder. So in essence, we've now been able to exactly map where the oxide is the most disordered in our sample. We then do the same thing by also plotting the peak amplitude, and similarly, the peak center. And interestingly, the same regions that have the most disorder in the sample are the ones that have the lowest peak amplitude and the largest peak center for the niobium-oxygen bond. So what that tells us is that the presence of oxygen vacancies in our niobium oxide lead to a disordered oxide forming in this structure. And that's important to know because if there's been some calculations that show that the presence of oxygen vacancies in our structure lead to magnetic moments. So these magnetic moments introduce noise in our system, and as such emphasize the need to, in order to address them and move them in forward. Okay. So another area we want to look at is the niobium film itself. So to this, we use the combination of electron microscopy, which I just discussed, as well as time-of-flight secondary ion mass spectrometry. So time-of-flight, or so TOF-SIMS, involves the use of a high-energy ion beam that interacts with the sample and provides you with the parts per million level understanding of various impurities in our sample, such as oxygen, carbon, hydrogen. And this is all done with spatial resolution on the order of less than 100 nanometers. So again, what we're after here is we want to understand if there's any sort of precipitates, any sort of additional species, impurities that can be leading to an impact on the superconducting properties of the system. So here we've mapped the different impurity levels of oxygen, hydrogen, and carbon for the 2D qubits, so that's seen in black, as a function of depth. So 0 represents this very surface going into the film, so you can see how at each of the very surfaces we have a lot of impurities, but that decays as we move forward. We've also compared it with bulk niobium cavities seen here. The reason we've done this is because at Fermilab we have a very good understanding of the impact that particular impurities such as carbon, hydrogen, oxygen have on the performance of these systems. And we want to see if the concentrations of these impurities are similar, if not similar to these as well, because it gives us a pathway in order to understand them further. And we find is that compared to the bulk niobium of the cavities, in the case of these 2D qubits, there's a larger or similar impurity concentration close to the surface, which means that the same set of insights that we've already developed for the bulk niobium cavity are also relevant in this case as well. One in particular is the idea of niobium hydrides. So in the case of, if we take a look at a phase diagram of the niobium hydrogen, we find is that at room temperature, hydrogen exists in interstitial positions of niobium and it's entirely dissolved. But the moment you start cooling down to low temperatures, there's new phases that form. And rather the hydrogen finds its space into particular locations in the niobium crystal structure. To see how in practice, here we've taken an atomic force microscopy surface image at both room temperature and down to 150 Kelvin. And we find something interesting, is by cooling it down, we see that these new precipitates tend to form. See this? It's the exact same region we've seen that they form. We then warm up and they entirely disappear. And in fact, if we can go one step further, we can also take a diffraction pattern from these locations and find that they correspond again to the niobium hydride. This is important because the niobium hydride is non-superconducting. So by having these non-superconducting precipitates that exist within our superconducting lattice, that can limit the quality factors at high fields, but also have some sort of impact in terms of the quantum performance, in terms of performance in quantum, in these superconducting qubits as well. So the question here was, do they also appear in superconducting qubits? And that's something we really sought to understand because based on our preliminary analysis of looking at the hydrogen levels in terms of these films, we see that they're very similar, if not higher. And in fact, they do appear. Here we can see an atomic force microscopy image taken at room temperature versus 150 Kelvin for a niobium superconducting qubit, and you see that these new features tend to appear when cooled down. In fact, you can see them here as well. So it's very clear that by cooling them down, once again they appear, and the moment you warm back up, they again disappear. To further confirm that this is indeed corresponds to these new hydrides, we could take the same sample. Here is a diffraction pattern taken of niobium. We cool down, and once again we see that these new peaks tend to appear. Further, we can actually map these. So we take the signal associated with these hydrides, and we find that they're on the order of, you can see here, so these bright spots in the black lattice correspond to these hydrides, so they tend to be on the order of 5 to 10 nanometers. So now we're investigating actively in terms of trying to see whether they do indeed impact the performance. The last thing we wanted to look at was how are they forming, what's the mechanism through which the hydrogen is being introduced into the niobium, and is there anything we can do in order to prevent these from occurring in the future? So what we did was we took two different samples. One, we took a niobium thin film immediately after it was deposited and took a look at the impurity concentration of the oxygen, hydrogen, and carbon. So that's seen in the black curve seen here. We then repeated this for the pattern device. So this has gone through the entire lithography process. And we find, and so that's something that looks like this. And in this case, we find that all of these impurities concentrations are significantly higher after this process was completed. You can see here. And as such, it becomes clear that the wet etchants we're using actually tend to introduce the hydrogen, which can lead to these non-superconducting phase. So as the active work right now is trying to use different etchants, the ones that don't necessarily contain as much hydrogen in an effort to reduce this moving forward. Okay, so last two I will fly by, and then I will talk about how these results are actually been quite impactful in terms of leading to the state-of-the-art performance in terms of superconducting qubits. So similarly, we did this sort of analysis on the interface between the niobium film and the underlying substrate. In that case, we found that there was an alloyed region that occurs. This is on the order of 5 nanometers. Let's click through it. And this alloyed region likely also introduces magnetic impurities, and something that we need to consider as well. And then finally, we also looked at the Josephson junction. So the Josephson junction, once again, is a nonlinear component that we use in order to be able to interrogate individual states, particularly. And in this case, we found something interesting, is that when we image the Josephson junction, so that's seen here, so this is one lead, and this is the other lead, and then you have a connection here. In this case, we find that there's actually a fabrication defect that was occurring seen here. So this was leading to the formation of presence of an additional capacitance to the Josephson junction and leading to a variation as a function of different devices on particular chips. So by being able to image this, being able to identify that its presence, We were then able to modify the underlying fabrication in order to improve the performance moving forward. Okay, so then the important thing is now that we've done this analysis, now that we know the types of defects that are present, can we use these findings to systematically drive and improve qubit coherence on the level of hundreds of microseconds, if not much higher? So the very first thing, again, that we focused on was niobium surface oxide. And this is because niobium surface oxide is known to lead to information loss. For instance, if we take a niobium superconducting cavity and we take the quality factor, we see this, or we see the, we measure this blue curve seen here. So it's on the order of 10 to the 9 in the quantum regime. We then dissolve the oxide, completely remove it, and do the same measurement on the exact same cavity. We see an order of magnitude improvement in terms of performance. And this now leads to this 10 to the 10 quality factor in terms of oscillation of these electrons. Similarly, there's been some studies since then where out of Berkeley, whereby measured by removing the oxide of different 2D resonators, seen here, they're able to significantly decrease the amount of loss. And in fact, what they find is the oxide thickness correlates directly to the amount of loss. So it's clear that removing the oxide leads to less loss. We then did similar calculations, similar measurements on a number of different regions, so things like the metal substrate interface, substrate air, and we were able to estimate the total contribution in terms of loss that these introduce. And we found is that while all of them introduce loss, nothing is quite as severe as the metal-air interface or this niobium oxide. So it was extraordinarily clear to us that if we want to drive performance further, if we want to get to the state of the art in terms of coherence time, we need to address this niobium oxide interface. But at the same time, it gives us a roadmap. It tells us that if we're able to reduce the decoherence here, we can then start to think about the substrate, we can then start to think about the Josephson junction, the film itself, as well as then moving on to multi-qubit chips and be able to drive coherence from what it is in terms of tens of microseconds now all the way up to millisecond levels. So that's what we did. So our strategy here was to figure out a way to prevent this surface oxide from forming. And to do that, we took a niobium film in a vacuum chamber, and then we immediately sputtered on top another film on that. So whether it's tantalum, aluminum, or titanium nitride, various films, and then took it out of vacuum. In this case, we were able to prevent the niobium oxide from forming, and then went through with the remainder photolithography and then the various etching processes. Again, the hypothesis here is by forming this protective shield on the niobium and preventing it from oxidizing, we should be able to see a significant improvement in terms of the coherence times. So in terms of practice, here's what we see. Again, we have a superconducting circuit fabricated here. Again, if we take a cross-section of the chip, we see this interface in here with the niobium layer on the underlying sapphire, as well as this region that corresponds to this capping layer, this capping shield that prevents it from oxidizing. If we zoom in on this region, here we see what I'm talking about. A few nanometers of tantalum, a few nanometers of titanium nitride, a few nanometers of aluminum that are on top of this niobium and protecting anything from forming. Whoops, what just happened? Okay, so then we wanted to, of course, actually address how effective this approach is at preventing oxidation. So we again used time-of-flight secondary ion mass spectrometry, and we measured the amount of niobium oxide present in our sample. And we find is that there's a 1,000 times decrease in terms of the oxide layer right at this interface between the capping layer and the niobium. So here, this is the amount of niobium oxide that's present for a pristine sample. If we then compare it with tantalum, titanium nitride, aluminum, in all cases, we're able to dramatically reduce the amount of niobium oxide present. So this is great and all. This is a really nice material science study, but then the question becomes, does it actually matter? Does it actually impact the coherence time of these superconducting qubits? And fortunately, the answer is yes. It's very dramatic, in fact. Is that if we take a look at this niobium, this is the baseline niobium chip, and then we compare to each of the different caps layers, so tantalum, titanium nitride, aluminum, we see that the average coherence time across a number of different devices is 3 to 5 times higher. In fact, we even measured a coherence time on the order of 198 microseconds, which is quite high, and I'll compare this directly to the actual literature in a couple slides, but we've got 198 microseconds in terms of lifetime for a superconducting qubit chip. The story gets more exciting. So of course, our goal here wasn't simply to make a single qubit, a single high fidelity qubit, wash our hands, move on to a different topic, but it's to really produce a industrial level process that can allow us to actually fabricate superconducting qubits on a scalable level so we can actually get to the consumer. So what we did was we again worked with Rigetti Computing. We provided them with the recipe. They repeated it in their fab, and what did they see? Well, here we see the results. So here are niobium qubits, which they were seeing. So just for niobium, they were seeing on the order of 150 microseconds for T1 for their various devices. The moment they capped, they saw a significant boost on the order of 200, 250 microseconds. In fact, there were many measurements, many devices where the maximum coherence time was the order of 450 microseconds, which is actually incredible in terms of where this actually stacks in terms of the field itself. For instance, if we compare, so here the measurements that we saw are in the order of 450 microseconds, 200 microseconds, and in terms of all reported literature, this falls quite nicely in terms of the highest reported times ever. And while this is great, it's great to have a world record in terms of the highest coherence. What's much more impressive and much more interesting from my standpoint is that now we know how we got there. We were able to actually identify that key loss mechanism and be able to remove it. And because we've done this study, because we have this infrastructure in terms of understanding what these other defects are, we can continue to repeat this process. We can do the same thing for the substrate. We can do the same thing for different interfaces and continue to climb up this ladder that I described before. So for instance, I'll take it one step further, is that this question becomes, so we've done this for niobium, we've removed the niobium oxide, we've capped it with tantalum, but the tantalum still oxidizes. The tantalum forms a tantalum oxide. So why is this less lossy? In fact, if we see an image here, we see the tantalum oxide on top of the tantalum, and just optically it looks pretty much identical to the niobium oxide on niobium. So what's different here? And this is something that we're still trying to study. We're still trying to get a better handle for what exactly is going on. But what's interesting is that what we find is that in the tantalum oxide, if we take a spectra known as, if we take an EEL spectra, so this is an electron energy loss spectroscopy, we find that the peaks associated with the tantalum oxide remain constant throughout the entire oxide. Whereas for the niobium oxide, is something I talked about before, is that they have a lot of vacancies, a lot of variation, and that can lead to the difference in terms of magnetic dipoles. So this oxide appears to be much more stoichiometric and something that requires further analysis. Additionally, another area that we found is that when we etch the chip, we form these qubits, we find that it actually oxidizes on the side wall. So here we have capped it on the top, but we have not capped it on the side. So this leads to the presence of this oxide here. So this is something we want to remove moving forward, and if we're able to remove this, I have no doubt that it will continue to improve the performance. So to summarize, I just want to say that examining the materials associated with superconducting qubits is critical to improving performance. And using a wide variety of different characterization techniques, we've seen that oxygen vacancies are linked to amorphous niobium oxide. Niobium hydride precipitates form at low temperatures, which are non-superconducting and may be problematic in terms of performance, as well as intermetallics. And then through this sort of really sophisticated, robust approach in terms of identifying the particular defects that are present in these different samples, we're able to remove the niobium oxide and lead to a 3 to 5 times improvement in terms of performance. So in terms of next steps, and this again is the most exciting part for me because now we know how we can go even further. We know where we can try to figure out ways to remove the surface oxide on the sidewalls. We can now try to address the remaining sources of decoherence. And then climb up this ladder in terms of here's where we are, and here's how we continue to climb in the order of milliseconds, and even seconds in terms of coherence time for superconducting qubits. So with that, a number of folks I want to acknowledge across a number of different institutions, and if you're interested in the work I talked about at the very end in terms of the state of the art, that is this manuscript seen here, which is available on arXiv, and I'm happy to take any questions.
Thank you for the interesting talk. Do we have any questions from the audience?
A quick question. When you're doing capping, one of the sort of obvious capping layer would be forming niobium nitride, which is very stable, but somehow you do not do it? What's the reason?
Yeah, so I think a lot of it is, this capping project is still in its infancy. There are a number of different materials that we want to try. And we're actually doing a lot of calculations in terms of identifying which ones are the best barriers, which ones are superconducting at low temperature, which ones proximatize, and which ones are crystalline. So those are the three sort of parameters we're looking at. The niobium nitride didn't make the first cut, primarily because it's not something that, in a lot of cases, it forms non-uniformly, so you'll have very thick in one region, thinner in other regions, and that would lead to changes in terms of superconducting properties. So we were much more focused on, we started by trying to look at layers that we could form conformally, but these are additional things we're looking at. So for instance, we looked at titanium nitride, but right now that's in consideration as well. So thank you.
Hi. So I have two questions, if there's time for two questions. My first question is, have you studied the difference between controlled oxidation of the niobium surface or just like exposing it to atmosphere and characterizing that?
Yeah, so that's a wonderful question. So we haven't studied it too in depth. We've studied in terms of figuring out like how quickly it grows. But what's interesting about the niobium oxide is that the moment you take it out of ambient conditions, within seconds you'll have an oxide that forms. Within an hour you'll have a fully formed oxide. So you can continue introducing oxygen, but at some point it's self-limiting and no longer begins to grow. So from our standpoint, what was a much more interesting question was how do we entirely remove it altogether, as opposed to spending as much time thinking about how it forms, things like that.
Okay. My other question is, so you've encapsulated your niobium layer in tantalum or aluminum. There have been a lot of improvements in superconducting qubits these days using just plain tantalum, coherence times of like milliseconds. So what advantage does niobium encapsulated in tantalum have over just plain old tantalum?
Yeah, so that's a great question. So one small thing is, even the tantalum one, the fully tantalum ones are still similar order, if not lower, in terms of what we've seen. So they're on 200 microseconds, 400 microseconds, 500 microseconds, so right there with us. What we're primarily, our standpoint, our viewpoint is that we know, especially at Fermilab, we know that the niobium metal particularly has a photon lifetime of 2 seconds. That one we've studied to that, and we know that in the quantum regime. 2 seconds would be extraordinary in terms of coherence time for a superconducting qubit, because we're talking about microseconds. So we're very confident in the fact that the metal is not the limiting factor. So if that's the basis, then the question becomes, why would we move to a different metal if the limiting factor is the oxide? So our sort of approach then is that let's keep the metal, which we know is great, and simply address the oxide. Because if we start changing all over the place, if we start going to tantalum, maybe it'll turn out that tantalum is not as good of a metal. With all that said, we are also repeating the studies with tantalum, but that is our philosophy on it.
Thanks.
You're trading one uncontrolled oxide for another. Mm-hmm. And it's not surprising at all that the one with aluminum is only slightly better than your niobium. Mm-hmm. And it's also not getting one peak coherence time, it's the distribution of coherence times. Mm-hmm. And with Rigetti, it seemed like there was a very wide distribution. Is that correct?
Yeah. So those are all wonderful questions. Yeah.
Excuse me?
Yeah. So I think the main thing is, I do want to highlight that the main thing we should be looking at in these box plots are the plots themselves. So this is the 25th to 75th percentile. These low measurements are sort of pervasive for all. And what that happens is that over time, there tend to be various two-level systems in which that interact with the actual system, or which interact with the qubit, and that leads to an extraordinarily low. So no matter what device we're dealing with right now, you'll have those low measurements. With that, yeah, okay.
Yeah, it wasn't just that they're low, that there's a
yes.
big spread, yes. And picking out just the highest one yes. has limited utility in anything you're trying to integrate. Mm-hmm. And controlling the oxide could be beneficial. I think someone's already mentioned it. Mm-hmm. What you're doing now is just putting another metal on, mm-hmm. and then you take it out of the vacuum. You could put another metal on like you do, and that has a stable oxide formation that you can control in vacuum. And that might cut down on the distribution.
Exactly. Yeah, so it's a great question. So we're actually doing that in progress right now. We have measurements planned is capping with gold, capping with platinum, capping with palladium. These are all things that don't oxidize. And if they do oxidize, they form a very, very sub-nanometer thick oxide. And we're very curious to see what the results look like. It's a wonderful question. And hopefully in a month or so, I'll have results for you on that.
So another group of folks who I imagine would be interested in this type of work are accelerator scientists and engineers.
Yep.
I imagine there's plenty of them at Fermilab. I was just curious if you and your group were in contact with those folks.
Yeah, that's a great question. A lot of these ideas actually spun out of our accelerator project. In fact, the whole SQMS center is from the accelerator physics. And the idea of encapsulation has been something that they've been thinking about in that field for years, particularly for high electron fields. So yeah, the short answer is yes, and the long answer is this is something that we want to identify what this perfect or the ideal capping layer is, and then that's something that's translatable for there as well. Thank you.
Time for one more question. Okay, let's thank our speaker one more time.
All right. Hi, y'all. We have about 25 minutes left before we take our next break. We are going to go ahead and have a panel discussion here. So if I can have all the speakers for the day come pick out a high chair and make themselves comfortable. We're going to have a more casual discussions here for the next 20-25 minutes. And then we'll head on over to Burke for our networking, lab tours, and poster sessions.
Quick announcements for students who are giving posters up at Burke. Please make sure you grab your poster as we leave to head up for the tours, and we'll set up in the Burke atrium with your posters. So make sure you pick those up out here. We're right by the registration table.
All right, if I can have...
You won't leave one mic for Q&A, right?
Do two mic, you can mic me up on the biggest screen.
Well, go. Okay. Yeah, so I've got 2 hand mics and 2 clip-on mics.
Yeah.
So I need to say at least 1 hand mic for Q&A.
Yes.
So then,
Yeah,
I guess we're gonna have to pass one of those around.
Yeah.
These around.
Yeah.
Go ahead and.
Oh, you're mic'd up.
I was going to pass it.
I'll just leave this mic. Nobody's asking a question.
We are
Funny
gathered.
for us. That's hilarious. Oh, you actually are. Yeah. So I've only got 2 clip-on mics in that here. So one. You guys want to? I don't know, it's too.
Travis, you coming up? We made space for you.
I thought there was already taken.
No, you got it.
Trying to get out of this.
Oh, man. Let's see what you're doing. All right, so before we start a more casual panel, since we had a quick transition between all the talks, is there any other more technical questions from the audience for any specific speaker? I'll run this mic around. If not, if you think of something else, I'll open it up towards the last 5 minutes. Otherwise, we've got a very wide array of speakers here. I'll just go through them real quick just to rejig your memory here. So in no particular order, in the order they presented today, we have Dr. Travis Hombo, the Director of Quantum Science Center and Associate at Oak Ridge National Lab. And then we have Professor Mike Manfra, who's the professor here at Purdue University and a director for Microsoft Quantum Lab in West Lafayette. We have Professor Suzanne Yellen, professor at Harvard University, Professor Dana Anderson, Chief Strategy Officer at Inflection, formerly CoQuanta, and a professor in Colorado Boulder. And we have Professor Misha Lukin from Harvard University, and we have Professor Igor Arnautovich from University of Sydney. And we have Akshay Murthy, the deputy head of Qubit and Materials Department, SQMS division in Fermi Lab. So these are all our panelists today. If you have any questions in between, feel free to chime in. So yes, Sam.
Morris, I think you're moderating.
Yes, I'm moderating. I'm Morris. I am in the lab under the guidance of Professor Shalaev and Professor Boltaseva, working in quantum optics. So first question, more broad here. So I know, reading up on most of the speakers here, you all came from different physics and background that's not necessarily quantum computing and quantum information sciences. At what point in your career did quantum technologies kind of come into the picture for you, and you decided that's something you wanted to work on? Let's start from Akshay here.
Sure, that's it.
I
feel like they have more interesting answers, yeah.
Okay. Professor Manfred, you want to start? When did quantum technologies, quantum computing come into your career, and where did you start?
Oh, thank you. Roughly 2004, 2005 at Bell Labs.
Nice. All right.
So it's been a while.
Yeah. And what intrigued you to stay in it?
The experimental challenge, actually.
Okay.
And trying to use some actually new physics for a technology, physics that wasn't completely understood, and that had no real basis for being a technology. So if it could, that'd be really cool. So I thought that was a great challenge.
All right, Professor Lukin.
So my background is in quantum optics, and quantum optics it's basically a field of science which studies the interaction between light and matter at the quantum level. And this always has been a field of fundamental science, but it always had some kind of like applied side to that. For example, understanding the limit of interferometers and things like this. And actually experimental quantum information science in many ways has actually originated in the field of quantum optics. So in fact, while during my PhD, I did not work on quantum information. It was kind of very early on, around 96, 97, that I was very intrigued by that. And I saw a lot of potential and also a lot of challenge. And I think this is, what attracts scientists to the, solving challenging problem and learning how the world works and how far you can push is what, is what's really exciting.
It was Thursday, September 23rd, 1980. Actually, Misha and I are academic brothers. We had the same PhD advisor, just somewhat different, almost a generation apart, not quite. But mine was really when I got into LIGO, the Laser Interferometer Gravitational Wave Detector in the 80s. Those were the days that people first started talking about squeeze states and really understood how you could perform measurement beyond standard quantum limits and so on and so forth. So long history in it, but recently it's become realistic to not have a several $100 million project to see quantum come to fruition.
So just to repeat, my background is quantum optics, and I had the same advisor as my left neighbors. First quantum, the reason why I even joined there was that quantum was so different. Now I'm still in quantum because I see that quantum is actually also realizable.
Thank you. I think I mentioned at the beginning that I was originally a chemist working in chemical control using optical pulses, and moved over starting in quantum information when I went to Oak Ridge National Laboratory. But the point where it actually became a goal for me, a career, was when I realized that quantum computers could be used to explore parts of nature that we have no access to otherwise. And that is pretty motivating for me personally. but there was no clear path on how to approach that goal. And what I'm probably most impressed with what's going on in the country at the moment is we are creating these paths now for students like yourselves to have an indication of how to accomplish these goals. So while I think many of us come from very diverse backgrounds, it seems to me that at least moving forward, there's a lot more consensus around what it means to be in quantum information.
I think, objectively speaking, I'm probably the less quantum scientist out of all of the respected people here, so I'm doing a lot of materials for quantum. But how I ended up doing that was I needed a visa to go to Australia, and the easiest way to do is to do a PhD. That was on Diamond, and I came. It was June 2007, and my supervisor told me, well, there's a workshop in 2 weeks, go and attend and learn. And in that workshop, Professor Misha Lukin presented. You probably don't remember. And it was back in the days when NV centers were still unknown and people were coupling NV center to carbon-13 and NVN, and Misha had one of the first kind of demonstrations on coherent control, and I was like, wow, that's impressive. And that's where I started to look into defects. So yeah, that's why.
Myself, like Igor, so I'm a material scientist by trade, in case you couldn't tell from the talk. But I think for me, it was very clear that quantum has the potential to impact our society through a number of different ways that we can perceive, but a number of different ways that we can't foresee moving forward. And I think that's, for me, is super exciting because that, we're at the front edge of the impact that it can make. And that combined with the fact that, at least in the technology space that I'm working in, the importance of material science is so abundantly clear, made it a no-brainer for me after I got my PhD. I started a postdoc in this area a couple of years ago, and then now I've moved up to a scientist position as well. So,
And to flip that, so you guys all kind of came in from very different backgrounds and specialities, but now you kind of see a generation, and especially in the audience, a whole generation of students and postdoc that's really coming in focused directly on quantum information, quantum computing. Do you see like huge differences in the way postdocs and grad students do research, and how would you describe it? And is there any pitfall or advantages that students and postdocs should pay attention to? And then this is more for professors in the audience, I think. I saw Professor Lukin shaking his head or reacting to something. You guys having to?
Happy to start.
Yeah.
Okay, I'm happy to start. So I think, like I like often to say that, the field now is in a kind of very special phase of the development. And, it can be quantified by several different ways. So first of all, it's already remarkable that people like us are sitting in this panel here. And what I mean by that, is like 20 years ago, people like myself and, Dana and Susanna would never talk to people like Mike,
You still may not want to.
No, but look, it's, but it is really this, this has been really, the barriers between different fields have been broken, and we are taking it for granted, but this was absolutely not, obvious, and, it started out with breaking barriers between, let's say, AMO physics and condensed matter theory, and then it turns out that we are looking and facing the problems very similar, with superconducting qubits and, and atoms, the ideas of cavity QED, circuit QED are now so much ingrained, they are taken for granted, Early on, these things, they have been kind of, really revolutionary in many ways. And so I'd And I think what happened is that it really accelerated the progress of the field dramatically, and this, this, kind of small quantum leaps, they are basically, happening, every few years. And, example that, I briefly talked about today. I mean, a few years ago, if people would ask me, when would like quantum error correction sort of will become practical, most of the people, myself included, would say, okay, somewhere between very long time and infinity, But I would like to say that I no longer think that it is the case. It's still, the road to building, large scale, utility scale quantum machines with built-in error correction is still very hard, complicated. It involves basic science, engineering, innovation, all of these things. But, I would, in my opinion, these things are now very much in sight, And I think that already kind of required, all of our communities working together. And, I think this trend will accelerate and hopefully will actually kind of elevate the field to a different level.
Since we're next to each other, I'll go next. The world has changed dramatically, very much for what Misha has just said, but also in terms of culture in many respects. And especially the students and postdocs. The beautiful thing is now you have a lot more opportunities for what you're doing to what goes next. And regarding pitfalls, I want to encourage you to look at your choices. I usually say, take your destiny in your own hands. Take a look at industry, take a look at national labs, take a look at academics, and do some homework, get some insight, because you have the choice, pretty much, of where you want to go. And since, in that sense, it's definitely what we say a seller's market, explore your opportunities and choose wisely. Do an internship, talk to people in industry, talk to people at national labs, speak with people in academics. You have the choice. Next, another aspect of the national and global landscape that has changed is, in my day, somebody like me who studied quantum optics would either go into academics or possibly one of the most admired places in the world was AT&T Bell Labs or Xerox PARC or IBM. The world has changed. They are not the ones any longer that do the forefront research. It happens now much more in academics. It happens much more even in small companies, commercial companies. That landscape has changed. And what has particularly happened is much more of the innovation, with all respect to Microsoft who's here and IBM who's here, a lot of the innovation takes place through entrepreneurial activities. QEra, Atom Computing, IonQ, they're really pushing the forefront of the science combined with technology. That's different. So look at your landscape thoroughly and early before you actually are kicked out and have to choose.
So since a lot of the bases are covered already, let me zoom in on one particular aspect that probably kind of was included in your question. There is all this quantum hype, and there's a lot of people who are speaking about hype in this context. The pitfalls are obvious, right? The pitfalls are you have a new idea how to build a quantum computer, and you go to whatever the New York Times and say, I have the solution, the quantum computer is here, tomorrow we are factoring 100-digit number, and the day after tomorrow we solve the climate problem. On the other hand, that's the effect that the hype has on one half of the population. The other half of the population, they say, oh, there's this hype and I'm really afraid of that, so I would like to do something which is more grounded. And I would say none of the two is correct. And I think go for it. Go, in particular, if that's something which interests you anyway. But do ask yourself, is it realistic? Is it interesting? So is it of any use for humankind? And can I personally contribute something to it? For the last question, be be somewhat bold, but don't be totally unrealistic. For example, the student who was leading this work I was talking about today, for both of the papers that we have out, one published, one on the archive, immediately got approached by some popular science magazines who wanted to interview him. And he came to me and said, oh man, how do I tell them that I don't want to do that? I don't want to subscribe to this hype. And we talked a little bit about that, and he actually talked to them and made it very clear that he does not want them to kind of include in their article any promises that he is not willing to kind of undersign, and whatever put as a milestone in a DARPA proposal or something like that. And that was for the first one. And for the second one, they nevertheless came back and wrote it like that. People are still interested in that. So don't be afraid of the hype. Be glad that there's a lot of funding in it, both in academia and in industry. And be also not afraid to be realistic about it.
Thanks, Suzanne. So when I had my first postdoc, I had gotten a car from my grandparents. It was an Oldsmobile, it was very dated, and one day it didn't start. So I wasn't able to leave work, and I got picked up basically hitchhiking, trying to get home. And this guy, he was also a scientist from the laboratory, he said, well, what do you work on? I said, oh, I'm working on teleportation. And he just laughed the entire ride home. He said, oh my gosh, wait until you have to get a real job. And you know, this was 20 years ago, and I can appreciate the fact that at the time, he didn't recognize the significance of what's going on. But now things have changed. And I really liked what Suzanne said about being bold. You are in a position that I certainly was not, which is you are afforded the opportunity to be bold in your future around this topic. And so I would encourage you to do that. While I appreciate Morris's point that, you know, we have gone through our struggles to get to where we are today, I would not overlook the fact that you are also going through a period of immense change, just like Dana was saying, both in terms of the field as well as society itself. The people who come the generation after you will have it much easier than you are having it right now. So the decisions you're making and the paths that you are forging for them will have an enormous impact. You've probably seen this book, Quantum Computing for Babies, very popular. It's probably been out 5 years. Even if you bought that book the day it came out, we've got 15 years before those babies are going to be ready for quantum. So the things that you're doing now, the things that you are helping us shape, I think are incredibly important. So be bold.
I guess a lot have been said, so I of course agree with most of it. I would also maybe add that a bit of more, not pessimistic, but more be realistic view that the quantum winter will also come. There's a beautiful blog by, the name escaped me, I forgot, the theoretical physicist. About the quantum winter. But you know, all of you have an opportunity to get the best training. You're in one of the best places around the world to do so. So get training, head in the sky, legs on the ground, look beyond quantum. When you're going to be sitting on these chairs, maybe quantum is not going to be a thing anymore. It will be like the carbon nanotube elevator to the moon. Who remembers carbon nanotubes anymore? So just open-minded, that's, I guess, my message. You get the training, the best training you can, and then open-minded, and off you go.
Thank you. We've got time for one more question, then we kind of have to wrap it up. Is there any question from the audience? So I guess since last year, so I have one last question, and maybe this is more, I guess for some of you, you already use it, but not all of you. So since last year, I know the field of machine learning and AI has exploded, and now that it's becoming with natural language bots, it's becoming accessible to everyone. Are you thinking of incorporating, if you don't already, incorporating machine learning and AI into your research? And do you think there should be something similar, analogous in quantum computing and quantum physics that can be used to pick up more interest from the general public into the field of quantum sciences?
attended this. I mean, if you don't make use of ChatGPT, it's really your own fault. let me say that much. It's great. It's dangerous, but it's in particular great.
Actually, I don't think machine learning, the fact is it's just not new. Ironically, while I was also doing LIGO, so was the neural networks going through its second revolution. Now it's its third. So in fact, it's in some sense always been embedded, at least in my domain. And it's, as I say, it's really, I mean, there's as much hype there as there is in quantum computing. The main change is just that the technology of the processors, the GPUs, NVIDIA devices, have made it more doable on real problems. But in terms of applying it to physics, I just don't think it's ever really gone away. He can answer later.
Yeah. Okay, so so maybe what I would like to kind of add here is that in this development of kind of AI, it's an interesting kind of story, in some way interesting example, for the field of quantum. There will likely be a day like this in quantum when people will wake up and say, oh God, these things are here, and maybe not immediately in everyday life, maybe first in science, and as Dana says that in science, AI has been around already and has never gone away. But I like to tell people the story when I first went I was still a postdoc, but I was asked to come to DARPA to present, something which was sort of a program DARPA was planning, and it was an interesting experience. There was a scientist from the Bell Labs at the time, originally from the Bell Labs, who was a deputy director of DARPA for a long time, and he was very sharp, but he had a particular view. He basically thought that everything interesting which could have been done, was done in the Bell Labs. And if some people propose something which was not done in the Bell Labs, it will never get done, And so he basically, in front of me, kind of demolished the people who were presenting. So he treated me kind of kindly because I was a junior person there. But basically what happened was after that, the DARPA program manager, who I think was actually Jack Shah, but it was not a person who was someone else. But he actually had to kind of talk to me to explain what this DARPA is about. And he said, look, at DARPA we invest in like visionary ideas, and we take pride in the fact that some of them never work. And he gave me an example of one field which DARPA invested heavily, but it just really failed to produce anything of value. Guess what was it? It was artificial intelligence, and the year was 2000, maybe 2001 or 2002. But the moral of the story is that basically during the 90s and then during the kind of 2000s, there are a lot of knowledge have been created, a lot of techniques, a lot of theory, a lot of technology has been developed, and then with the advance of more powerful computers, all of a sudden these ideas paid off. So basically, when people talk about quantum winter and things like this, I do not necessarily buy this kind of conversation. It is for sure true that many of startups, will not be, there. I mean, there are a lot of promises which are made, which are not completely unrealistic, and hopefully that will be cleaned up. But this foundational knowledge that, we are creating, that you guys are creating through your work, will be there to stay. And someday, it will be useful not just for scientists, but maybe for the world at large.
I'm not an expert in machine learning, but nevertheless, it is something that we use, not in the actual compute process, but clearly when we have multiple qubits, be they spin qubits or the hybrid structures that we work on, tuning those devices up, becomes intractable for a human. At some point, the human is not going to sit there and fine-tune 1,000 gates. And no, it won't work. And so certainly there's great need and utility in having that done by machines. And so that's a concrete example where we are certainly considering it in my work with Microsoft as well.
And unless any other speakers has a comment. All right, cool, awesome. Unfortunately, that's all the time we have. I want to thank all of our speakers for their great talks today and taking the time. We have an extended break, about 10-15 minutes, and afterward, if you are interested in joining us for our lab tours at Berk Nanotechnology Center, Zach and Sam can slowly walk you over to the building, and we'll meet there in the atrium. If you're not interested in the tour, I encourage you to still come back around later to Berk Nanotechnology Center for our poster session to see all the great work your fellow graduate students and postdocs are doing, and get some of these speakers' attention then. All right, thank you so much, y'all. See you then.